In this video, we'll create a deployment and scale the deployment using the kubectl scale command. Before we start, let's focus on deployments. Objective of deployment in Kubernetes is to provide capability to describe a desired state in deployment. We need to also understand that deployment controller internally will change the actual state to the desired state at a controlled rate. Now let's go ahead and see what all we can define when we are creating a deployment. To create a deployment, we need to write a manifest file. That manifest file will contain entries that helps us to create replica sets. It also facilitates us to define container specs. Let's go ahead and open the file. To open the file, we'll go to the prompt, we'll write vi, and we'll give a space followed by deployment v2.yaml. We'll press enter. Once you'll press enter, it will open a file. These are the entries that you need to make in order to create a deployment. First two lines specifies API version and kind. We need to ensure that we are using API version by specifying API version : followed by app/v1. Kind need to be deployment. Then comes role of metadata, which is in line 3 in the current YAML file. Metadata contains two essential elements. First is name, that gives a name to the deployment. We are using tomcat-deployment. Other element of metadata is labels that helps us to identify the resources. And we are using one label, that is app:tomcat. It is followed by spec, where we specify the desired number of replica sets. We are using replicas :3. And then we are using selector. Selector contains element called as match labels, where we are using the label that is defined in metadata of deployment, which is app:tomcat. Spec also is used in order to specify template, where we are giving metadata labels app:tomcat. And finally, we need to give specification for containers. And that we are specifying by writing spec:, which contains specified using containers : and then we are giving specification of the container that we want to use, which contains name, specified by name : followed by tomcat, followed by image : tomcat : latest, in order to ensure that we are able to pull the latest image. And we are also specifying ports. For ports, we are taking container port specified as container port : 8080. You need to ensure that you are maintaining the right hierarchy of YAML file. After writing the file, we'll save and we'll exit. To save, we'll press escape followed by :wq. Now we have created the declarative definition of deployment that we want to create. Let's go ahead and create it. To create, we'll write kubectl followed by space, followed by apply, followed by a space, and then we'll specify -f followed by a space and name of the file, which is the previous file that we created, named deployment v2.yml. We'll press enter. Once you'll press enter, you will get a message that indicates that you have created a deployment, and name of the deployment is tomcat-deployment. Now let's go and describe tomcat-deployment. To do that, we'll use a command called kubectl followed by a space, followed by describe, followed by a space, followed by deployment, followed by a space, and we'll specify name of the deployment that we want to describe. After specifying name, we'll press enter. Once you'll press enter, it will give you complete detail of the deployment. Let's go to the conditions section, which has type, status, and reason, which indicates available, true, minimum replicas available, and there are certain progressing, status is true, and new replica set available. Below that, you will find new replica set, which indicates that your deployment, which is tomcat-deployment, -alphanumeric combination of identifier, it states that 3 out of 3 replicas are created. This is how you will be able to see the status and also number of replicas which are created for your current deployment. We'll clear the screen by writing clear at the prompt. Now our next objective is to scale the deployment that you created, which can be done using kubectl scale command. Let's go and specify kubectl followed by space, followed by scale, followed by space, we'll write deployment.v1.apps, we'll give a slash, followed by name of the deployment, which is tomcat-deployment. We'll specify the name. After specifying the name, we need to plan how many replicas we need. To do that, we'll give a space and we'll write -- replicas, followed by equal to, followed by 5. Because we want 5 replicas instead of 3 existing replicas. We'll press enter. Once you'll press enter, it will show you a message that indicates that your tomcat-deployment has been scaled. Let's go ahead and write kubectl, followed by space, followed by get, followed by space, followed by rs to see the replica sets. We'll press enter. Once you'll press enter, you'll get all the replica sets which are currently present in your cluster. Our recently created deployment, which is there in line number 2, with the name tomcat-deployment-alphanumeric number, it shows that now it is scaled to 5, current is 5, and ready is 5. This is how you'll be able to create a deployment and scale the deployment using kubectl scale command. In this video, we'll demonstrate how to use kubectl to scale stateful sets and make in-place updates on the scaleful sets. Scaleful sets is the workload API object, and primary objective of scaleful sets is to manage stateful applications. It manages deployments and scaling of a set of pods by ensuring ordering and uniqueness of the pods. There is a classic difference between deployment and stateful set. And that is, unlike a deployment, a stateful set will maintain a sticky identification for each of their pods. Now let's go ahead and find out how many stateful sets are currently present in our cluster. To do that, we'll be using a command at the prompt by writing kubectl, followed by space, followed by get, followed by space, followed by stateful sets. We'll press enter. Once you'll press enter, you'll find that you have 2. One is Tomcat app and second is web. Let's go ahead and use Tomcat app in order to see how to use kubectl command to scale the stateful sets. And to do that, we'll be using a command that starts with kubectl, followed by space, followed by scale, followed by space, followed by stateful sets. After writing stateful sets, we'll give a space and we'll specify name of the stateful set that we want to scale. And name is Tomcat app. After specifying name, we'll give a space and we'll specify -- replicas equal to the new replica number that you want to specify. We can clearly see in the previous command when we used kubectl get stateful sets, Tomcat app was showing 1 replica which is defined. Let's go ahead and scale it to 5. To do that, we'll specify 5 and we'll press enter. Once you'll press enter, you'll find that scaleful set named Tomcat app has scaled. Let's go and confirm it. To confirm it, we'll write kubectl followed by space, followed by get, followed by space, followed by stateful sets. We'll press enter. Once you'll press enter, you'll find that now the new configuration of replicas have changed from 1 to 5. Now let's go and see how do we make in-place update on stateful sets. To do that, we'll open the file which we have configured in order to create Tomcat app. To open, we'll write vi followed by space, followed by the name of the file which is stateful set example.yml. We'll press enter. Now we'll go and we'll make some changes in the current file. To do that, let's go and change the ports. From 88, we'll change the port to 90, for which, depending on the editor, you need to move to edit mode. If you are using VI editor, you have to press Escape I. It changes to insert mode. You can change whatever you wish to. Assuming that we have changed the port numbers in the current file to a different number, we are changing from 88 to 90. After making the changes, we'll press Escape followed by WQ in order to save and exit from the editor. Now we need to execute the updates. To execute the update, since we have created it using kubectl apply, will be again using kubectl, followed by space, followed by apply, followed by space, followed by -f, followed by space, and will specify name of the file that we have recently updated. We'll press enter. Once you'll press enter, instead of created, you'll find that it displays message that it is configured. Apart from this, you can also go ahead and use kubectl edit command or kubectl patch commands. These are three commands that can be used in order to apply your make in place updates on your stateful sets. In this video, we'll create and define a horizontal pod autoscaler that autoscales target replica set on basis of the CPU usage of the replicated pods. Now let's go ahead and extend the deployment that we created and we scaled in video titled Scaling Deployment. We are doing that in order to ensure that that particular deployment is exposed as a service using service configuration. Let's go ahead and open the file. To open the file, at the prompt we'll write vi followed by space followed by deployment v4.yml. We'll press enter. We have already discussed configuration file of the deployment in the video titled Scaling Deployment. What we are doing here is we are adding a service. We'll quickly move to the element from where we are declaring the service for the current deployment. And we are doing that by using triple dash after the deployment configuration in order to start a new configuration. First two lines indicates API version and kind. Instead of taking deployment as kind, we are taking service as kind. Next, we are using metadata in order to specify values to name, which is tomcat-deployment. Labels, we are using app:/tomcat. Post that, we are defining specifications for the service, where we are using spec:, followed by ports:. We are using only one port for now to expose the deployment as a service, and that is specified using port:8080. Dash before port is used in order to specify the hierarchy in YML file. Next is the selector, where we are using app:/tomcat. After defining the service as well as deployment, we'll save the file by pressing escape WQ and we'll press enter. Once you'll press enter, you'll come back to the command prompt where now you need to run the command that should create not only deployment but also service. To do that, we'll write kubectl followed by a space followed by apply followed by space followed by -f followed by space followed by name of the file, which is deployment v4.yml. After writing the name of the file, we'll press enter. Once you'll press enter, you'll find that since deployment was already created in the previous lab titled Scaling Deployment, it is showing that now your deployment.app/tomcat-deployment is configured. Be careful, it's not created because it was created in the previous lab titled Scaling Deployments. But for service, it is indicating that service/tomcat-deployment is created. So now you have deployment and service created. Now, since the service is running, it's the right time to create the autoscaler. In order to create a horizontal pod autoscaler that takes responsibility of maintaining replicas of the pod, depending on your need, you have to use command called kubectl autoscale to create horizontal pod scaler. Primary objective of horizontal pod autoscaler is to increase and decrease the number of replicas in order to maintain an average CPU utilization across all the pods. Let's go ahead and create horizontal pod autoscaler, keeping in mind CPU and the recommended usage of replicated pods. To do that, we'll write a command called kubectl followed by space, followed by autoscale, followed by space, followed by deployment, followed by space, specify name of the deployment, which is tomcat-deployment, followed by space. Now you have to factor out CPU usage. We'll specify space followed by -CPU-% equal to 40. Now we have specified detail to horizontal pod scaler where it has to maintain an average CPU utilization of 40% across all the pods. Next objective is to specify min and max. To do that, we'll give a space. We'll write dash dash min equal to, let's take 3. We'll give a space and we'll specify max by using dash dash max equal to 7. We'll press enter. Once you'll press enter, you'll find that horizontal pod autoscaler is created and it will take responsibility of increasing and decreasing the number of replicas in order to maintain an average CPU usage of 40% in the current case. This is how you'll be able to create and define horizontal pod autoscaler that autoscales target replica set depending on CPU usage of the replicated pods. In this video, let's describe the concept of daemon set and the patterns that can be used to communicate with pods in a daemon set. Now we know that daemon set is a process that runs in background. Since daemon set runs in background, it can be used to monitor resources like pods in order to decide either to create new pods or to kill existing pods. Apart from that, daemon set also does not provide any visible output to users. And finally, we can say that Kubernetes provides daemon set to manage all the daemon processes that runs in background. Now let's try to understand what is daemon set in Kubernetes. Daemon set in Kubernetes was introduced as an extension API in version 1.1, and this is the reason why we call it as part of extension API in Kubernetes. It takes responsibility and ensures that some or all nodes run pod, and that is decided by node selector. Now, after understanding what is daemon set in Kubernetes, let's try to understand how do we configure daemon set, for which we'll be using a diagram which is currently displayed on the screen. In the left side of the diagram, we have the configuration details, where we are configuring daemon set. In the configuration detail box, first 2 lines specifies the API version and kind. Metadata is used in order to give name to daemon set and also bind that daemon set with some labels. We are using name as ds-production and labels as apps::production. Then comes spec, which has selector. Selector has a property called as apps. We are specifying it to be production. After spec and specifying the selector, we are using template, and inside template we have a property called metadata, and that property have 2 essential features. First is name and second is labels. We are using labels that we have specified when we are defining metadata for daemon set. And finally we have the spec, which is all about what that daemon set need to do. Spec specifies that host network is true. It means that it will be network based. Then containers that it will create will be named as ds-prod, and image that it will use is bm/prod::v2. This configuration file will be used to create daemon set, which will run in background. Now let's try to understand the diagram. In the diagram, we have planned creating daemon set with principle of 1 monitor pod per node. So when you create daemon set by using kubectl command, it will be processed by API server, and API server will ensure that it creates 1 monitor for each node. And that particular monitor will run in background. And this is the reason why this monitor pod need to be created in form of daemon set. Now finally, let's try to understand what all are different daemon set pod access patterns. There are 3. First is traditional service, where pods in the daemon set are configured in order to send updates to some other service like stats database. Second is headless service. You can create a daemon set with headless service pattern where it creates a headless service with the same pod selector that you have used in order to create daemon set. Using that, it discovers daemon set and identifies endpoint resource or retrieves multiple A records from DNS. And third option is host port option, where pods in the daemon set will be using a host port so that pods are reachable via node IPs. So you need to decide what processes you want to run in background, and to do that you have to work with workload called as daemon set provided by Kubernetes. In this video, we'll demonstrate how to create a daemon set using the rolling update strategy. Now let's try to understand what is a daemon set first. Primary objective of daemon set is to ensure that all nodes run a copy of pod. And as nodes are added to the cluster, pods are also added to them. And as the nodes are removed from the cluster, those pods are also garbage collected or they are removed. We need to also keep in mind that deleting a daemon set will clean up the pods if they are created. So it plays an important role in resource management. Now there are two different types of update strategies which can be used in daemon set. First, on-delete. With on-delete update strategy, you'll find that after you update a daemon set template, new daemon set pods will only get created if you have manually deleted old daemon set pods. Whereas rolling update strategy indicates that after you update a daemon set template, old daemon set pods will be killed and new daemon set pods will be created automatically. Now let's go ahead and see how to create a daemon set and specify rolling update strategy to it. Now to create a daemon set, we have created a manifest file. Let's open the manifest file in order to understand the configuration. To do that, we'll write vi followed by space followed by name of the file where we have configured our daemon set with rolling update strategy. We'll press enter. First two lines indicates that you are going to use API version app/v1. Kind indicates the object type, which is daemon set. Then we are using metadata in order to give a name to daemon set, that is tomcat-daemon set. We are also binding a label to it for identification, that is app:/tomcat_d. Then we are writing the specification where we are using selector by specifying selector:, and we are specifying match labels with value app:/tomcat_d. And then comes the most important element in your current YML file, that is update strategy. We are using update strategy : followed by type : rolling update. Now we need to also specify maximum unavailable. That we are doing by specifying rolling update : and below rolling update : we are populating max unavailable to be 1 by using max unavailable : 1. Then comes the template where we are specifying metadata : below metadata : we are using labels : and we are specifying app : to be tomcat_d. And then comes specification for containers where we are using spec : containers : we are giving a name : tomcat_d. Image that we are specifying is tomcat : latest. We are also specifying termination grace period seconds, which is currently set to 60, which indicates that when your pod phase is terminating and it remains there until pod is killed, after its termination grace period seconds expires. After writing the current configuration file, we'll save and exit. To save and exit, we'll press escape followed by :wq. Now we have configured. Our next objective is to create daemon set, which we can do using kubectl create or kubectl apply. Let's go ahead and use kubectl apply because sometimes we may need to update the daemon set. To do that, we'll write kubectl followed by space followed by apply followed by space followed by -f followed by space, and we'll specify name of the file where we have configured rolling update daemon set. We'll press enter. Once you'll press enter, you will get message that indicates that your daemon set is created. Now let's go ahead and check the update strategy of the current daemon set to ensure that it is set to rolling update. To do that, first we'll clear the screen. Now let's go ahead and see what all daemon sets are currently present in our cluster. To do that, we'll write kubectl followed by space followed by get followed by space followed by daemon sets. We'll press enter. Once you'll press enter, you will get the details of all the daemon sets which are currently created. Now you would like to confirm that your current daemon set is following rolling update strategy. We'll write command that starts with kubectl followed by space, followed by get, followed by space, followed by ds, which indicates daemon set, followed by /tomcat-daemon set, which is the name of the daemon set, followed by a space, followed by -o, followed by a space, and we'll use go template. To do that, we'll write go -template equal to, we'll write an expression within double curly brace in order to ensure that it is able to get. Within curly braces, we will write .spec, .update strategy, .type, and we'll specify again double braces. Within double braces, we'll use double quotes. Within double quotes, we'll specify /n. After writing the template, you can also specify the namespace, else it will treat it to be part of the default namespace. We have created daemon set in the default namespace, so we'll not specify -n. We'll press enter. Once you'll press enter, it will display you the current strategy of your daemon set, which is rolling update. This is how you will be able to create a daemon set using rolling update strategy and use kubectl get commands in order to verify. In this video, we'll create a configuration file and use the kubectl apply command to create jobs and list all the pods that belongs to that particular job. Now, job creates one or multiple pods. Objective of job is to ensure that the specified number of them successfully terminates. And it terminates as pod successfully completes. Jobs ensures that when a specified number of completions which are successful is reached, the task is complete. Be careful when you are deleting a job, because deleting a job will clean up the pods that it created. Now let's go ahead and see how actually we can create a job, for which we have written a configuration file. We'll open the configuration file by writing vi followed by space followed by name of the file, which is jobs example v7.yml in our case. We'll press enter. First two lines specifies API version, and you'll find a change. Now instead of app, we are using batch/v1. Keep this in mind when you are creating a job, your API version should match to the batch. Second element is kind, which we have specified as job because we are going to create a job. Then we are giving metadata name in order to bind the job with the name, followed by spec where we are using template. Template is followed by metadata where we are specifying the name, and then comes the main element, which is spec, where we are specifying containers because jobs will need to create pods in order to execute, for which it needs container specification. We are giving a name to the container. Name in our case is job container that we have specified below containers : by using --name : job container. Below name, we have to specify the image, which we are specifying by writing image : followed by space followed by Ubuntu : latest. And then comes the command that we want to be executed as part of the job. You can use any command depending on capability of the image. For now, we have specified bin/bash followed by -c followed by one small script, which is for counter, followed by the count numbers, that is 9, 8, 7, 6, 5, 4, 3, 2, 1. We have terminated it by using semicolon, followed by do, echo. We need to ensure that do and echo have space, followed by a space, followed by $counter, which will refer to the variable. And finally, we are specifying done. Now, this particular script will change depending on what statements you want to execute as part of job. We have specified restart policy as never by using restart policy : never. After creating the configuration file, now we have to execute it. To do that, we'll press escape followed by :wq to save and exit from the editor. Now let's go ahead and run it. To run, we'll be using command that starts with kubectl followed by space followed by apply followed by space followed by -f followed by space, followed by name of the file, which is job examples v7.yml. We'll press enter. Once you'll press enter, you'll find that it has created the job. You can check on the status of the job by using again kubectl command. Let's go and use kubectl, followed by space, followed by describe, followed by space, and we'll specify jobs / name of the job, which is test jobs. After specifying the name, we'll press enter. Once you'll press enter, you'll find that it has started creating the pod and also states job completed. You can see that in the last few lines of the output. This is how you'll be able to create your job. Now let's go ahead and list all the pods that belongs to the current job. To do that, we'll be using command that starts with kubectl, followed by space, followed by get, followed by space, followed by pods, and you'll press enter. Once you'll press enter, you will get all the pods. Within this, you can see test jobs - alphanumeric identifier in one of the rows of current output. This is how you'll be able to list all the pods that belongs to the jobs. In this video, we'll demonstrate how to deploy a replicated topology with a stateful set controller and simulate pod and node downtime to observe resistance to downtimes. In order to build a replicated topology, you need to be aware about certain essential elements. And before that, you need to decide the topology that you want. For now, we'll go with single master topology, where you can have multiple slaves running asynchronous replication. Now let's go ahead and create a configuration file which will create config maps, services, as well as stateful set. We have already written a file. Let's go ahead and open the file by writing vi, followed by a space, followed by the name, which is replicated sets v8.yml. We'll press enter. Once you'll press enter, we'll go through the objects which we are creating. First object that we are creating is config map, that is specified using API version to be v1 and kind to be config map. Then we have metadata, where we are specifying name. Along with metadata, we are also having data where we are specifying configuration files that will be used by master config and all the slaves. After configuring config map, our second configuration is the service, for which we have used API version :v1. Kind is specified using kind :service. We are giving rest of the details in order to ensure that we are able to create an object of type service. After creating object of service, we'll be creating another service who will work as client for connecting to MySQL instances to read the data. And to do that, we have specified again API version :v1 kind :service. In short, we have created two services and config map in order to provide data to other objects. And finally, we have created stateful set, where we have used API version :apps/v1 kind :stateful set. We have specified configuration as per our choice. Most important element in the current file for stateful set is the number of replicas, which is specified just below service name under spec as replicas :3. And then we'll specify the template, metadata, and configuration of init containers, which is specified in spec. You can have as many as init containers that you want, and that you'll be able to decide depending on what configuration you want to do on service, where you will need help of your MySQL administrator. After specifying configurations, we'll save the file and we'll exit. To save, we'll press escape followed by :wq. It saves the file and it exits from the editor. Now we need to create all the objects which will build and deploy a replicated topology with the stateful set controller which was created in the file. To do that, we'll use command called kubectl, followed by space, followed by apply, followed by space, followed by -f, followed by space, and we'll specify name of the file where we have configuration of config maps, two services, and stateful set. We'll press enter. Once you'll press enter, you'll find that all the objects are created. You have config map, whose name is MySQL. You have two services. First is MySQL, which is the server. And then you have service/mysql-read, which is the client. And finally, you have stateful set.apps/mysql, which will build a stateful set controller. Now let's go and watch the startup progress. And that we will be able to do by writing command that starts with kubectl, followed by space, followed by get, followed by space, we'll write pods, followed by space, we'll specify -l, followed by space, followed by the label that we will use in order to look for all the pods. We are writing app equal to MySQL, which is one of the labels specified in all four objects which got created earlier. We'll give a space and we'll write --watch. We'll press enter. Once you'll press enter, it will show you the progress. And as soon as all the pods are created, you will get detail along with status indicating that it's running. We'll press Ctrl C because it may take some time in order to move the status to running. We'll clear the screen. After clearing the screen, now our objective is to simulate pod and node downtime to observe resistance to downtimes. And to simulate, we need to increase availability of reading from the pod of slaves instead of a single server. To do that, you can use readiness probe for MySQL. There are various ways in which you can simulate pod and node downtime. One way is to force readiness probe to fail if the command breaks. So let's go ahead and write a command. kubectl followed by space, followed by exec, followed by space, followed by mysql-0, which is the pod, followed by a space, followed by -c, followed by a space, followed by MySQL, followed by a space, and you will use --, you will give a space and you will write mv. You're trying to move. You'll give a space and you'll specify the directory. We'll specify /usr/bin/MySQL. We'll give a space and we'll specify /usr/bin/MySQL.backup. So we are taking a backup of MySQL. This is how you'll be able to deploy a replicated topology with a stateful set controller and simulate pod and node downtime to observe resistance to downtimes. In this video, we'll recognize the role of Kubernetes garbage collector along with the approach that controls dependent objects. Garbage collection is one of the essential tasks in order to ensure that resources are free and can be allocated to other pods. Now, what happens during garbage collection in Kubernetes? When garbage collection is invoked, it will pause the program which is currently in execution. Apart from that, it will mark all reachable references from current position as alive, and that activity will start from the root set. Post that, it will iterate through all the allocations which are done. It will free those who are not alive and mark the survivors as dead in order to prepare the next garbage collection round. This approach is also called as mark sweep approach of garbage collection. Now, before we understand how garbage collection works, we need to understand ownership types in Kubernetes. There are two ownership types. First, ownership in classical garbage collection. As the diagram currently displayed on the screen indicates, you will have deployment. Deployment will create multiple replica sets, and each replica set will create pods. Now, in case of ownership in classical garbage collection, it will adopt approach where each object is aware about other object that it owns, as it is indicated in the diagram. But in case if ownership is on K8s, which means that owner is Kubernetes, the owned object contains an owner reference to its owner. So in case of classical GC, each object is aware which other object it owns. But in case of ownership on K8, S, which is Kubernetes, it should contain an owner reference to its owner. This is what is classic difference between these two different type of ownerships. In short, when inspection will happen for garbage collection, in case of ownership on K8s, it will inspect the owner references of replica sets. Whereas in case of ownership in classical GC, objects are already aware, so it does not need to inspect owner references of the replica set. Now, internally, your garbage collector will look for object graph so that it can decide ownership. Now, let's try to understand object graph that gets created for an application when you create various different type of workloads that will manage that application. The diagram currently displayed on the screen indicates that you have a sample application for which you have service, deployment, config map, and secret. These are 4 different type of workloads that you have created. Deployment is a special one because it will have communication to replication controller, and replication controller, after reading replica's properties from deployment configuration, will create replicated number of pods. This is how you'll be able to intercept object graph that gets created internally. Now, whenever you delete Kubernetes object, what happens? So when you try to delete Kubernetes object, you will be following 3 different approaches. First, you'll adopt foreground deletion, which means that object itself cannot be deleted until and unless all objects that it owns are deleted. Second is background deletion, where object itself is deleted, only after which the GC, that is garbage collector, deletes the objects that it owns. And third is orphan deletion. The object itself is deleted. The owned objects are orphaned by removing the reference to the owner. So in case if object will not have reference to the owner, those objects will be treated as orphan and they will be deleted on its own. So when you are planning creation of objects, you need to understand how many objects will survive garbage collection depending on current state of objects and their ownership. In this video, we'll implement a case study of cascading deletion and managing orphans dependents. Now, what happens when we delete an object? When we delete an object, whether the object's dependents are also deleted automatically or not. Now, when dependents are automatically deleted, it is called as cascading deletion, and there are 2 different modes in which you can implement cascading deletion. Let's go ahead and see what all are the pods which are currently present in our cluster. To do that, we'll go to command prompt, and at prompt we'll write kubectl followed by space get followed by space pods, and we'll press enter. Once you'll press enter, you'll find that there are 3 different pods. Now we need to focus on cascading deletions, which can be foreground or which can also be background. Now, in order to control the cascading deletion policy, there is one important attribute that you need to use. That attribute is called as propagation policy. It's a field that needs to be specified when you are going and when you are submitting delete option as an argument to delete an object. Let's go ahead and see how we can delete dependent in background first. To do that, we'll be writing a command that starts with kubectl followed by space proxy followed by space -- port equal to 8080. Next, we have to specify curl command. That we will do by writing curl followed by space -x followed by operation which is space delete followed by space localhost colon the port where we are proxying, that is 8080 /apis /apps followed by /v1 followed by /namespaces followed by /default because we are using default namespace followed by /replica sets and name of the replica set. To specify name of the replica set, we'll specify / followed by my -repset. Now we need to specify certain options, and that is by giving a space and specifying -d followed by single quotes opening and closing. And within opening and closing, we have to specify certain properties inside curly braces. And first property is kind, which need to be specified in double quotes. We'll specify kind. We'll come out of double quotes and we'll write colon, followed by within double quotes, we'll specify delete options. After writing first key value, we'll give a comma and we'll specify second key value, which is API version within double quotes, followed by colon, followed by v1 within double quotes. And after that, we'll put a comma because we are going to specify the most important property which will help us to manage cascading deletion strategy. And that is specified using propagation policy field. After specifying propagation policy, we'll provide a colon and then we'll specify the policy, which can be background or foreground depending on your choice. Let's go with background. To do that, we'll write background within double quotes. Now we have specified the object that we need to create, where kind is delete options, API version is v1, propagation policy is background. If you want foreground, you need to change it to foreground. Finally, we'll specify header content, and that we will do by giving a space followed by -h followed by space, and within double quotes we'll specify the header property that we want to specify. We'll specify content -type followed by a colon, and after colon we'll give a space and we'll specify application/JSON. This is how you'll be able to manage cascading deletion policy. Now, once you'll press enter, it will apply cascading deletion policy. Be careful if you are deleting because it may create issues. By using the approach that we have specified, we'll be able to manage deletions. If you want orphan to be dependent, you need to just change background or foreground of propagation policy to orphan. In this video, we will list the resource types and resource units that are used in Kubernetes and then describe how pods with resource limits are executed. Typically, we can classify types of resources in Kubernetes in two broad categories. First is compute resources, which will include CPU, memory, which can be measured. And second category is API resources, which includes pods, services, config maps, etc., which are Kubernetes objects. Now, before we try to understand resource units and how pods with resource limits are executed, we need to understand quality of service classes. There are three quality of service classes provided by Kubernetes. First is best effort, where pods with no request or limits are terminated first in case of resource exhaustion. Second quality of service class that we need to consider is guaranteed. You'll find that pods where both limit and request are set for all the resources, that includes CPU and memory, along with their values are same. Now, these pods are considered to be high priority pods. Therefore, they are terminated only if they are over limit and there are no lower priority pods to terminate. And third is interesting one, which is burstable. These will be applied for pods where both request and limits are set for one or more resources, that include CPU and memory, but their values are not the same. These pods are terminated only when there are no best effort pods available to terminate. Now let's try to understand resource request and limit works. And that we will do using a table which is currently displayed on the screen. We need to know that Kubernetes scheduler will always make sure that sum of all the compute resources of containers that are running on instances are never exceeding the overall allocated resources for pods. And in order to do that, we'll be using request and limit. Request is considered as ask for the resource amount Kubernetes will guarantee a pod. How much resource is being guaranteed by Kubernetes that can be allocated to a pod. Second is limit, which specifies maximum resource amount Kubernetes will allow a pod to use. In short, pod scheduling is always based on request, not limit, but a pod and its containers will be never allowed to exceed the limit that you have specified in configuration. Finally, we need to find out when nodes are appropriate. there are 4 conditions which nodes need to meet. Where first condition is they fulfill pod resource requirement. Second is they always satisfy node restrictions. Third is they satisfy pod's special relationship requirements. And finally, they ensure the overall cluster resources are properly utilized. These are 4 essential requirements that node need to meet in order to be appropriate node for usage. In this video, we'll demonstrate the composition of deployment and the service resources using the Kustomize tool. You need to first ensure that you have Kustomize tool installed. To do that, you need to go to prompt, and at prompt, you need to write Kustomize. After writing Kustomize, press enter. Once you'll press enter, it will show you that Kustomize is installed. Apart from that, it also gives you certain details to go through help section. We'll clear the screen. After confirming that Kustomize is installed, you need to locate those files for which you want Kustomize to create composition. We have created 2 files. One of the file contains details of the deployment and other file contains details of service. These 2 YAML files are there which are configured. Now you want to create a composition. To do that, you'll be creating a file called customization.yaml. Let's go and open the file. To open the file, first you need to move to the directory where you have created those files. Directory is C8. After moving to the directory, you will create a file with name customization.yaml, and to do that you will write vi followed by space customization.yml. We'll press enter. After pressing enter, you need to use element called as resources, which specifies what resources Kustomize will modify. In our current case, it is v12 deploy.yml file and v12 service.yml. Ensure that both the files are in the same directory. If not, you have to specify full path. After writing resources and specifying resources that you want Kustomize to handle, we'll save and we'll exit. To save and exit, we'll press escape followed by :WQ. So now you have built your customization.yml file which contains details of your resources. Now let's go ahead and execute Kustomize build command. Apart from that, we will also add kubectl apply command, reads the composition created by Kustomize and build the required resources. To do that, we'll go to the command prompt and we'll write Kustomize followed by space build followed by space dot followed by space and pipe symbol in order to add some other command. Command that we will add here is space kubectl followed by space apply followed by space -f followed by space dash. Now this is the command that you'll be using in order to create resources using Kustomize tool. Let's go ahead and press enter. Once we'll press enter, it will read the files which has been created as a composition by Kustomize tool because you have invoked Kustomize build command, and it will display you a message indicating that required resources, which are services and deployment in our case, are created. This is how you will be able to work with composition of deployment and the service resources using Kustomize tool. In this video, we will be listing the imperative commands that can be used to manage Kubernetes objects. Now let's go ahead and first focus on Kubernetes object management techniques. There are 3 techniques that can be used to manage Kubernetes objects. First is imperative commands, which operates on live objects. Recommended environment to use this management technique is development. Supported writers will be 1+ and you will have low learning curve. Second technique is imperative object configuration, where you need to create individual files to operate. Recommended environment for production, and supported writer is only 1 because you'll be writing a file. Third is declarative object, which operates on file directories. Recommended environment is production and supported writers are 1 plus. Now let's go ahead and compare these techniques. So we are going to compare imperative commands, imperative objects and declarative objects. To compare, we need to know features which are listed in the table currently displayed on the screen. Imperative commands are simple, easy to learn and remember. Apart from that, imperative commands requires a single step to make changes to the cluster, whereas imperative objects can be stored in source control systems, facilitates you to reuse it again and have multiple versions. Imperative objects can integrate changes and audit trail review processes. And finally, imperative object provides a template for creating new objects. It simplifies the way administrators can work on objects. And third is declarative objects, which retains the changes. Apart from that, it provides better support for operating on directories. And third, it supports automatic detection of operation types per object. For example, it can detect create, patch, or delete. Now we will try to see some of the examples of imperative commands. First is kubectl space run, which helps you to run a container. Second, kubectl space create, that helps you to create Kubernetes object. Third is kubectl space expose, in order to expose a service. Fourth is kubectl space delete, that deletes an object. And finally, kubectl space edit helps you to edit an existing object. Now let's go ahead and see an example of declarative object, for which you need to create multiple configuration files, place it in config directory, and process all the files. In order to process files, you can use command that starts with kubectl space diff space -f followed by space configs, which is name of the directory. This will give you difference of commands which are there in various files present in configs directory. And then you can use kubectl space apply space -f space configs, where configs is the directory, in order to execute configuration files, create or update existing objects. Second approach of using declarative object is to recursively process directories. Commands are going to be similar, that is kubectl space diff space -r followed by space -f space followed by name of the directory. And you can apply the command using kubectl space apply space -r space -f space configs, where configs is name of the directory. -r tells Kube API server to process all the directories and files present in those directories recursively. So you have to decide what kind of approach you will use in order to manage Kubernetes objects. In this video, we'll install Helm and add the service catalog Helm repository to a local machine that will help to install the service catalog in Kubernetes cluster. Basically, a chart is a Helm package, and it contains all the resource definitions that are required in order to run an application, tool, or services inside a Kubernetes cluster. Let's go ahead and see what all are the steps that we have to take in order to install Helm. First step is to download the key and add. And in order to do that, at the prompt we'll write curl followed by a space, followed by the endpoint where key is present, followed by a space, followed by pipe, followed by a space, and we'll use sudo followed by a space, apt-key followed by space, add, we'll give a space and we'll specify dash. After writing the command, we'll press enter. Once you'll press enter, it will download the key as well as it will add. Once you get message indicating OK, it means that now you have the key. Next step is to install certain dependencies. And to do that, we'll write apt-get followed by space, followed by install, followed by apt-transport-https. We'll give a space and we'll write --yes. After writing the command, we'll press enter. Once you'll press enter, it will check the dependencies and it will ensure that dependencies are installed. If they're already installed, it will not install. If they're older version, it will get upgraded. If it is not installed, it will install the dependencies. We'll clear the screen for now. After clearing the screen, our next objective is to add Helm repository to current Ubuntu repository. In order to do that, we'll write a command that starts with echo, followed by a space. Within double quotes, we'll specify deb, followed by a space, followed by the endpoint, followed by space, followed by all, followed by space, followed by main. We'll ensure that double quotes is closed. Then we'll give a space and we'll add a new command to it by using pipe followed by a space. That command starts with sudo, followed by space, followed by t, followed by space, and followed by the directory where you want to add helm-stable-debian.list. After writing the command, we'll press enter. Once you'll press enter, you'll find that it has added helm-stable-debian.list to your repository folder, which is sources.list.d. Our next task is to update so that it can download all the resources from the added repository. And to do that, we'll write apt-get followed by space followed by update and we'll press enter. Once you'll press enter, it will connect to the repository and it will download all the required packages in order to help you to install Helm. Our final command is to install. To install, we'll write apt-get followed by space followed by install followed by space followed by Helm and we'll press enter. Once you'll press enter, it will start installing Helm. Finally, you will get a message that indicates that it has set up Helm now. We'll clear the screen by writing clear and pressing enter. Now our objective is to add the service catalog Helm repository to the local machine. And that can be done by executing a command that starts with Helm followed by space, followed by repo, followed by space, followed by add. We'll give a space and then we'll write svc-cat. We'll give a space and we'll specify the endpoint of service catalog. Once you will write and press enter, you will find a message that indicates that svc-cat has been added to the repository. This is how you will be able to add the repository. Now let's go ahead and check to make sure that service catalog is installed in your local system. And to do that, we'll use a command that starts with Helm, followed by space, followed by search, followed by space, followed by repo, followed by space, and we'll write service-catalog. After writing the command, we'll press enter. Once you'll press enter, it will show you details which includes name, chart version, app version, as well as a brief description. This is how you will be able to install Helm and add the service catalog Helm repository to a local system to install the service catalog in Kubernetes cluster. In this video, we will list and describe features of prominent tools that are used for templating YAML in Kubernetes. Managing YAML file is essential. You need to follow specification of YAML in order to create your configuration files. There are various tools which can be used in order to help you to build YAML templates, and those tools are called as templating tools. Let's go ahead and list two important templating tools. First is YQ, which takes a YAML file as input. Second is Kustomize. It's a command line tool that can help creating and transforming YAML files. Now let's try to explore YQ capabilities. First capability is it reads values from the files. Apart from that, it also has capability to update existing values. And third, it helps you to convert YAML into JSON. YQ can also be used when you want to add new values, generate new YAML files, or even merge two or more YAML files into a single one. Kustomize comes with various properties. where first property is it's a command line tool which uses a file called customization.yml. Kubernetes provides inbuilt customize tool. Third capability is it helps to create and transform YML file. Finally, you can execute customize commands by passing the directory where you have your customization.yml file located. Now let's try to understand role of Helm, because administrators and Kubernetes professionals will be using Helm and Kustomize together. Why do they do that? And that we will understand using a diagram which is currently displayed on the screen. In order to create YML, you need to segregate responsibilities, where you will be creating Helm manifest chart that will take responsibility of application packaging and application configuration. Application packaging includes configuration of pod, deployment, service, ingress, volume, and various other dependencies. For application config, you will be specifying configuration of environment variables, config maps, secrets, resource definitions, and all these two will be bundled together in form of Helm manifest chart. Then comes what we will specify in Kustomize patch. In Kustomize patch, we'll be specifying all the runtime configurations, which includes CRD configs, that is custom resource definition configurations, operational annotations, pod security contexts, and sealed secrets. These resources will be created and managed with combined power of Helm and Kustomize. So once you understand templating tool, in order to write productive YML files, you can decide which templating tool you will use and also discover when you have to combine Kustomize with Helm for charting. So in this course, we have examined the resource types and resource units that are used in Kubernetes, how to create and scale deployment and stateful sets, create and manage jobs, check downtime resistance, and install Helm and service catalog in Kubernetes clusters. We did so by exploring how to use kubectl command to create and scale deployment, scale stateful sets and make in-place updates on the stateful sets, how to create a daemon set using the rolling update strategy, use the kubectl apply command to create a job and list all the pods that belongs to that job, the imperative commands that we can use to manage Kubernetes objects, how to implement cascading, deletion, and manage orphan dependents, how to install Helm, add the service catalog Helm repository to a local machine to install the service catalog in Kubernetes cluster, and Kustomize tool to illustrate the composition of deployment and service resources. The concept of daemon set, the patterns we can use to communicate with pods in a daemon set, along with the features of prominent tools that we can use to template YML in Kubernetes. In the next course, we will learn how to perform critical pod and deployment management tasks, which includes removing a pod, increasing the number of pods, scheduling pods manually and with the use of label selector, configuring environment variable with a pod, mounting a secret to a pod, creating a deployment definition file to deploy 4 pods, and scaling the replicas. In this video, we'll create a replica set definition file and use kubectl command to create a replica set and then verify that a particular pod is managed by current replica set and not by another. In order to create a definition file of replica set, we'll be using a command vi followed by space, followed by name of the file that we want to create where we want to define our replica set. We'll press enter. First 2 lines of the current YML file will specify API version, which is apps/v1, followed by kind, which specifies replica set, followed by metadata where we are giving a name to it. Name is nginx-proxy sample, followed by labels. We are specifying 2 labels. First label is app, which we are specifying as nginx-proxy sample. Second label is tier, which is specified as front-end app. After specifying metadata, we need to create another block for spec where we need to specify number of replicas. We have specified number of replicas to 5 by using attribute of spec called replicas. Then we are giving selector followed by match labels where we are specifying match labels to be tier, and tier's value is front-end app. After specifying replicas and selector, in the current spec, we are also specifying template which contains metadata followed by labels, and we are specifying one label that is tier front-end app. Then comes specific spec for container. We are specifying containers. We are giving name to the container which is nginx followed by image. We have specified nginx. After making the changes, we'll press escape followed by :wq, which will save and exit from the current editor. Once we are out of editor, we'll come back to the prompt where we'll specify command that starts with kubectl followed by space apply followed by space -f followed by space name of the file which we created in the previous step. After writing name of the file, we'll press enter. Once we'll press enter, we'll find that it creates a replica set and gives it a name. Now let's go ahead and get the current replica set which is deployed. To do that, we'll write a command at the prompt that starts with kubectl followed by space get followed by space rs. After writing the command, we'll press enter. Once you'll press enter, it will display list of current replica sets which are currently present in the cluster. We need to find out recently created replica set, and that was nginx-proxy sample. So this command confirms that our replica set is created, desired was 5, current is 5, and all 5 are ready. Now let's go ahead and verify that a particular pod is actually being managed by the replica set and not by another controller. To do that, we'll select one of the pods, and to get all the pods, we'll write kubectl followed by space get followed by space pods, and we'll press enter. Once you'll press enter, you'll get all the pods which are currently deployed in your cluster. We have pods which starts with nginx-proxy sample-alphanumeric. We'll select one of them. After selecting one of them, we'll clear the screen. After clearing the screen, now our task is to verify that the current pod that we have selected from the list is being managed by this replica set and not by another controller. To do that, we will write command that starts with kubectl followed by space get followed by space pods followed by space followed by name of the pod which we want to verify followed by space -o followed by space YAML in order to ensure that we are getting output in form of YAML. Then we'll use space pipe symbol followed by space grep followed by space -a, which is a flag that takes a number and prints the number of lines after the match. After -a, we'll give a space and we'll specify 5 in order to ensure that it takes 5 lines after the match. We'll give a space and we'll write owner. After writing owner, we'll press enter. Once you'll press enter, you'll find that it displays owner's reference. And under owner references section, which is being displayed in the second section of output, we can go ahead and look for name, which specifies nginx-proxy sample. It confirms that the current pod is being managed by your replica set that you created and not by another controller. This is how you can create a replica set definition file and use kubectl command to create a replica set, and finally verify that a particular pod that you selected is being managed by this replica set and not by another controller. In this video, we'll remove a pod that is managed by a replica set by simply changing its label. Let's go ahead and first get all the pods. To get all the pods, at the prompt, we'll write kubectl space followed by get space followed by pods. We'll press enter. Once you'll press enter, you'll get list of all the pods. Now let's select pod that we want to remove from the replica set. Assume that we are selecting one of the pods, that is nginx-env-8qmp6. After selecting the pod that we want to remove by changing the label, we'll go ahead and we'll edit. To edit, we'll write command at the command prompt that start with kubectl space edit space pods space name of the pod. After specifying name of the pod, we'll press enter. Once you will press enter, you'll find that it opens YML file that keeps specification of the pod, which was created at runtime when we created our replica set. Now, once YML file opens, you can locate labels. Under labels, you will have role or whatever name you have given to your label while creating your replica sets in replica set configuration file. You need to edit it. For now, we'll change the role to isolated. Now, after changing the role to isolated or anything different, we'll save the file and we'll exit after making the change. To save and exit, we'll press escape followed by :WQ and we'll press enter. Once you'll press enter, it will show you a message that indicates that your current file which was generated to represent a pod has been edited. We'll clear the screen. After clearing the screen, we'll run kubectl get pods command. To do that, at prompt, we'll write kubectl followed by space followed by get followed by space pods and we'll press enter. Once you'll press enter, you will notice that now you have 5 pods for the replica set instead of 4. That was the number which was defined while creating. That's because the replica set dutifully creates a new pod to reach the desired number of 4 pods which is specified in your replica set configuration. Now the isolated one is still running, but it is no longer managed by the replica set. This is how you can remove a pod from replica set by changing its label. In this video, we'll use kubectl command that uses horizontal pod autoscaler with the replica set to increase the number of pods when the CPU load gets higher without exceeding 5 pods. Now let's go ahead and first get the deployments. To get the deployment, we'll connect to the cluster and at the command prompt, we'll write kubectl followed by space followed by get followed by space followed by deployments and we'll press enter. Once you'll press enter, you'll get all the deployments which are currently done. You have nginx-deployment, php-apache, tomcat-deployment, web-deployment. So these are the existing deployments that you have for which number of pods might have got created. Now our objective is to create horizontal pod autoscaler where we want to increase the number of pods when the CPU load gets higher, but we need to ensure that it should not exceed 5 pods. To do that, we'll be using kubectl command to create a horizontal pod autoscaler where we'll specify the range between 1 and 5 replicas of the pod, and increase and decrease of replicas will depend on CPU utilization. Now let's go ahead and fix it to 60%. It means when usage across all pods is 60%, it should increase. And accordingly, it should decrease. We'll select one of the deployments. Let's select nginx deployment where we have 3 out of 3. We want to scale it. To scale it using horizontal pod autoscaler, we'll write a command that starts with kubectl followed by space autoscale followed by space deployment followed by space nginx-deployment. After specifying deployment for which we are creating horizontal pod autoscaler, we'll give a space and we'll specify the CPU %. To specify CPU %, we'll write --CPU- % equal to 60. We'll give a space. After specifying --CPU- % equal to 60, we'll go ahead and we'll specify --min, which would be equal to 3 because we want 3 to be minimum, followed by space, followed by --max, which we want to limit to 5. After writing this statement, we'll press enter. Once you'll press enter, you'll find that it has created horizontal pod autoscaler for autoscaling nginx-deployment depending on metrics that you have specified. Now let's go ahead and check the current status of autoscaler. To do that, we'll write kubectl followed by space get followed by space HPA, and will press enter. Once you'll press enter, it will show you nginx-deployment and targets 60%. Apart from that, it shows min pods to be 3, max pods to be 5. This is how you will be able to use kubectl command that uses horizontal pod autoscaler with the replica set to increase the number of pods when the CPU load gets higher without exceeding 5 nodes. In this video, we'll demonstrate how an administrator can create a deployment definition file and use kubectl command to deploy 4 pods with nginx as the hosted application, and finally use kubectl scale command to scale replicas. To do that, we'll be writing a file. To create the file, we can use vi editor. To use vi editor, at the prompt we'll write vi followed by space followed by name of the file. After giving a name to the file, ensuring that extension is .yml, we'll press enter. After pressing enter, we'll make certain entries in the file that helps us to create object of type deployment and specify to deploy 4 pods with nginx as the hosted application. To do that, in the first 2 lines, we'll specify API version, which for deployment would be apps/v1. Kind tells the object type. An object type that we want to create is deployment. After specifying kind, we'll specify metadata, where we'll give name to our deployment, and name that we are giving is nginx app deployment. We'll use certain labels in order to work on them later, specifically with selectors. Labels we are specifying is only one. Name of the label is app and value is front end, followed by the spec, where we are giving replicas to 4. That is what was needed as per the requirement. We are specifying selector. We are specifying replicas as 4. And then we are going and we are specifying selector. Below selector, we have given match labels. We are using the same label that we have defined in metadata of deployment, that is app, followed by front end value. Next is template, where we are specifying metadata, labels, app : front end, and then comes the most important part, where we have to specify application that we want to host is nginx. To do that, we have written spec, followed by containers, followed by name, which is nginx, image, a specific version of nginx, followed by ports in order to bind the container port, and that we are doing by specifying container port to be 90. After writing the definition file, where we have specified object type to be deployment, application that we want to host is nginx, and number of pods that we want is 4. After creating the file, keeping in mind all these basic requirements, we'll press escape, followed by :wq, and we'll press enter. Once you'll press enter, you'll come out of the editor. Now we need to use kubectl command to actually create deployment object. To do that, we'll write kubectl, followed by space apply, followed by space -f, followed by space name of the file. After writing the command, we'll press enter. Now once object is created, we would like to see the current status. To do that, we'll write kubectl, followed by space, followed by get, followed by space, followed by rs, and we'll press enter. Once we get the replica set of nginx app deployment, we can see desired is 4, current is 4, and ready is 4. Now our next objective is to scale. To scale, we'll be using a command called kubectl, followed by space scale, followed by space deployment, .v1, .apps, / name of the deployment, which is nginx app deployment. After specifying the object which we want to scale, we'll give a space and we'll specify the new replica by using -- replicas equal to 6. We'll press enter. Once you'll press enter, you'll find that nginx app deployment has been scaled. Now let's go ahead and see desired, current, and ready for nginx app deployment after scaling. To do that, we'll re-execute the command, that is kubectl space get space rs, and we'll press enter. After pressing enter, you'll find the list. From the list, you need to locate nginx app deployment and see the desired, which has scaled up to 6. This is how you can create a deployment definition file and use kubectl command to deploy 4 pods with nginx as the hosted application, and finally use kubectl scale command to scale replicas. In this video, we'll recall the concept of Kubernetes scheduling and the role played by Kubernetes scheduler in container orchestration. Let's try to understand Kubernetes orchestration and scheduling using a diagram which is currently displayed on the screen. User will make a request. They'll make a request for deployment, and deployment internally will create replica sets which will have pods. Now pods need to be scheduled. They need to be scheduled in order to ensure that they are running on appropriate nodes. Here comes role of the master API, which is an instrument that provides read-write access to the cluster's desired and current state. As the diagram indicates at the bottom, we'll have two essential elements. First is the controller and second is scheduler. Scheduler can use the master API to retrieve the current state information, apply certain logics and calculations, and then update the API with the new information about the desired state. For example, it can specify that to which node a new pod need to be scheduled or which pod should be moved to another node. Controller takes responsibility of providing appropriate control over pods that are allocated specific nodes where they need to run by scheduler. Other important concept that we need to understand from perspective of Kubernetes orchestration and scheduling is you will have consumer API which are node agents. As we can see in the diagram on the right, we have node 1 that contains kubelet. And responsibility of kubelet is to manage the container runtime. In our current case, container runtime that we are using is Docker, which is present on worker node. Whenever a kubelet will recognize discrepancies between the reported desired state and the actual state of its host, it will run or terminate the needed containers to reach the target state, which is described by the master API. Now let's try to understand various stages of scheduler that is used for decision making. There are 3 stages. First is node filtering, where scheduler need to check which nodes are compatible to run the workload. It does that by running all nodes through a set of filters and removing those which are not compatible from considerations perspective. Second stage is node priority calculation. If the filtering stage suggests certain nodes to choose from, the scheduler will run a prioritization check. And finally, it moves to actual scheduling operation stage, where after the check is completed, the scheduler calculates the score for each node and the highest scoring node will run the pod. Now let's go through algorithms in detail. And first is volume filter. When we talk about volume filter, it passes through various checks. And first check is, do the zone of pod requested volume fits the node's zone? Second element is, can the node attach to the existing volumes? Third, are there mounted volume conflicts? And finally, are there additional volume topology constraints? Now we can see in the diagram that volume filter starts working. After it has completed its task, it moves to resource filters, then it moves to topology filters. Topology filters provide certain pods, then prioritization check is executed in order to select the right node where pod can run. So by using these checks, which is volume filter, scheduler will know in advance which nodes can't run the pod, so it will remove those nodes from the list of possible targets. After volume filter has executed, it moves to second stage, which is resource filters. As the diagram indicates, we are assuming that volume filters have completed its task and it has given suggested list of nodes where pods can run. Then comes role of resource filter, which will do following checks. First check will be, do pod request resources like RAM, CPU, GPU fits the node's available resources? Second, can pod requested port be opened on that particular node or it is already occupied by some other pod? Third, is there no memory or disk pressure on the node? Now these filters are straightforward. Scheduler will check if the resource requested by pods are available or not. And they will ensure that there is no pressure on the node like low memory or low disk space, and then confirm whether requested ports can be opened on the node or not. Third is topology filter. As the diagram indicates, we have completed volume filtering, resource filtering. Now we are on topology filter, where we need to check, is the pod requested to run on this node? Are there inter-pod affinity constraints? And finally, can the pod tolerate the node taints? Now, in this particular stage, the scheduler verifies if the pod explicitly stated its need to run on a particular node or if it specifies pod affinity. And then comes the final step, that is scheduling pod destination, where it need to first specify resource requirements, use node constraints, facilitate scheduler's configuration, be aware of the volumes, use affinity and anti-affinity if it is configured, utilize custom or multiple schedulers. All these elements must be checked before pod's destination is decided. This is how Kubernetes schedules pod to run on a particular node. In this video, we'll create a Kubernetes user account using the X509 client certificate. Let's go ahead and create a user on the master machine. For that, we will connect to the master and then go into the home directory in order to perform the remaining steps. Let's create the user by writing user add followed by space name of the user, that is user1, and press enter. Once we'll press enter, if user is already present, it will show that user is already existing, else it will create a user. Now let's go ahead and create a user1 directory. To do that, we'll write mkdir followed by space followed by /home followed by user1, and we'll press enter. Now we have created user1 directory. Let's move to that directory. To move to the directory, we'll write cd followed by space followed by /home followed by /user1/. Now our current working directory is user1. We'll clear the screen. After clearing the screen, we'll create a private key. To create a private key, we'll be using OpenSSL, and we'll write command that starts with OpenSSL followed by space gen RSA followed by space -out followed by space user1.key followed by space 2048. We'll press enter. Once you'll press enter, you'll find that it generates RSA private key. Now we need to create a certificate. In order to create a certificate, we'll use command OpenSSL followed by space req followed by space -new followed by space -key followed by space user1.pem followed by space -out followed by space user1-csr.pem followed by space -subject, that is specified using subj, followed by space, and within double quotes we'll specify /cn equal to user1. We'll close the double quotes and we'll press enter. Now, in case if you get an error, it might be because you are using the wrong name for the keys. After changing it, either it will be .pem or it will be .key. We'll press enter. Once you'll press enter, it will create a CSR certificate, but yes, without any group. Now we need to sign the CSR with Kubernetes CA. To do that, we'll first clear the screen. After clearing the screen, we'll write a command. We'll specify command that starts with OpenSSL followed by space X509 followed by space -req followed by space in followed by space user1.key followed by space -ca followed by space /etc/kubernetes/pki/ca.crt, which is location of the certificate authority, followed by space followed by -ca key followed by space /etc/kubernetes/pki/ca.key followed by space, and will specify -ca create serial followed by space -out followed by space user1.crt followed by space -days followed by space 500 in order to ensure that certificate is valid for 500 days. After you'll press enter, you'll find that your key is created. Using the key, you can create a user account using Kubernetes commands. This is how you will be able to create Kubernetes user account using the X509 client certificate. In this video, we'll demonstrate how to use label selectors to schedule pods and use anti-affinity to launch a pod on a different node. Let's try to understand what is affinity. When we talk about pods, interpod affinity will be specified using fields like pod affinity or field affinity in the pod spec. An interpod anti-affinity is specified as the field called pod anti-affinity or field affinity in the pod spec. Now we need to understand that pod anti-affinity requires nodes to be labeled. In other words, every node in the cluster must have an appropriate label matching topology key. Now let's go ahead and create a YML file where we will be creating web server deployment which has pod anti-affinity. When you configure anti-affinity, it informs the scheduler that all its replicas are to be co-located with pods that have selector where you are using a specified label. This will also ensure that each web server replica does not co-locate on a single node. To do that, we'll be creating a file by writing sudo space vi space c9 underscore v8 underscore 2.yml and we'll press enter. Once you'll press enter, it will launch the file where you need to specify first two lines as API version, which will be app/v1. Kind will be deployment. Metadata, you can specify a name. We are taking a popular name called redis-cache. Then we have to specify spec, where we are specifying selector, match labels, and we are taking the label which will be used by pod anti-affinity. Label that we are defining here is app:store. Replicas that we want to create is 3. And then we are using template, metadata, labels. Again, we are specifying app:store. Then comes the most important part where we will be specifying the affinity. To specify affinity, we'll be using spec:, and in the new line, we'll be writing affinity:, following YML syntax rules. And since we want anti-affinity, we'll specify pod anti-affinity:, followed by required during scheduling, ignored during execution. And we are binding it with a label selector rule. That label selector specifies a rule which uses match expressions where key is app, operator is in, and values is store. So it will match the label which contains value called store. Now from where it will match? It will match from topology key : kubernetes.io/hostname. And finally, we need to specify the containers that we want to create, where we have specified name and image. This is how you will be able to apply anti-affinity. Let's go and save it. To save, we'll press escape, WQ. After saving, we'll be using kubectl apply command in order to create the pods. To do that, we'll write kubectl, followed by space, followed by apply, followed by space -f, followed by space name of the file. After specifying name of the file, we'll press enter. Once you'll press enter, you'll find that deployment.apps/redis-cache is created. Now let's go ahead and see the pods. To see the pods, we'll be writing kubectl, followed by space get, followed by space pod, followed by space redis-cache. We'll press enter. After applying, we'll clear the screen and we'll write kubectl, followed by space, followed by get, followed by space rs, and we'll press enter. Once you'll press enter, you'll find that you have redis-cache-alphanumeric number. That indicates the replica set which is created for your current deployment. Now let's go ahead and see what all pods are there which are allocated to the current replica set. Now to get pods, we will write kubectl, followed by space, followed by get, space, followed by pods, and we'll press enter. Once you'll press enter, you'll find that redis-cache has created the desired number of replicas and they are starting. You have to wait for state to change to running. Next, we will write a command called kubectl, followed by space get, followed by space pods, followed by space -o, followed by space wide, and we'll press enter. Now, once we'll press enter, it will show IP addresses as well. Now, let's go ahead and check our pod. You'll find that every pod is running on a different host. Third is in pending state. It will be allocated a different host once it moves to running state. This is how you can use label selectors to schedule pods and use anti-affinity to launch a pod on a different node. In this video, we'll use the kubectl taint command to taint a node with type equal to special, no schedule, make the node unschedulable, and create a pod to tolerate the taint. Taints will allow a node to repel a set of pods. We need to understand that tolerations are applied to pods and they allow the pods to schedule on to nodes with matching taints. Taints and tolerations are complementary because they work together to ensure that pods are not scheduled onto inappropriate nodes. Now let's go ahead and use kubectl command to taint a node. But before we do that, we'll get all the nodes of current Kubernetes cluster. To do that, we'll write kubectl followed by space get followed by space nodes and we'll press enter. Once you'll press enter, it will show you a list of nodes. You need to focus on name and capture the name of the node where you want to place a taint. And to do that, we'll be using a command called kubectl followed by space taint followed by space nodes followed by space the name of the node. Let's select one of the node. We'll select IP -172 -31 7 102. This is the node on which we want to place the taint. To taint, we'll specify a key value. So we are specifying here K1 equal to V1 followed by colon and no schedule. So in the current case, we are planning to place a taint which has a key called K1, value V1, and taint effects no schedule. This means that no pod will be able to schedule onto the node which we have specified until it has a matching toleration. Let's press enter. Once you'll press enter, you'll get a message indicating that the current node that you have specified is tainted. Now let's go ahead and how do we configure pod to use the taint key that we have specified. And to do that, we'll be creating a manifest file. Let's go ahead and use vi followed by space followed by name of the file. We have c9_v9.yml file. We'll write the file and we'll press enter. After pressing enter, you will enter certain configurations where first two lines specifies API version, which is v1, kind, pod. Then you are giving name and label to your pod by using metadata. Below metadata, you are specifying name to be Tomcat server pod. Labels you are specifying as env::test. Then comes spec, where you are defining the containers by populating its attributes called name to Tomcat, image to Tomcat, image pull policy if not present. If it is present, it can reuse it. That's what is meaning of image pull policy. And finally, we'll come to toleration, where a toleration should match a taint if the keys are same and the effects are the same. In the current case, we are using key K1, and this is the key that we have specified while placing the taint on the node. Operator is exists, in which case we don't need to specify value. But if you are specifying operator's value to be equal, you have to go ahead and give the value. And finally, effect is no schedule, which matches to K1 that we have specified while placing the taint on the node. Now, if you are not giving any effect, then it will match all the effects with the key that you have specified below toleration, which is K1 in current case. Let's go ahead and save the file by pressing escape WQ followed by enter. Now you are out of your editor. You can go ahead and try creating the node using the configuration file that you have written in the previous step. To do that, we'll write kubectl followed by space apply followed by space -f followed by space name of the file. After you have specified name of the file, we'll press enter. Now, once you'll press enter, you'll find that Tomcat server pod is created. Now let's go ahead and remove the taint from the current node so that it will not impact rest of the demonstrations. To do that, we'll be using kubectl followed by space taint followed by space nodes followed by the node name followed by space k1 equal to v1 colon no schedule followed by dash. We'll press enter. Once you'll press enter, whatever taint was applied on the node will be untainted. This is how you can use kubectl taint command to taint a node with type equal to special colon no schedule and make the node unschedulable and create a pod to tolerate the taint by configuring toleration in the configuration file. In this video, we'll create a manifest file that creates a pod with a sample container that requests 2 GB of memory with half a CPU and has a limit of 3 GB of memory with the whole CPU. To do that, let's go ahead and create a file. To create a file, we'll connect to Kubernetes cluster. Once we are connected at the terminal, we'll write vi space name of the file. We'll press enter. After pressing enter, we'll specify configuration in YAML format. First 2 lines will be API version and kind. Ensure that your kind is pod. Then you are giving a name to your pod by using metadata, and below metadata you are specifying name colon user interface layer. And then comes the spec where you are specifying containers. Below containers you are configuring 3 essential attributes. First is name, that is app. Second is image, that is ng-annex. And then comes the resources where you are going to apply the limits. We are using requests where we are giving memory colon 2 GB. Then comes CPU where we are specifying 500 M. In order to understand what is meaning of 500 M, we need to know that 0.1 is equivalent to 100 M, which indicates half, which is 0.5, will have 500 M, where M can be read as milli CPU. So we are allocating 500 milli CPU, which is equal to 0.5 CPU. Then comes the final limits, where we are specifying limits. Below limits, we are taking memory to be 3 GB and CPU to be 1000 milli CPUs, which is equal to 1 CPU. After creating the configuration file, we'll save. To save, we'll press escape followed by WQ and we'll press enter. After we press enter, we need to go and create. To do that, we'll write kubectl followed by space apply followed by space -f followed by space name of the file, which is c9 underscore c10.yml. We'll press enter. Once you'll press enter, you'll find that your pod is created. This is how you can create a manifest file and use kubectl command to create a pod with a sample container that requests 2 GB of memory with half a CPU and has limit at 3 GB of memory with a whole CPU. In this video, we'll demonstrate how to manually schedule a pod and force a pod to be on a specific node without using the scheduler. Now first, let's go ahead and see what all nodes are currently present in the cluster. To do that, we'll write kubectl at the prompt, followed by space, followed by get, followed by space, followed by nodes, and we'll press enter. You'll find that you have 3 nodes, out of which 1 is master and 2 are worker. Now we'll be creating a manifest file where we will create pod. To do that, we'll be creating a file using vi command. We have written vi space c9 underscore v11.yml at the prompt. We'll press enter. Once you'll press enter, you need to write certain configurations carefully. First 2 are API version, which is v1, followed by kind, pod. Then you have metadata where you are specifying name and labels. Name that we are giving to our pod is sample app pod. Labels that we are specifying is only one, that is app colon sample app. Then we are giving specification of containers. It can be any container where you have your application. We are giving containers name as sample container and image to be Tomcat. Once you create the file, we'll save and we'll exit. Now when you go and when you apply in order to create pods, your scheduler will take responsibility of allocating nodes automatically. Let's go ahead and check it out. To do that, we'll write first kubectl, followed by space, followed by apply, followed by space dash f, followed by space name of the file. Name of the file is c9_v11.yml, which we created in the previous step. We'll press enter. Once you'll press enter, you'll find that your pod is created. Now let's go ahead and see on what node it is scheduled. To do that, we'll write kubectl, followed by space get, followed by space pods, followed by space dash o, followed by space wide. We'll press enter. Once we'll press enter, it will list all the pods which are currently running in the system. We need to locate our pod which we created recently, and we'll find that sample app pod is assigned one of the nodes. Now let's go ahead and clear the screen by writing clear at the prompt and open the file so that we can specify how to manually schedule, so that automated scheduler will not take care of scheduling pod to a particular node. To do that, we'll first get the nodes by writing kubectl, followed by space get space nodes, and then decide on which node you want to schedule. For example, assume that we want to schedule on IP-172-31-3-83. We'll copy. After copying, we'll edit the file. Once you are there in the file, you will go to spec section of your current YML file. Press enter to create space where you will be specifying one extra attribute called as node name. You'll specify node name, and following YML semantics, you will specify the node where you want the current pod to be scheduled. Let's go ahead and save the file and exit. To do that, we'll press escape followed by :WQ. So now we have tuned the file. Before we go ahead and apply in order to create pod once again, let's go ahead and delete the pod. To delete the pod, first we need to capture the name of the pod. To get the name of the pod, we'll write kubectl, followed by space, followed by get, followed by space pods, and we'll press enter. Once you'll press enter, it will list all the pods once again. You need to select the pod which you created earlier. After copying the pod, we'll clear the screen. After clearing the screen, now we have to delete the pod. To delete the pod, we'll be using command called kubectl, followed by space, followed by delete, followed by space pod, followed by space name of the pod that you want to delete. We have specified sample app pod. After giving the name, we'll press enter. You'll find that it has deleted the pod. Now, once pod is deleted, you can go ahead and create the pod again, which will not use scheduler. Rather, it will create that particular pod using manual node entry that you have made in your configuration file. Let's go ahead and write the command, that is kubectl, followed by space, followed by apply, followed by space dash f, followed by space name of the file, which is c9v11.yml. We'll press enter. Once you'll press enter, you'll find that pod is created. Now let's go ahead and see where that pod is created. To do that, we'll write kubectl, followed by space get, followed by space pods, followed by space dash o, followed by space wide, and we'll press enter. Once you'll press enter, it will show you the list. You need to locate your pod that you recently created, and you'll find that your sample app pod is created on the IP that you have specified in your configuration file. This is how you can manually schedule a pod and force a pod to be on a specific node without using the scheduler. In this video, we'll configure manifest file and use kubectl command to create a pod with one of the available latest images running asleep for 1 hour. Then give it an environmental variable named test with the value sample and execute a command in the container to show that it has configured environmental variable. Let's go ahead and configure a manifest file. To do that, we will write vi, followed by name of the file, which is c9_v12.yml. We'll press enter. After pressing enter, you need to make some entries in order to create a pod with the desired outcome. Line number 1 and line number 2 is all about what is the API version, what is the kind. API version is v1 and kind is pod. Then we are specifying a metadata where we are giving name to the current pod, which is Ubuntu. We are giving a label by specifying labels and giving Ubuntu value to the label key called app. Then comes the spec where we are defining specification for containers. We have specified containers : and we have used Ubuntu as the value of image property of containers. Then we are defining our environmental variable, which is done by giving a name, which is test, value, sample. And finally, we are using command called sleep, which will ensure that your container sleeps for 3600 seconds, which is 1 hour. And finally, we are specifying image pull policy, that is if not present, and we are giving name of the image, which is Ubuntu. Restart policy, we are setting it to always in order to ensure that pods are automatically started. Let's go ahead and save the file and exit from it. To do that, we'll press escape followed by WQ. Now, once we are out, we need to create the pod, and that we will do using kubectl followed by space apply followed by space -f followed by space name of the file, which is c9_v12.yml. We'll press enter. You'll find that it displays pod/Ubuntu created, which indicates that pod with the name Ubuntu is created. Now let's go ahead and connect to the container. To connect to the container, we'll be writing a command which starts with kubectl followed by space exec followed by space -it followed by space Ubuntu, which is name, followed by space -- followed by space /bin/bash. We'll press enter. Once we'll press enter, we will be connected to the container which is running in the pod that we created in previous steps. Now let's go ahead and write echo followed by space $test, and you'll find that it displays the value called sample which you have configured in your manifest file. This is how you will be able to configure manifest file and use kubectl command to create a pod with one of the available latest image, running a sleep for 1 hour with an environmental variable named test with value sample, and then we have executed a command in the container to show that it has configured environment variable. In this video, we'll create a secret from files containing a username with a password. Use the secret to define environmental variables and mount the secret to a pod to admin cred folder. Let's go ahead and first create a file that contains username with a password. To do that, we'll go to the terminal, we'll write vi followed by a file which contains the entries. We have named the file as appuser.properties. We'll press enter. You'll find that we have stored username and password. We'll save and we'll exit after creating the file. And to do that, we'll press escape followed by :WQ and enter key. Now our next objective is to create a secret using appuser.properties file. To do that, we'll write a command that starts with kubectl space create space secret space generic space appuser_secret, which is the name of the secret, followed by space -- from -file equal to path of the file where we have appuser.properties. After writing the command, we'll press enter. Once you'll press enter, you'll find that it creates the secret. Now our objective is to use the secret which we have created to define environmental variables and mount the secret to a pod to admin cred folder. To do that, we'll create a file by writing vi followed by space followed by c9_c13.yml, and we'll press enter. Once you'll press enter, it will open a file where you need to go and write configuration. Line number 1 and line number 2 is all about what is the API version, what is the kind. API version is v1 and kind is pod. Followed by name of the pod that we have specified in name element of current YML file, which is present inside metadata. Name is secret test pod. Followed by spec, followed by containers below spec, and we are specifying name of the container to be secret pod. We are specifying image to be reddish, and then we are using secret to bind it with an environmental variable. To do that, we are writing env : followed by name : app_username, which is name of the environmental variable. Now we are pulling value from the secret that we created. To do that, we are writing value from colon, followed by secret key ref colon, followed by name and key, where name we are specifying as app user secret, which is name of our secret that we created in previous step, followed by key, which is username that is present in secret. Then comes mounting. We are using volume mounts, specifying name of volume mounts to be TMP, followed by mount path, which is /admin cred/, followed by read-only property. We are setting it to true. And then we are defining the volume that we are using in volume mounts. To define volume, we are writing name colon TMP, secret colon secret name, that is app user secret. This is how you will be able to define an environmental variable and mount the secret to a pod to admin cred folder. Let's go ahead and save the file and exit. To do that, we'll press escape followed by colon WQ and we'll press enter key. Now we have to create a pod where we have defined environmental variables and we have mounted the secret to the pod's admin cred folder. To do that, we'll write kubectl followed by space apply followed by space -f followed by name of the file, which is c9_c13.yml. We'll press enter. Once we'll press enter, we'll find that the pod is created. And while creating the pod, it has defined environmental variable and it has mounted the secret to pod's admin cred folder as specified in configuration file. So in this course, we have examined how to perform critical pod and deployment management tasks, which includes removing a pod, increasing the number of pods, scheduling pods manually and with the use of label selector, configuring environment variables with a pod, mounting a secret to a pod, creating a deployment definition file to deploy 4 pods and scaling the replicas. We did so by exploring how to create a replica set definition file and use kubectl command to create a replica set, create a deployment definition file and use kubectl command to deploy 4 pods with nginx as the hosted application, and how to create a Kubernetes user account using the X509 client certificate. Use kubectl command with horizontal pod autoscaler and replica set to increase the number of pods when the CPU load gets higher. The role played by Kubernetes scheduler in container orchestration and how to manually schedule a pod and force a pod to be on a specific node without using the scheduler. How to configure manifest file and use kubectl commands to create a pod and give it an environmental variable named test with a value sample. How to create a secret from files containing a username and password and mount the secret to a pod to admin cred folder. In the next course, we will explore the networking model and the different types of services that can be implemented in Kubernetes, learn how to create namespaces, implement pod network, map services to pod network addresses, and create and configure node port and load balancer. In this video, we'll describe the Kubernetes network model and identify the networking problems that can be addressed using Kubernetes cluster networking. Now let's go ahead and first identify critical challenges faced by Kubernetes from perspective of networking. First is we need to plan container-to-container networking in order to ensure that 2 containers are able to communicate with each other. We need to also focus on how pod will communicate with services. And that leads to a challenge which you need to take care, that is pod to service networking. Third networking challenge that you need to take care is pod to pod networking. And finally, how your services will be made available to end users using internet. And that leads to configuration challenge of internet to service networking. Then comes how do we plan Kubernetes network. So there are certain decisions that we need to take when we are planning Kubernetes networking. And first decision that you have to take is how pods are placed physically on different nodes. Second, how Kubernetes service works. Third, have you implemented load balancing? If yes, how load balancing is implemented. Fourth, how network policies are implemented in your current Kubernetes network. And finally, how much overhead Kubernetes overlay networking will add. after taking these critical decisions, you'll be able to derive a network model. The main idea behind the design of Kubernetes network model is that you should be able to directly move your workload from VMs to Kubernetes containers without any change in your application. This particular need imposes three fundamental requirements to come up with right network model. And first is all containers must have capability to communicate with each other directly without using NAT, that is network address translation. Second requirement of Kubernetes network model is all the nodes can communicate with all containers without using NAT, and vice versa, that is all containers must be able to communicate with all nodes. And third is the IP of a container that it sees for itself is the same IP that others sees it as. Now let's go ahead and take up a scenario how to implement network model. And that we will do using a diagram which is currently displayed on the screen. We can see two nodes and we have a routes table. First node is allocated an IP address and second node is also allocated an IP address. And if you see, they are from the same range. Now the idea is to allocate a subnet for each container host and then set up some kind of routing between the host to forward containers traffic appropriately. And that's where role of route table comes into play, where IP addresses are mapped to a particular route. So whenever there will be communication need, depending on container's IP address, it will use route table in order to create communication with other container. So this is how you will be able to derive right Kubernetes network model to take care of all the communication challenges that exist in Kubernetes, which includes container to container, pod to pod, pod to service, as well as internet to service. In this video, we'll list the prominent technologies that can be used to implement Kubernetes networking model. There are multiple different technologies which are used in order to implement Kubernetes networking. Let's go ahead and list some of them. First is ACI. Second is AOS for Abstra, which is a turnkey automation solution that simplifies the process, design, deployment, and operation of data center networks. Third is Entria, which is Kubernetes native project that has capability to implement CNI, that is Container Network Interface. Fourth is AWS VPC CNI for Kubernetes. It's a plugin that allows Kubernetes pods to receive native AWS VPC IP addresses. Followed by certain others where we have Azure CNI for Kubernetes, which allows container to be part of Azure Virtual Network. Then we have Calico, which is a container networking solution that makes use of layer 3 to route packets to pods. And finally, Cilium implements basic Kubernetes network policy, but it has also capability to use identity-aware and API-aware visibility to enable both DNS-aware policies. Now let's go ahead and list features of these Kubernetes technologies. We'll start with ACI, which offers an integrated overlay. Apart from that, it also supports underlying SDN solution that has capability to manage and support containers. And third feature is it provides container networking integration for ACI. Then comes Entria, which is an open source Kubernetes networking solution. It is considered as Kubernetes native. Third feature is it leverages Open vSwitch as the networking data plane. Then comes AOS for Abstra, which is intent-based networking system, has capability to manage complex data center environments, and it supports layer 3 connected hosts. Apart from that, it also provides rich set of REST API endpoints which can be used by Kubernetes. Fourth is AWS VPC CNI. It is integrated AWS Virtual Private Cloud Networking mechanism, offers high throughput and availability as committed by AWS. It also allows Kubernetes pods to have same IP address inside the pod as they do on the VPC network in AWS. Apart from that, we will also list feature comparison of Azure CNI for Kubernetes, Calico, and Cilium. Azure CNI for Kubernetes has capability to integrate Kubernetes pods with Azure Virtual Network. In case of Azure CNI for Kubernetes, pods can connect to peered VNet and to on-premises over Express Route or site-to-site VPN. And third critical feature is it assigns VNet IPs to pods with a pool of secondary IPs which are pre-configured on network interface. Then comes Calico, which is an open source networking and network security solution used for containers. It supports multiple different types of data planes, provides a full networking stack, and have capability to be used in conjunction with cloud provider CNIs. And finally, Cilium. It's an open source software, provides transparent secure network connectivity between application containers which are present on Kubernetes. It is L7/HTTP aware and it has capability to enforce network policies on L3 and L7 layers. In this video, we'll describe the concept of container-to-container networking and how Kubernetes enables pod-to-pod communication using real IPs. Let's focus on container-to-container communication, which means that in real scenarios, within each pod, the requirement may be to run multiple containers, and those containers must communicate with each other. In order to enable that communication among containers, K8 container-to-container communication, where K8s stand for Kubernetes, uses shared file system or local host network interface. Now let's try to understand container-to-container communication strategies. Now there are two different strategies that we have discussed in the previous slide. First, shared volume. Second, local host interface. When we talk about shared volume, as the diagram indicates on the left, you will have shared data volume with a particular name. Now that particular volume will be used by container which is present on pod. So you have two container pod where first container is nginx-container and second container is Debian-container. In order to create container-to-container communication, we are using a shared volume which is represented in both the containers of your pod. Then comes how do local host interface works. You'll have two container pod and both containers will be able to communicate with each other using local host endpoint. As the diagram on the right indicates, you have nginx-container which listens on port 80. Now Debian container can invoke curl https://localhost:80 in order to communicate with nginx container. This is how you will be able to build container-to-container communication using right strategy. Now we need to discuss how pod will communicate to each other. In short, pod-to-pod communication. Pod-to-pod communication is enabled using following solutions. First, layer 2 switching solution. This is considered as the simplest approach and it works well for small deployments. In this particular strategy, pods and nodes should see subnet used for pods IP as a single L2 domain. Now, pod-to-pod communication will happen through ARP and L2 switching. We could use a particular bridge CNI plugin to reuse L2 bridge for pod containers. Second approach is to adopt layer 3 routing solution. It is considered as more scalable approach where we use node routing rather than switching the traffic to the pods. Again, in this scenario, we can use bridge CNI plugin to create a bridge for pod containers, but yes, we need to ensure that gateway is configured. Third strategy is overlay solution. Now, until there is a specific reason to use an overlay solution, it is generally not considered because it lacks support for multiple networks. Now, Kubernetes requires that nodes should be able to reach each pod even though pods are in an overlay network. Now let's try to understand layer 2 switching solution using a diagram which is currently displayed on the screen. In the screen, we can see one important element which is connected to pods present at both the sides. And that important element is KubeBridge. It needs to be pre-created such that ARP packet goes out of the physical interface In order to do that, we have another bridge with physical interface connected to it and node IP assigned to it, which cube bridge is hooked through the vth pair as it is demonstrated in the diagram. So we have cube bridge, then you have bridge with physical network along with vth pair among cube bridge and bridge with physical network, and this is implemented at both ends. We can also understand looking at the diagram that we can pass a bridge which is pre-created, in which bridge CNI plugin will reuse the bridge whenever it is needed. Now every pod present in a node will be allocated container subnet. We need to focus on what is node CIDR, what is container subnet that we are using, what are the IPs that are allocated to pods in both cases, and then implement cube bridge and bridge with physical network to implement layer 2 switching. Now what about layer 3 switching? In layer 3 switching, as we can see in the diagram, we have container bridge, and in both diagrams we can see we have route table which provides default route to other pods present in other nodes. Now we could populate the default gateway routers with the routes for subnet as it is shown in the diagram just below container bridge. Each node is having routes that are configured. Benefit is we can automate keeping the route table updated as nodes are added or deleted in the cluster. In order to do that, we can use certain container networking solutions which will take responsibility of automation. But in the current case, architecture is similar. What we are doing in layer 3 is we are using routing table instead of using bridge with physical network. And finally, overlay solution, where Kubernetes requires that node should be able to reach each pod even though pods are in overlay network. In order to do that, as the diagram indicates, which is entirely similar to previous diagram, that is layer 3 solution, we are able to see one extra artifact here, that is overlay tunnel. This is done in order to get a virtual or logical network that is overlaid on the underlay. Now, pod-to-pod traffic would need to be encapsulated at the source node itself, and the encapsulated packet will be forwarded to the destination node where it is de-encapsulated, and all that is managed by tunnels which are configured on each node. So depending on your need, you can select the right solution to enable communication between containers as well as nodes. In this video, we'll create a network namespace and list all the available namespaces by listing all the mount points. We need to understand that Kubernetes utilizes container runtime. In order to work with network namespaces, we need to work at container level. Let's try to understand how do we use namespaces in order to isolate network at container level, which in turn will be utilized by Kubernetes. To do that, first we will create network namespaces. To create network namespaces, we'll connect to the system and will ensure that Docker is installed. To confirm that Docker is installed, we'll write Docker followed by space version and we'll press enter. You'll find that it gives you the version of Docker which is installed. Now we'll clear the screen and we'll create two network namespaces. To create network namespaces, we'll be using command called IP followed by space netns, which stands for network namespace, followed by add, followed by the name. We have specified name as namespace 1. We'll press enter. Once you'll press enter, you'll get a new prompt. You can create one more network namespace. To do that, we'll be using the same command. We'll need to just change the namespace name to namespace 2 and we'll press enter. Now our objective is to see how many network namespaces are created. To do that, we'll write command that starts with IP, followed by space netns, followed by space list, and we'll press enter. You'll find that as of now you have 3 namespaces. One was created earlier and 2 we have created now. Now what happens when the IP tool creates a network namespace? It will create a bind mount for it under /var/run/netns folder. Now let's go ahead and see mount points of the network namespaces that we have created. To do that, we'll write ls followed by space /var /run /netns and we'll press enter. Once you'll press enter, you'll find the mount points. Now we need to go and list the interfaces that are visible inside the newly created namespace. And to do that, we'll be writing a command that starts with IP, followed by space netns, followed by space exec, followed by name of the namespace. I will write namespace 1, followed by space IP, followed by space A, and we'll press enter. Once you'll press enter, you'll find that loopback device is down and the route table is also blank. Now what we need to do in order to configure it? In order to configure it, we'll be creating a bridge. To create a bridge, we'll be writing a command that starts with brctl, followed by space add br, followed by space, let's say, docker 0. After writing the command, we'll press enter. Once you'll press enter, it will say that docker 0 is already existing. So we'll change the name to docker 1 and we'll press enter. Once you'll press enter, it will give you new prompt. Now let's go and see the bridge name, the bridge ID, and also the interface, whether it is enabled or not. To do that, we'll write brctl followed by space show and we'll press enter. Once you'll press enter, it will show you the bridge name, which is docker 1 that we have recently created. It allocates a bridge ID to it and it sets STP to no. Now we need to add IP link to the bridge that we have created. To do that, we'll write IP followed by space A, followed by space add, followed by IP address. For example, we'll add 172.31.56.253/16. After specifying the IP, we'll specify CIDR as well. And to do that, we'll write dev followed by space the bridge name, which is docker 1, and we'll press enter. Once you'll press enter, it will add IP link and it will set it to docker 1. Next is to ensure that we are able to set up the link. And to do that, after adding CIDR along with IP, we'll write a command that starts with IP, followed by space link, followed by space set, followed by space dev, followed by space docker 1, which is name of the bridge that we created, followed by space up. After writing the command, we'll press enter. Once you'll press enter, if successfully executed, it will come to a new prompt. And finally, we'll go and we'll see the route. To do that, we'll write route followed by space -n and we'll press enter. Once you'll press enter, you'll find that it has created a routing table with multiple destinations. This is how you can create a network namespace and list all the available namespaces by listing all the mount points and also configure route table. In this video, we'll create two HTTP server pods that responds on the port 8888 using the host name of the pod on which they are running. Then we'll verify that the pods are running in the cluster and query to list the network addresses of the pods. Now let's go ahead and create a file in order to configure two HTTP server listening at 8888 port. To do that, we'll create a file. To create a file, we'll connect to the master and we'll write vi followed by space followed by name of the file, which is c10_v6.yml. We'll press enter. First two lines are API version and kind. We are creating deployment, followed by metadata where we are specifying name to the deployment, that is HTTP deployment. We are specifying spec because we have specified replicas to be 2. Selector contains match labels where we have specified key as app and value as HTTP-test-pod. Then comes the template where we are specifying metadata followed by labels, and we are using the same key value pair that we have specified in selector, that is app, which is the key, HTTP-test-pod, which is the value. And then comes the spec where we are specifying containers, Name of the container that we are specifying is python-http-server. Image that we are taking is python:2.7. Command that we want to execute is /bin/bash, and then we are passing arguments within square bracket. We are using -c within double quotes followed by comma followed by double quotes, and within double quotes we are specifying echo hello from $hostname so that it can get the host name, and output of this is getting forwarded to index.html. that we are doing by using greater than symbol followed by space index.html followed by semicolon. We are specifying a command called python followed by space -m followed by space simple http server followed by space 8888, which is the port. And then we are specifying the ports where we are giving a name as HTTP, and container port that we are specifying is 8888. Now we'll press escape followed by :WQ in order to save and exit. Now we are out of editor. Let's go and create the deployment which creates the required pods. To do that, we'll write kubectl followed by space followed by apply followed by space -f followed by space followed by name of the file, which is c10_v6.yml. We'll press enter. Once we'll press enter, it will show that it has created the deployment. Now to see the pods, we'll write kubectl followed by space get followed by space pods followed by space -o followed by space wide, and we'll press enter. Once you'll press enter, it will show you the current status along with the nodes which are allocated. This is how you'll be able to create two HTTP server pods that responds on the port 8888 using hostname of the pod on which they are running. We use getPods command in order to verify the pods are running in the cluster, as well as used -o followed by space wide in order to query the list of network addresses of the pods. In this video, we'll identify the challenges of pod networking along with how services can mitigate the challenges using cloud native service discovery and why proxying is used for services. Now let's try to understand certain networking challenges in Kubernetes. And first challenge is, how do we manage network addressing? Networking in Kubernetes varies from traditional networking because we cannot use static IP addresses and ports for communication within Kubernetes. They are not suitable for Kubernetes as it identifies the network entity instead of IP address. Second challenge is network communication. As an administrator, it becomes a challenge to understand the communication between microservices because networking defines how communications happens in cloud and has become a critical component that will ensure that every aspect of microservice architecture is handled through implementation of proper network communication. So we need to be careful, specifically when we are going with cloud native solutions. Third challenge is network interface. From a long period of time, the networking community has been working hard on virtualizing many network functions into specific systems. They are called as virtual network functions. Now, these functions are implemented by VM-based organizations. So, when we go with container architecture, which are based on a particular organization, in order to attain their benefits, we will like to keep default values. And this is the reason why we need to be very specific when we are talking about network interface. Then comes network complexity. Kubernetes is deployed sometimes across more than one infrastructure platform. It can be multi-cloud, it can be hybrid plus on-premises, or it can be community cloud. Now, every cloud offers its own network policies, which makes tasks complicated. So whenever we are going for Kubernetes across multi-cloud providers or across multiple different types of infrastructure, we need to focus more on handling those challenges. Multi-tenancy is becoming popular because of cloud, and it is one of the challenges that a Kubernetes administrator has to face. You'll find that many enterprises deploy Kubernetes as a service. Now, when one cluster houses the lifecycle of application deployed on multiple tenants, and workloads, multi-tenancy must support Kubernetes across teams and environment, for which you need to do proper configuration, and that configuration is the challenge that an administrator will face. Now finally, network policies, which is one of the critical components for Kubernetes deployment. It needs to be carefully configured by administrator in order to avoid any conflict in policies. Now, after exploring networking challenges in Kubernetes, we need to also focus on cloud native service discovery. There are two different ways. First, client-side discovery, where client is responsible to determine which service instance it should connect to. It does it by contacting a centralized service registry component which keeps record of all the running services and their corresponding endpoints. Second type of discovery, which is supported by cloud native service discovery, is server-side discovery. In this particular mode, you'll find existence of load balancer, which will be placed in front of service instances. Now the client connects to well-defined URL of the load balancer, and load balancer decides which backend service it shall route the request to. Now let's go and briefly understand certain scenarios of service discovery. We are taking up 3 scenarios and we'll explain that using a diagram which is currently displayed on the screen. First scenario is you're not using microservices. So you will have facility to provide direct access to the service. So client in the first case, as it is displayed in the diagram, will communicate to the service directly. Now comes microservice client discovery. In order to ensure that changes whenever they are made in services does not impact client, and specifically if dynamic IP addresses are being allocated to services, we need to use a registry as an interface between client and service. Registry will keep on updating service, its details as well as endpoint in order to help client to discover the right service. And depending on the entry which is made in registry, whenever client will place a request, it will match to the corresponding entry and it will invoke the right service. Third is microservices server discovery, where, as the diagram indicates, which is there at the extreme right of the current screen, we are using a load balancer. So client will not directly communicate with the services or through a registry. Rather, they will connect to load balancer and load balancer will decide which service instance will serve the client. And finally, let's try to explore service proxying. Kubernetes comes with API server proxy that allows the user outside of the Kubernetes cluster to connect to cluster's IP, which otherwise might not be reachable. As it is displayed in the diagram currently visible on the screen, we are using API server which is configured in control plane. Client places request using kubectl. As a response to that particular request, your request passes through internet, goes to service load balancer, and from there, containers and applications running on pod is allocated to serve the client's request. So in the current case, API server acts as a proxy who provides reference of the pod where container along with application is deployed. So these are various techniques that can be used in order to access a service or a component. In this video, we'll create and define a service without a pod selector and manually map the service to the network address and port where it's running. Now we need to understand certain critical facts about services without selector. Services' objective is to abstract access to Kubernetes pods, but they can also abstract other kind of backends sometimes. For example, you want to point your service to a service in a different namespace or on another cluster. In this particular scenario, you can define a service without any pod selector. Now let's go and demonstrate how to define a service without pod selector and manually map it. To do that, we have created a file and name of the file is c10_v8. We'll open the file in order to do configuration. And to do that, we'll write vi followed by space followed by c10_v8.yml, which is name of our YML file. We'll press enter to launch the editor. Once editor is launched, you need to make certain entries that starts with API version, which is v1, kind is service. Metadata will specify to associate a name to the service, and name is service without selector. Then comes the spec, where we have to specify the ports, which includes protocol, port, and target port. Now, because this particular service has no selector, you will find that the endpoint object is not created automatically. For that, you need to manually map the service to the network address and the port where it's running. And that we will do by creating an object of type endpoints. After triple dash, we have specified another object declaration in the current YML file, which includes API version, that is v1, kind, endpoints, metadata to specify name of the service, and we have specified service without selector for that. Then comes the subsets, where we are specifying address. We have taken IP address as 172.31.59.112. And port that we are using is 9090, which is specified in the spec of the service as well. We need to ensure that the name of the endpoint object is valid DNS subdomain name. Now let's go ahead and save the configuration file and exit from the editor. To do that, we'll press escape followed by WQ. We'll press enter and we'll be out of the editor. Now let's go ahead and create the required objects. To do that, we'll write kubectl followed by space, followed by apply, followed by space dash f, followed by space name of the file, which is c10_v8.yml file. We'll press enter. Once we'll press enter, we'll find that the required service and the endpoint which facilitated us to manually specify the target IP and port has been created. This is how you can create and define a service without a pod selector and use endpoint to manually map the service to the network address and the port where it's running. In this video, we'll demonstrate how to configure multiple port definitions on a service object to expose the service on more than one port. One of the critical tasks is to ensure that your service is available over multiple different ports. That may be a need in order to make your service more accessible and available. Kubernetes comes with a solution where it helps you to configure multiple port definitions on a particular service object. And when you do that, you must ensure that you are giving your port names so that they are unambiguous. Let's go and configure a file in order to demonstrate how we can expose a service on more than one port. To do that, we'll open a file by writing vi space c10_v9.yml, which is our file. You can specify whatever name you want, but ensure that extension is .yml. We'll press enter. In the file, you have to specify API version to be v1, kind to be service, metadata. In order to give a name to the service, we are giving it a name called multi-port service. Then we will specify spec, where we are taking up a selector with one key value pair, that is app, and sample service, which is the value. Finally, we are specifying multiple ports. For the current service, we are using two different ports. First port is HTTP port, where we are using protocol as TCP. Port that we are allocating is 80. Target port is 9090. Then comes the second port, which is HTTPS. Protocol is TCP and port is 443, which is the default port that is associated with HTTPS in most of the servers. And target port that we are taking is 9092. After writing the configuration file, we'll save and we'll exit. To do that, we'll press escape followed by :WQ. Now we are out of the editor. Now let's go ahead and create the service by using kubectl followed by space apply followed by space dash f space followed by name of the file. After specifying name of the file, we'll press enter. Once you'll press enter, it will show you the service which is created. Now let's go ahead and get the service. To get the service, we'll specify kubectl followed by a space get followed by space svc and we'll press enter. Once you'll press enter, you'll find that your multi-port service is created and it has been allocated 2 ports. One is 80 and second is 443. This is how you can configure multiple port definitions on a service object to expose the service on more than one port. In this video, we'll recognize the role of endpoint slices along with the supported address types and describe the topology information. Now let's try to understand critical features afforded by endpoint slices. First feature is it always helps to track network endpoints. It is also highly scalable and extensible. Apart from that, it is also considered as an alternative to endpoint. Finally, plays important role to implement topological routing. Now, what types of addresses are supported by endpoint slices? There are 3 different types. First, IPv4, second, IPv6, and third is FQDN. So these are different types of addresses which can be intercepted by endpoint slices. Now let's try to understand one important fact about endpoint slices. Every endpoint within an endpoint slice can have relevant topology information as well. This is used in order to indicate where an endpoint is. Apart from that, what information it contains corresponding to node, zone, and region, when the values are available. And finally, the control plane takes responsibility of setting topology label, which can be of following types. First label is kubernetes.io/hostname, which indicates name of the node where the current endpoint is. Second is topology.kubernetes.io/zone, which indicates the zone. Third is topology.kubernetes.io/region, which indicates the region where that endpoint is. And finally, let's try to have a look over configuration file that helps to configure endpoint slice. Line number 1 and line number 2 are API version, where we are specifying discovery.k8s.io/v1 beta1. Current configuration is following YAML format. Second line is kind, where we are specifying what type of Kubernetes object we want to create, and it is endpoint slice. Third comes the metadata, where we are giving a name to endpoint slice. In the current case, name that we are specifying is test sample. And then comes label that we are associating with the current object. It is kubernetes.io/service-name:test, where test is the value, kubernetes.io/service-name is the key. And finally, we are specifying what type of address this endpoint slice need to support. And that we are doing by specifying address type :IPv4. And the last entry which is there present in the current configuration file is ports, where we are specifying 3 essential properties. First is the name, which is HTTP. Second is type of protocol, which is TCP. And third is the port. Apart from that, one of the most important entry that you need to specify in your endpoint slice configuration file is endpoints itself, where we'll be using addresses. Below addresses, we'll specify an IP address, and then we'll specify conditions. Ready, true, it means it is ready to use. Host name, pod-1, which is name of the host where this endpoint slice will be present. And finally, topology labels, we are specifying 2. First is kubernetes.io/hostname:node-1. And second label of topology that we are specifying here is topology.kubernetes.io/zone: one of the zones of your cloud provider. In current case, we are using configuration for AWS. This is the reason why we have specified US-west2-A. This is how you can use endpoint slice along with supported address types and topology information. In this video, we'll list and describe the features of prominent types of Kubernetes services. Let's first start understanding what are services in Kubernetes. Services are considered as an approach in Kubernetes to expose an application so that clients can consume it. In Kubernetes, services are determined by selectors which are specified in manifest files. Apart from that, Services also define logical sets of pods and policies which can be used in order to access those pods. And primary objective of services in Kubernetes is to decouple pod backend with front-end clients. Now, after exploring what services are in Kubernetes, now let's try to understand anatomy of service in Kubernetes. We'll assume that you have web browser so that user can access applications. Now let's go through the current diagram which is displayed on the screen. Using web browser through internet, request will be made in order to access a deployment which has a pod, and on pod you have container where you have your application. Through internet, request will access service which will be exposed using an IP and node port. That node port will point to node on which your pod is present with the containers that holds applications which are configured in deployment. Now, there are various different types of services in Kubernetes. Let's try to explore what all different type of services are there in Kubernetes. But before that, we'll try to understand anatomy of service. There will be a traffic which is considered as request. It will go through a proxy, and from proxy it will invoke services which will access applications running on pod. In response to execution of the service, there will be response which will be sent back to the appropriate user. Now, the current diagram which is displayed on the screen displays a specific type of service called as cluster IP. This is the default service types provided by Kubernetes. It exposes the service on a cluster internal IP, which can be only the source to reach service within the cluster. Now let's go through the second type, which is load balancer. Load balancer will expose the service externally using load balancer of your cloud provider. We need to understand that the load balancer routes to appropriate node port and cluster IP services which are created dynamically and automatically. As the diagram indicates, now your traffic will be routed through load balancer. Third service type is node port. This type of service exposes the service on each node's IP at a static port. Now, what happens when you are using node port? When you are using node port, internally a cluster IP is created automatically and the node port service will route to it. But from outside the cluster, you have to contact the node port service by using appropriate addressing scheme, which is node IP followed by colon followed by port. As the diagram indicates, traffic invokes and it connects to appropriate node port, which in turn generates a dynamic cluster IP in order to provide communication to the pods and the services. Now, there is a special type of service in Kubernetes called as ingress. An objective is to provide load balancing, SSL termination, as well as name-based virtual hosting. Now, let's go through the diagram. In the diagram which is currently present on the screen, your traffic comes to ingress where you have the details. It has domain details, service detail, and few other details which can be specified in ingress. And then traffic is routed to appropriate service which is running in Kubernetes cluster. These are different types of services which are present in Kubernetes. Now we need to also focus on one of the essential elements that is called as proxy mode for services. And there are three different proxy modes which can be used. First is proxy mode, which is user space. In this particular mode, you'll find that kube proxy keeps always an eye on the Kubernetes master. It will watch for the service and endpoint objects that gets added or removed. And for each service, this particular mode will open a random port on your local node. So whenever you connect to proxy port, they are proxied to a services backend pod and reported in the endpoint. Then comes the second approach, which is IP tables. Now, when you have this particular mode on, kube proxy continues to watch the Kubernetes master for added or removed services and endpoint objects. And for each service, unlike in user space, this mode installs IP table rules in order to capture the traffic to the services, cluster IP and port, and then finally redirects that traffic to a service backend set. And third is IPVS. In this particular mode, again, kubeproxy will watch the service and the endpoint, and it calls netlink interface in order to create appropriate IPVS rule. After creating IPVS rules to ensure IPVS status is consistent with its expectation, the mode will periodically sync IPVS rules with services and endpoints. Now, whenever a service is accessed, traffic will be redirected to a backend pod. And finally, let's try to understand discovering Kubernetes services. There are two different ways. First, DNS, which is a recommended method, where DNS server is added to the cluster in order to watch the Kubernetes API that creates DNS record set for each new service. And second is by using env-var. In this particular discovery method, a pod runs on a node, so you will have kubelet which adds environmental variable for each active service. So depending on your need, you can select the right kind of service that you want to configure in Kubernetes. In this video, we'll create a configuration file to configure type node port and type load balancer to enable Kubernetes control plane to allocate a port from a range and provision a load balancer for the service. To do that, we need to create a file. To create a file, we need to use editor of our choice. We are using VI editor. In order to launch VI editor, we'll write VI followed by space name of the file. Ensure that extension of the file is YAML. We'll press enter. Now we are defining two essential components. One is type node port and second is load balancer. Node port is defined in configuration file by specifying API version to be v1, kind to be service. Metadata should be used in order to give a name to your service. We are using name as my node port. Then we are providing the spec which contains type and value of type is node port. Then comes selector. We are using app followed by my app service as the value of app selector. Then we are using ports in order to configure port, target port and node port. You can specify port, target port, node port of your choice, but you need to ensure that they are within the range. Next is load balancer. To do that, after triple dash, we are writing API version :v1, kind is service, metadata, name my node port LB in order to ensure that we are able to give a name to our service which is of type load balancer. Then we are using spec in order to define selector. We are using the same selector which we have used in node port. And finally, we are using ports where we are specifying protocol to be TCP, port to be 80 and target port to be 9376. Apart from that, depending on your load balancer configuration, you need to get the IP and you need to specify it in cluster IP, which is 10.0.171.239. We have commented it because this is the place where you need to ask load balancer IP and specify. Finally, we are specifying type to be load balancer. After configuring the file, we'll save the file by pressing escape followed by :WQ and we'll press enter to exit from the editor. Now let's go ahead and create node port and load balancer. To do that, we'll be using command that starts with kubectl followed by space apply followed by space -f space followed by name of the file which is c10_v12.yml in our case. We'll press enter. Once we'll press enter, you'll find that it has created the required service. This is how you can write a configuration file to configure type node port and type load balancer. In this video, we'll create a deployment that runs 3 replicas of an application and create an internal TCP load balancer using a service. To do that, we need to create a configuration file. And to create a configuration file, we'll write vi followed by space followed by the file name, ensuring that extension is YAML. We'll press enter. Our first task is to create a deployment that runs 3 replicas. In order to do that, first 2 lines are API version and kind, where we specify deployment. Then we give a name that is sample-deployment below metadata. We specify a label and then we go for specs where we specify replicas to be 3. Selector is defined with match labels where we are using app as key and NGINX as value, and then we have specified template where labels are specified to be app and NGINX again. And finally, we are giving spec to container where we are giving name as NGINX, image to be a particular version of NGINX which will be pulled, and finally the ports. We are giving container port as 80. After defining deployment, our next objective is to define a service of type internal TCP load balancer. For that, we have given / in order to separate and start a new configuration. We'll start with API version :v1 client service. We'll use metadata to give a name that we are specifying is internal-lb app. And then comes annotations, which we are using in order to configure it in form of internal load balancer. Annotation that we are using for now is for Azure load balancer. To do that, we are writing service.beta.kubernetes.io/azure-load-balancer-internal, and we are setting it to true. Then comes the spec where we are specifying type to be load balancer. We are using ports. We are using only one port, so we have specified 80, and then comes the selector, which is app internal-lb app. Finally, after doing the configuration, we'll save and exit. To save, we'll press escape followed by :WQ and enter. Now we will create the objects. To do that, we'll write kubectl space followed by apply followed by space -f c10_v13.yml in our case. We'll press enter. Once we'll press enter, it will create the required deployment with 3 replicas as well as internal load balancer. Let's go and verify. To verify number of replicas are created or not, we'll write kubectl followed by space get followed by space rs, that is for replica set. We'll press enter. Once you'll press enter, you'll find that your sample deployment has been allocated 3 replicas where it shows desired is 3, current is 3. This is how you can create a deployment that runs 3 replicas of an application and creates an internal TCP load balancer using a service. So in this course, we have examined the networking model and the different types of services that can be implemented in Kubernetes, how to create namespaces, implement pod network, map services to pod network addresses, and create and configure node port and load balancer. We did so by exploring the Kubernetes network model, the networking problems that we can address using Kubernetes cluster networking, the prominent technologies for implementing Kubernetes networking model, along with the concept of container-to-container networking, and how Kubernetes enables pod-to-pod communication. How to create a network namespace, list all the available namespaces, create 2 HTTP server pods that responds on the port 8888 and list the network addresses of the pods. The features of the prominent types of Kubernetes service, the role of endpoint slices, the supported address types, and how to create and define a service without a pod selector. How to create a configuration file to configure type node port and type load balancer to enable Kubernetes control plane to allocate a port and provision a load balancer for the service. How to create a deployment that runs 3 replicas of an application and create an internal TCP load balancer using a service. In the next course, we will learn to create and manage different types of Kubernetes services, service account objects, API token, and add image pull secret to service account. In this video, we'll write configuration to create pods running NGINX cluster-wide address space and create a service for NGINX replicas using kubectl expose command. In order to create pods running NGINX cluster, we need to create a configuration file. Let's move to the directory where we want to create the configuration file. And that we will do by writing cd space, name of the directory, which is C11 in our case. Once we are there in the directory, we'll write command in order to open a file where we want to write configuration. To do that, we'll write vi followed by space name of the file, which is c11_v2.yml in our case. We'll press enter. First 2 lines are API version and kind. We are going to create a deployment where we'll specify Nginx cluster specification. After specifying kind, we need to associate it with the name that we are doing by writing metadata, and below metadata we are using an element called as name, and we are giving a name as test Nginx, followed by spec, which includes selector, match labels, and we are specifying run to be the key and test Nginx to be the value of the label. We are specifying replicas to be 2, and then we are specifying template along with metadata, and below metadata we are specifying labels, where again we are using the same label key that is run and the same value that is test Nginx. And then comes the final specification, which is most important, that is containers, specifying 3 essential properties of containers in our YAML. First is the name, which is test Nginx. Second is image, which is Nginx. And finally ports, which we are specifying as 80 by specifying it to container port attribute. After creating the file, we'll save and we'll exit. To do that, we'll press escape followed by :WQ. After writing :WQ, we'll press enter and we'll find that now we are back to the prompt. At prompt, we have to create deployment. To do that, we'll write kubectl followed by space apply followed by space -f followed by space name of the file. After specifying the command, we'll press enter. Once we'll press enter, we'll find that it creates a deployment called test Nginx. Now your deployment is ready, which makes it accessible from any node in your current cluster. Now let's go and see how many nodes are there. To see number of nodes, we'll write kubectl followed by space get followed by space nodes and we'll press enter. Once you'll press enter, you'll find current nodes of the cluster, out of which 1 is master and 2 are worker. Now let's go and check the nodes the pod is running on. To do that, we'll write kubectl at the prompt followed by space followed by get followed by space pods followed by space -l followed by space run equal to, you'll specify the name, which is test Nginx. After specifying the name, in order to see the IP address of nodes where these pods are running, you'll specify space -o followed by space wide and you'll press enter. Once you'll press enter, you'll find that it displays IP address of the nodes where these pods are running. Now we have checked that pods are running on different nodes. We'll clear the screen by writing clear. Now our next objective is to create a service for Nginx replicas. And for that, we'll be using expose command. To use expose command, we'll write kubectl followed by space expose followed by space deployment / test Nginx, which is name of our deployment. After writing the command, we'll press enter. Once you'll press enter, it will show you a message that indicates that now your service of test Nginx deployment is exposed. Now let's go ahead and check the service. To check the service, we'll write kubectl followed by space followed by get followed by space svc, which indicates service, followed by space test Nginx. After writing the command, we'll press enter. Once you'll press enter, it will show you detail of the service, where it displays name, type, cluster IP, external IP, ports, and age. This is how you can write configuration file to create pods running Nginx cluster wide address space and create a service for Nginx replicas using kubectl expose command. In this video, we'll describe approach and primary modes of finding a service supported by Kubernetes. There are 2 prominent ways in which we can work on services. First is SOAP based and second is REST based. Services in Kubernetes are typical REST objects. It means they are accessible using HTTP protocol. Apart from that, services will facilitate to post service definition to API server for further processing. And finally, we can also consider services to be an abstraction that provides abstract access to Kubernetes pods. Now let's try to understand it using a diagram which is currently displayed on the screen. User will place the request over internet. It means HTTP protocol, and that particular call will be intercepted by API server, and API server will delegate the right pod which has to serve the request. This is the reason why in the diagram at the right we can see there are two different types of pods which are aligned. At the bottom we have backend pods where you will have databases. Then you will have service backend which will access your database running in backend pods. And call to access backend will be made from front end, which is deployed in containers served by front end pods. In other words, whenever user sends a request, API server will translate that request. It will be managed by API server in order to delegate that request to be processed by right set of pods. We need to also understand that pods and containers will be diversified and they will be distributed across multiple nodes. Now let's try to understand how do we define services in Kubernetes. There are two different approaches. First, service with selector, and second is service without selector. Now let's go through service with selector. To define service with selector, in manifest file, first two lines will always specify API version and kind. Kind will be of type service, then you have to give a name to the service by using metadata, followed by spec which contains selector, because we are going to define service with selector, which is best practice. We are using selector. Selector has an attribute in order to specify selector label that is specified in the current configuration in form of app:/myapp. And then comes service description where we specify protocol, port and target port. Now, if you want to define service without selector, rest of the entries will be common. You need to just delete selector from spec. Now, after defining services, you need to identify approach or modes of finding services. There are two prominent approaches. First, you can adopt environment variables, where when a pod runs on a node, kubelet will add environmental variable for each active service, which will be used in order to find the service. And second mode is DNS. In this particular mode, DNS server is added to the cluster in order to watch the Kubernetes API that creates DNS record sets for each new service. Now let's go and try to understand certain features of environment variables. Environment variables will facilitate service to be addressed automatically because it is automatically injected in containers. In short, environmental variables will be available in containers itself, which will specify service addressing scheme. Second feature is you need to follow naming convention which is based on service name. In short, Kubernetes will automatically inject environmental variables in containers, and these environmental variables will provide the address to access services. Second approach is DNS approach, where you'll find that records are automatically created in cluster DNS, and containers have capability to automatically get configured so that they can query to cluster DNS. Let's try to understand it using a diagram which is currently displayed on the screen. We have GKE cluster, which is Google Kubernetes cluster. It means your Kubernetes cluster is hosted in Google Cloud. We can see two worker nodes, and each worker node is specified with a particular IP address. Whenever there will be call, there will be lookup in DNS table, and from the DNS server using CubeDNS SVC, that is service, it will be able to intercept the actual destination and discover the service. In the current case, we are using GKE cluster, and this is the reason why we are using Cloud DNS. In order to sum up, we can say that when we use DNS, records are automatically created in cluster DNS. In the current case, it is Cloud DNS, and containers will automatically get configured so that they can query Cloud DNS using CubeDNS SVC or service. And CubeDNS autoscaler will also facilitate to get the right DNS as a result of query. This is how you will be able to define your service and decide the right mode in order to facilitate and locate the service. In this video, we'll create a manifest file to create service of type cluster IP using kubectl apply and use kubectl get service to see the stable IP address of the service. Now let's write manifest or configuration file in order to create a service which targets a particular TCP port on any node. To do that, we need to write a configuration file. Before we write configuration file, we need to ensure that all nodes are up and running. To do that, we'll write kubectl followed by space get space nodes and press enter. And you'll find that all nodes of the current cluster are ready. Now let's go ahead and write the configuration or manifest file. To do that, we'll write vi followed by name of the file. After writing name of the file, we'll press enter. After pressing enter, it will launch the editor where we need to write our specification. To do that, line number 1 and 2 are all about API version and kind. Ensure that you are using service for kind. Then comes metadata, where you are giving a name to it. We have given name as web server. We are also specifying labels under metadata, where key is run and value is web server. Then comes the specification of the service, where we are specifying ports, where port is 80, protocol is TCP, and selector that we are using is the label that we have specified under metadata, that is run as the key, web server as the value. After writing the configuration file, we'll save and we'll exit. To do that, since we are using VI editor, we'll press colon followed by WQ and enter. Now we are out of editor, where we'll go and we'll use kubectl apply command in order to interpret YAML and create the desired objects. To do that, we'll write kubectl followed by space apply followed by space -f followed by name of the file. After specifying the command, we'll press enter. You'll find that it creates the service called web server. Now let's go ahead and check the service, where we can track what type of service it has created. To do that, we'll write kubectl followed by space get followed by space svc followed by name of the service, which is web server. After writing the command, we'll press enter. Once you'll press enter, you'll find that it has created a service and it has allocated a cluster IP. It means that if we will not specify type of service, by default, it creates service of type cluster IP. This is how you can write a manifest file that creates a service of type cluster IP using kubectl apply and use kubectl get service in order to get the stable cluster IP address. In this video, we'll create a manifest file to create a service of type node port and use kubectl get service -OYML command to view specification and stable IP address. Primary objective of node port kind of service is to expose the service on each node's IP at a static port. In order to do that, we need to write configuration file and specify the right fields that helps Kubernetes control plane to allocate a port. But please remember, there is a specific range which is configured for Kubernetes control plane. By default, it is from 30,000 to 32,767. We need to remember this number because we have to select one of the port from this particular range. Now let's go ahead and write a specification in order to create service of type node port. To do that, we'll write vi followed by space name of the file that we want to create and we'll press enter. Once we'll press enter, we need to write certain configurations where we have to specify API version to be v1, kind to be service. This helps Kubernetes API server to understand what kind of object we are requesting to create. Then comes metadata, where we have to specify a name for the current service, followed by spec, which is divided into 3 essential elements. First is type, we need to specify it as node port. Second is selector, which we are specifying using key value of run, followed by value, that is web server NP. And finally, we are going to work with ports, where first port is port, we have specified 90. Then comes target port, which is set to same value as the port field. And finally, we have node port, where we are specifying port within the specified range that we discussed, where it should be between 30,000 and 32,767. We have taken 31,001 as our node port. After writing the file, we'll save and we'll exit. To do that, we'll press escape followed by :WQ. Once we'll press enter, it will take us out of editor and we'll be back on the command prompt. Once we are back on the command prompt, we have to create the service. To do that, we'll write kubectl followed by space apply followed by space -f followed by space name of the file, which is c11_v5.yml. We'll press enter. Once we'll press enter, you'll find that service is created. Now let's go ahead and see the details of the service by writing kubectl followed by space get followed by space svc followed by space name of the service, which is web server node port, followed by space -o followed by space YAML in order to specify the format in which we want output to be. We'll press enter. Once you'll press enter, it will display you detail of the service where it is using cluster IP and type of service that we have created is node port with the specified port. This is how you can create a service of type node port using a manifest file and then use kubectl get service -OYML command to view specification as well as stable IP address. In this video, we'll create a manifest file that helps us to create a service of type load balancer and use kubectl get service command to view specification and stable IP address. Now, we all know that on cloud providers which supports external load balancer, we can set the type field to load balancer, which provisions a load balancer for your service. But we need to understand that creation of load balancer happens asynchronously. Now let's go ahead and see how to write configuration file in order to utilize capability of cloud providers supported external load balancers. To do that, we'll first create a file. To create a file, we'll write vi followed by space name of the file. Ensure that file is YAML. We'll press enter. First two lines are again similar to the previous lab, that is API version is v1, kind is service, metadata name we have changed to web server LB service. Most important part is in spec where we are specifying a selector for future use and key for the selector that we are specifying is run : web server NLB. Then comes the specific configuration to tune this service as load balancer service, for which we are using port, target port and protocol. You need to find out from your cloud administrator IP address of load balancer. Now, some cloud providers allows you to specify the load balancer IP. In those cases, the load balancer is created with the user specified load balancer IP. But if you will not specify load balancer IP, the load balancer is set up with an ephemeral IP address. In order to specify an IP, we are using cluster IP : 10.0.171.239. For now, we have commented because you need to replace it with your load balancer's IP. Finally, we are specifying type, which is load balancer. After writing the manifest file, we'll save and we'll exit. To do that, we'll press escape followed by :WQ and enter. Now let's go ahead and create. To create, we need to write kubectl followed by space apply followed by space -f followed by space name of the file, which has configuration where you are creating service of type load balancer. We'll press enter. Once you'll press enter, you'll get a message indicating that service is created. Now let's go ahead and see the details of the service which was created. To do that, we'll write kubectl followed by space get followed by space svc space and we'll specify name of the service, which is web server LB service in our case. We need to specify space -o followed by the format that we want. We want YAML. So we'll specify YAML and press enter. Once you'll press enter, you will get detail of your service. Confirm that type of service is load balancer. This is how you will be able to create a manifest file that helps you to create a service of type load balancer and then use kubectl get service command in order to get details in YML format. In this video, we'll create a manifest file to create a service of type external name and use kubectl get service command to view specification and stable IP address. Now, an external name service is a special case of service. We need to understand that it does not have selectors. Apart from that, it will also not define any ports or any endpoints. Rather, it serves as a way to return an alias to an external service that is present outside the cluster. Assume that we have a service outside the cluster and we want to create an external name service for that. To do that, let's first create a namespace. To create a namespace, at the prompt we'll write kubectl followed by space create. Followed by space, what we want to create is namespace. So we'll specify namespace followed by space and we'll write external services. We'll press enter. Once you'll press enter, you'll find that your external services namespace is created. Now we need to create a configuration file and there we have to create an external name service within the namespace that we recently created. We'll write vi followed by space name of the file and press enter. Now, once that file opens, you need to write certain configurations, which starts with API version and kind. Kind is service, API version is v1, then we are giving a name by using metadata. You need to be careful when it comes to namespace. We'll change the value of current namespace to the namespace that we have created. So we have specified the namespace and now we'll specify the spec, where we have to just specify type, which is external name. An external name will be specified with the DNS of the service that you want to access. Now, what happens here when your Kubernetes server starts looking up for the host, you will have cluster DNS service, which will read CNAME record with a particular value that you have specified beside external name. Accessing these kind of services will work in the same way as others, but there will be one major difference, and that difference is redirection will happen at DNS level, but no proxying or forwarding will occur. Let's go and save the file after writing the statements by pressing escape followed by :WQ and press enter. Once you come back to your prompt, you need to use kubectl at the prompt followed by space apply followed by space -f followed by space name of the file, which is c11 _v7.yml. We'll press enter. Once you'll press enter, you'll find that it has created external service. Let's go ahead and see whether that external service is created or not. After writing the command kubectl space get space sbc space external service, which is name of the service, followed by space -o followed by space yml followed by space -- namespace equal to external services, which is the name of the namespace. We'll press enter. Once we'll press enter, we'll be able to get the details of the service. This is how you'll be able to write a manifest file that helps you to create a service of type external name and also use kubectl command in order to view specification and stable IP. In this video, we'll use kubectl command to view service account in the namespace, create additional service account objects and retrieve dump of the service account object. Now we know that every namespace has a default service account resource, which is called as default. You can list this and any other service account resources in the namespace with the following command. We can list all the service account resources in the namespace by using kubectl followed by space followed by get followed by space service accounts. We'll press enter. Now once you'll press enter, it will show you name of the service account. In order to get in a particular namespace, we'll write kubectl followed by space followed by get followed by space followed by service accounts followed by space followed by -- namespace equal to name of the namespace, and name of our namespace, which we created in previous video titled create external name service, is external services. We'll press enter. Once you'll press enter, you'll find that there is a default service account within your namespace as well. Now, how to create additional service account objects? To do that, first we'll clear the screen by writing clear. We'll create a configuration file, and that configuration file will have details of how to create and use service accounts. To do that, we'll write vi followed by space c11 underscore va.yml, which is name of our YML file. We'll press enter. Now, our first object that we are going to create is service account itself. To do that, line number 1 and line number 2, we have specified API version, which is v1, and kind is service account. Then comes metadata, where we are giving name to our service account, which is sample account, and we are also specifying namespace, which is external services. Assuming that our service is created, now our next objective should be to create a new secret manually. And you need to ensure that newly built secret is populated with an API token from the service account which you are going to create. To do that, we are creating one more object of type secret. After triple dash, we are writing API version :v1. Kind is secret. Metadata, we are specifying name to be sample secret. Namespace is external services. Annotations, which we are going to use in order to help identification of relevant object, is kubernetes.io/service-account.name, and we are specifying name as sample account. And finally, type :kubernetes.io/service-account-token. After writing the configuration file, we'll save and we'll exit. To do that, we'll press escape followed by :wq and we'll press enter. Now we have written the configuration file. Let's go ahead and create it by writing kubectl followed by space apply followed by space -f followed by space c11 underscore v8.yml file at the prompt. After writing the command, we'll press enter. Once you'll press enter, you'll find that new sample account is created and sample secret is created, which is populated with the API token for sample account service account that we have created earlier. Now let's go ahead and see the details. To do that, we'll write kubectl followed by space describe followed by space secrets / name of the secret, which is sample secret. We'll also specify the namespace by giving space followed by -- followed by namespace followed by space name of the namespace, which is external services. We'll press enter. Once we'll press enter, we'll get details of the tokens that was created. This is how you can use kubectl command to view service account in the namespace and create additional service account objects to retrieve dump of the service account object. Now let's go and confirm how many service account objects are there in current namespace. To do that, we'll write kubectl followed by space get followed by space service accounts followed by space -- namespace equal to external services. We'll press enter. Once you'll press enter, you'll find that your sample account, which is service account, is created and it is available. In this video, we'll modify default service account for the namespace and use secret as an image pull secret. Now let's go ahead and first add image pull secret to our service account. Before that, we will see what all service accounts are present in our namespace. We created a namespace and a service account in video titled Managing Service Account Objects. In order to see what all service account objects are there, we'll write kubectl followed by space followed by get followed by service accounts followed by space followed by -- namespace equal to name of the namespace, that is external services. We'll press enter. Once you'll press enter, you'll find two. One is default and second is sample account. Now let's go ahead and add image pull secret to a service account. We'll select default service account for that and we'll write a command that starts with kubectl followed by space followed by create followed by space followed by secret followed by space docker - registry followed by name, that is test registry key followed by space -- docker - server equal to hub.docker.com. You can specify your own server URL as well. Followed by space -- docker - username equal to Cody Blackwell test followed by space, followed by dash dash docker dash password equal to password that you have specified for your Docker hub, followed by space, followed by dash dash docker dash email and the email ID. We'll press enter. Once you'll press enter, it will create test registry key, which is a secret. Now we can go ahead and we can verify. To verify, we'll write kubectl followed by get, followed by secrets, followed by test registry key. We'll press enter. Once you'll press enter, you will get the details. Now we want to create a secret in a specific namespace, for which we'll move back to the previous command where we have specified kubectl space create, and at the end we'll write dash dash namespace equal to external services. We'll press enter. Once you'll press enter, you'll find that it has created test registry key in your namespace as well. To get the details, we'll write kubectl followed by space, followed by get, followed by space, followed by secrets, followed by space test registry key, followed by space will specify dash dash namespace equal to name of the namespace, that is external services in our case. We'll press enter. And you'll find that it displays image pull secret that you have created for a service account. Now we need to add image pull secret to a service account. After creating image pull secret, we'll right clear to clear the screen, and we'll use a command called kubectl patch in order to modify the default service account for the namespace to use this secret as image pull secret. We'll write the command that starts with kubectl followed by space patch followed by space name of the service account. Our service account is service account. If you want to apply it on default, you need to change the name of the service account, which is sample account specified after service account in the current command, to default. Let's not disturb the default and apply the patch on one of the service account that we have created in lab title managing service account objects. So we have specified sample account followed by space, followed by dash dash namespace equal to external service, followed by space dash p, followed by space image pull secret, and we have specified name attribute to be test registry key that we have created recently. Ensure that this entry is there in curly braces because it will be sent to API server in form of a REST call. So you need to ensure that this part is present in single quotes and all the strings are in double quotes. Finally, we'll press enter. In case if you get typo, it will indicate what typo you got. We have missed one S here, so we have specified the wrong namespace. We'll correct the namespace and finally we'll press enter. Once you'll press enter, you'll find that it displays a message indicating service account / sample account is patched. Now finally, let's go and see the output. To see the output, we'll write kubectl followed by space, followed by get, followed by space service accounts, followed by space name of the service account, which is sample account, followed by space dash dash namespace equal to name of the namespace external services, followed by space dash o, followed by space YAML. You can redirect and store the output in a particular file. For now, we'll press enter. Once you'll press enter, it will show you the detail of your current configuration. If you want to create a dump, after YAML, you need to specify space greater than followed by space name of the file. Let's name it as dump.yaml. We'll press enter and you'll find that it creates dump. To confirm, we'll write ls at the prompt and press enter. And you'll find that you have dump.yml file, which contains dump of your current service account. This is how you can modify default service account or any service account of your choice for the namespace and use secret as an image pull secret. In this video, we'll recognize features of components that are used to implement automation of service account. Let's first discuss what is a service account. Service accounts are processes that runs inside pod in Kubernetes cluster. We need to also understand that service accounts are always namespaced. It means they are bound to a particular namespace. Now, what is the primary objective of service account? Service account is considered as lightweight object that allows cluster users to create service account for specific task followed by the principle of least privilege. After understanding role of service account, let's go ahead and list service automation components. There are three critical components. First component is service account admission controller. It is part of API server and it acts synchronously to modify pods as they are created or updated. And modification of pods is implemented using a plugin called as admission controller. We can say that this is one of the essential components of service automation. Second is token controller, where token controller will run as part of Kube controller manager, but it acts asynchronously. And third component is service account controller, which manages service accounts inside namespaces and also ensures a service account name default exists in every active namespace. And finally, let's try to understand provisioning service account. Now we know that when a kubelet starts a pod that will run as a service account, it will place a request and that request will be JSON web token, which will be facilitated by Kubernetes API server. There are multiple different container networking interface plugins where we have experienced leaking credentials into logs and moving to new credentials by replacing service accounts, which was painful even for experienced Kubernetes operators. And there comes automated provisioning service account need, where you will have 4 participants as it is displayed in the diagram. First will be Kubernetes API server, second will be kubelet, third will be pod, and fourth will be your other apps. Now, what is role of Kubernetes API server? There are 3 essential tasks. First, pod setup, second, presentation, and third is reissuance. Now, let's try to understand pod setup, where Kubernetes API server will place request to kubelet to start pod. Kubelet in turn will place request for a token, and Kubernetes API server will issue the token. Using that token, it will start pod with token volume. And finally, it will present token to other apps. And once pod has started, it will be reported back to Kubernetes API server. Now, there are 2 other activities that Kubernetes API server need to facilitate. First, to manage request token. And second, to reissue token whenever it is needed. And whenever there is reissue, kubelet will refresh token and it will serve it to pod. And finally, other apps will send the response once token is presented. This is how service account is provisioned using various different components of Kubernetes cluster. In this video, we'll use kubectl commands to create, describe, delete or invalidate API tokens for a service account. Now first, let's go ahead and see how many service accounts are there which we have created for now. To do that, we'll write kubectl followed by space get followed by space service accounts followed by space dash dash namespace equal to name of the namespace, which is external services. We'll press enter. Once you'll press enter, it will locate all the service accounts and it will list it. Now let's go ahead and describe a service account. To do that, we'll write kubectl followed by space followed by describe followed by space followed by service account followed by space followed by name of the service account. For example, we'll use space sample account, which is the name of our service account. We'll press enter. You need to ensure that whenever you want service account from a particular namespace, you need to specify dash dash after giving a space, namespace equal to external services. Press enter. And you'll find that it gives you a brief description about your current service account, which includes name, namespace, label and annotation if any, image pull request that you have configured, mountable secrets and tokens. This is how you'll be able to describe. Now let's go ahead and delete or invalidate a service account token secret. So once you describe, you will get image pull secret. Name of the secret is test registry key. we'll go ahead and delete service account token secret to invalidate it. To do that, we'll write kubectl followed by space followed by delete. Followed by space, we'll specify secret followed by space name of the secret, which is sample secret, which you will find at the bottom once you will describe a particular service account. So we got to know the secret is sample secret. We need to also specify the namespace. For that, we'll give space dash dash namespace equal to external services and we'll press enter. Once you'll press enter, it will give you a message indicating that your secret has been deleted. This is how you'll be able to use kubectl command to create, describe, delete or invalidate API tokens for a particular service account. In this video, we'll recognize features afforded by Service Catalog and describe Service Catalog architecture that need to be configured to communicate with service brokers. Now let's try to first recognize critical features of Service Catalog. Service Catalog is considered as an extension API to use externally managed softwares. Second, it uses Open Service Broker API that enables communication with service brokers. And third feature is its capability to provide cluster operators to browse list of managed services. And finally, it uses aggregation layer. Now, what all are the API resources of Kubernetes cluster? First is Cluster Service Broker, whose responsibility is to encapsulate server connection details. These are created and managed by cluster operators who wish to use the broker server to make new types of managed services which would be available within their cluster. Second is Cluster Service Class. It's a managed service offered by a particular service broker. When a new Cluster Service Broker resource is added to the cluster, you'll find that Service Catalog Controller connects to the service broker to get a list of all available managed services. Once it gets, it creates a new Cluster Service Class resource corresponding to every managed service. Third is Cluster Service Plan. It's a specific offering of a managed service. Let's take an example. Assume that a managed service have different plans available. For example, it may come up with a free tier, paid tier, or it may also have different other configurations, such as using SSD storage or having more resources. It is similar to Cluster Service Class when a new Cluster Service Broker is added to the cluster. In response to that, Service Catalog creates a new Cluster Service Plan resource corresponding to every service plan available for each managed service. Fourth is Service Instance. It is a provisioned instance of a Cluster Service class. And finally, Service Binding, which provides access credentials to a service instance, which are created by cluster operators. Now let's go through Service Catalog architecture. We need to know that Service Catalog uses Open Service Broker API in order to communicate with service brokers. Typically, it acts as intermediary for Kubernetes API server so that it can negotiate the initial provisioning and get the credentials which are necessary for the applications to use any managed service. As the diagram currently displayed on the screen indicates that you will have Service Catalog which will use Open Service Broker API in order to list services, provision instances, and finally bind instances. Then you have app, which contains all the connection credentials as well as service details. And binding between app instance and Kubernetes catalog will be done using Service Catalog objects. All the requests will be managed by API server. So whenever you have service broker who has managed services, you can use Open Service Broker API to provision instances and finally bind your application with Service Catalog. Now let's try to focus on authentication methods which can be applied in Service Catalog. There are two. Basic, which typically has user ID password, and then you have OAuth, which is token based. So whenever you want to communicate with a service broker, you need to ensure that you are setting up the right architecture. You are using broker API in order to negotiate. In this video, we'll describe steps that helps to list managed services and plans available from a service broker and provision a new instance of a managed service. Now we need to understand how entire system works. So let's try to understand it using a diagram which is currently displayed on the screen. An objective is to focus on managed services and plans. There are three participants. First is cluster operator, second service catalog API server, and third is service broker. And at the right, you have list of services and plans. Now what happens here is first a cluster operator will create cluster service broker resource, which we can see in the diagram. It will be created within service catalog.k8s.io group. Now, this resource contains the URL and all the connection details required to access a service broker endpoint. Next, once the cluster service broker resource is added to service catalog, it will automatically trigger a call to the external service broker to get list of available services. And that's what we can see where we have an arrow. On top of that arrow, you have list services label. This interaction is between service catalog API server and service broker. Now, once list of services are retrieved, service broker will return a list of all the available managed services as well as list of service plans. So, whenever there is list service request made to a service broker, we'll get services and plans in response, which are cached locally in form of two different resources. First, cluster service class resource. Second, cluster service plan resource. Now, once you have cluster service class resource and cluster service plan resource, when cluster operator will invoke get cluster service classes, it will return cluster service class resources. Now your cluster operator have list of available managed services along with service plans. So this is how you'll be able to retrieve services as well as plans as an cluster operator. Now we'll discuss about provisioning new instance of managed services where actors are similar. You have cluster operator, service catalog API server, and service broker. And you have services which are there at the extreme right of your diagram. Now, cluster operator will place the request for creating service instance. Service catalog API server will create the instance and also initiate a call to external service broker to provision an instance of the service. And that's what we can see on the arrow, which is labeled provision instance. In response to provision instance request, service broker creates a new instance of managed services and it will return an HTTP response. And finally, cluster operator can check the status of the instance to see if it is ready. This is how provisioning of new instance of a managed service happens. Now let's also talk about binding managed service instance. Now once new instance has been provisioned, your cluster operator will like to bind to the managed services to get the connection credentials and service account details in order to ensure that applications are able to use the service. And that's what is done by service binding, for which cluster operator will place a request to retrieve service binding resource. Now, once cluster operator places a request for service binding resource, it will be delegated to service broker and service broker will create an instance of service binding. After the service binding is created, service catalog makes a call to external service broker requesting the information to bind it with the service instance. Service broker in turn enables the application permissions and roles for appropriate service account. And finally, it returns the information that is required to connect and access the managed service instance. This is provider and service specific, so the information returned may be different between service providers and their managed services, so we have to be careful. And finally, we'll talk about mapping connection credentials. Now you are aware about binding. What happens after binding? After binding, the final step involves mapping the connection credentials and service-specific information into the application. Let's try to understand it using a diagram which is currently displayed on the screen. On the left of your diagram, you have app, service catalog, and API server. Request will be placed to service broker. Service broker will return the service. We are assuming that instance has been binded. So in the final step, we need to map the connection credentials and service specific information into the application. These pieces of information are stored in secrets, which are Kubernetes objects, and those secret objects are used by applications. Using those secret objects, your application will be able to access and use to connect directly with the managed services. This is how you can map your connection credentials and make it available to application to invoke direct access to services. So in this course, we have examined how to create and manage different types of Kubernetes services, service account objects, API tokens, and add image pool secret to service account. We did so by exploring the approach of primary modes for finding a service supported by Kubernetes and how to create cluster IP, node port, load balancer, and external name services. How to modify the default service account for a namespace and use secrets as image pool secret. How to use kubectl commands to create, describe, delete, and invalidate API tokens for a service account. The key features of the essential components used to implement automation of service accounts along with the features afforded by service catalog and the architecture that we need to configure to communicate with service brokers. The steps for listing managed services and plans available from a service broker and how to provision a new instance of a managed service. In the next course, we will learn how to work with ingress, ingress controller, path types, and hostname wildcards, CoreDNS, network, and CNI plugins in Kubernetes. In this video, we'll recognize role of ingress to route outside the cluster to services within the cluster and prerequisites required to create and configure ingress. Now, what is role of ingress? Ingress is an API object whose objective is to manage external access to the services in a cluster, typically HTTP. Second role is it exposes HTTP and HTTPS routes from outside the cluster to the service within the cluster. It also facilitates load balancing, SSL termination, as well as virtual hosting. And finally, it helps specify rules that in turn helps to control traffic routings. Now, what all are the essential elements that are used to set up ingress? First is node, which is a worker machine in Kubernetes. Second is cluster, which is collection of nodes that runs containerized applications and are managed by Kubernetes. Third is edge router that enforces the firewall policy for your cluster. This could also be gateway managed by a cloud provider or even a physical piece of hardware. Fourth element is cluster network, which is set of links, logical or physical, that facilitates in order to enable communication within a cluster according to the Kubernetes networking model. And finally, service that identifies a set of pods using label selectors. Now let's take up a scenario of ingress traffic management, and that we will do using a diagram which is currently displayed on the screen. An ingress may be configured to give services externally reachable URLs, load balancing traffic, terminating SSL or TLS, and also offers name-based virtual hosting. Now, whenever there will be request from client, that request will pass through ingress managed load balancer. Ingress will take the request and it will use routing rules in order to delegate it to services which are running on various pods. In short, an ingress controller is responsible for fulfilling the tasks that need to be done by ingress. Now, what all are the prerequisites to create an ingress? First, it must have ingress controller. Second, you must select ingress controller that fits the reference specification. Third, it must have API version, kind, and metadata fields which must be specified in manifest file, which you are using in order to create an ingress. And finally, always give a name that is a valid DNS sub. In this video, we'll list ingress controllers and specify scenarios to choose the ingress controller implementation that is suitable for cluster. Now let's go ahead and list ingress controller with brief description that helps us to select the right controller. And to start with, from the table, we'll pick up the first row, which specifies controller and its description. It starts with AKS application gateway. It enables ingress to AKS cluster using Azure Application Gateway. In short, it is applicable on Azure Kubernetes service. Second is Ambassador API Gateway. It is a gateway that is facilitated with community or commercial support from DataWire. Third is AppCode Inc., which offers support and maintenance for most widely used HA proxy, which is based on ingress controller Voyager. Fourth is AWS ALB ingress controller that enables ingress using specific AWS application load balancer. Then comes HA proxy, one of the frequently used ingress controller. It is customizable community-driven ingress controller for HA proxy. And finally, we have an ingress controller from NGINX Inc. NGINX Inc. provides support and maintenance for NGINX ingress controller for Kubernetes. Now let's go ahead and classify types of ingress. And to start with, first is ingress backed by a single service. There are existing Kubernetes implementations that allows you to expose a single service. You can do that with an ingress by specifying a default backend, but yes, with no rules. Second is simple fan-out ingress. It's a configuration that routes traffic from a single IP address to more than one service. It is based on HTTP URI being requested, and simple fan-out allows to keep the number of load balancers down to a minimum. And third is name-based virtual hosting, which supports routing HTTP traffic to multiple host names which are present at the same IP address. Now let's take up a simple fan-out scenario and understand it using a diagram which is currently displayed on the screen. We know that fan-out configuration routes traffic from a single IP address to more than one service, and that is what the diagram indicates. You will have client who will place the request to ingress controller, and ingress controller will use HTTP URI in order to delegate the service to right pod. For example, in the current diagram, we have /example and /sample as URIs. They will be used in order to invoke services which are running on various pods. Finally, let's go ahead and understand how to implement name-based virtual hosting. For name-based virtual hosting, you need to ensure that you are selecting a controller that supports routing HTTP traffic to multiple host names, not on basis of URI, but on basis of host name which are present on same IP address. So whenever you create an ingress resource without any host defined in the rule, then it will delegate any web traffic to that particular IP. Let's go and understand it using a diagram which is currently displayed on the screen. Client will place the request to ingress controller. Ingress controller will take responsibility of identifying the host and delegating the request to the right service running on pods. So whenever we want to use ingress, we need to identify the right controller, we need to identify the right type of ingress that we want to implement. In this video, first we'll create a simple ingress resource and we'll show what update configuration need to be done in order to use ingress resource backend to ingress data to an object storage backend with static assets. To do that, we have created a file. And that file is present in a directory called C12 in our case. We'll go and we'll open the file where we have defined a simple ingress along with an ingress with backend. To do that, we'll write vi followed by name of the file. After specifying vi space name of the file, we'll press enter. Our first object that we are creating is a simple ingress for which line number 1 and line number 2 are API version and kind. Be careful because API version for ingress is networking.k8s.io/v1. Then comes kind, where we are specifying ingress. Metadata is used in order to give a name to your object, which is simple dash ingress followed by annotations. An annotation that we are using is nginx.ingress.kubernetes.io/rewrite-target followed by a colon slash. And then comes the specification where we are specifying ingress rules. In order to specify ingress rules, we are using HTTP, which is the protocol, followed by paths, where we are giving path as /sample. Path type that we are using is prefix, and backend for now we are using is a service whose name is test ingress service, which should run at port number 80. This is what is a simple ingress. Now assume that we want a resource backend to another Kubernetes resource within the same namespace as the ingress object. To do that, we have created another object where API version is similar to ingress, which is networking.k8s.io/v1, followed by kind, which is ingress, metadata in order to give a name to this ingress, which is ingress-with-backend. Then comes the spec or the specification, which will be updated with default backend. For default backend, we'll specify resource, where we'll be using 3 essential attributes. First is API group, which is k8s.example.com. Then comes kind, which is storage bucket, followed by name, that is static-content. After specifying default backend, we'll specify rules, where again we are using rule to be HTTP. Paths is defined using 3 essential attributes, where first attribute is path, which is /icons, followed by path type, which is implementation specific, and then comes the backend, where we have specified resource, which contains 3 attributes. First is API group, which is k8s.example.com, followed by kind, which is storage bucket, and name that we are giving to the current resource is web-assets. Now let's go ahead and create ingress. To do that, we'll press escape :WQ to save and exit from the current editor. Once we are out of editor, we'll be using command that starts with kubectl, followed by space apply, followed by space -f, followed by space c12_v4.yml. After writing the command, we'll press enter. Once you'll press enter, you'll find that your objects are created. After creating the object, we can view details of these objects by using a command that starts with kubectl, followed by space describe, followed by space ingress, which is the object, and then we'll specify ingress with backend. We'll press enter. Once we'll press enter, we'll get the details, where it gives the name, namespace is default, and you'll find that host is mapped with star, path is /icons, and backends contains attributes like API group, kind, and name. This is how you will be able to create a simple ingress resource and update configuration file to add ingress resource backend to ingress data to an object storage backend with static assets. In this video, we'll list path types and use of hostname wildcards that can be used to create multiple paths within an ingress. Now let's first go ahead and list certain path types. There are 3. First, implementation specific, which works applying rule where matching is up to the ingress class. Second is exact, which matches the URL path exactly as it is, and we need to understand that it is case sensitive. Third is prefix. In this particular case, path type matches based on URL path, prefix split by a slash. Then comes some of the examples of path types that we can evaluate using a table which is currently displayed on the screen. Kind is prefix, path is slash, and request path is all paths. Matches yes. Then comes second, which is exact, /sample. We are using request path as /sample. Matches yes. But when we go with the third one, and if kind is exact, paths is /sample, and you are placing your request path as /example, it will not match. Again, we'll go to the next one where we are using kind as exact, path is /sample, request path that we are specifying is /sample/. It will match? No. Then we'll go to the next one where we have exact, path is /sample/, request path is /sample, it will match? No. Now we'll go with prefix where we are taking /sample as paths and request paths would be /sample, /sample/. Will it match? Yes. Next is prefix, paths that we have specified is /sample/, request path is /sample, /sample/. Will it match? Yes. And finally, we have prefix where paths is specified as /aaa/bb, request path is /aaa/bbb. Will it match? No. So depending on your need, you need to classify the request path on basis of path type. Now, what about hostname wildcard? Objective is to use hostname in order to ensure that you are able to match host precisely. In case of hostname wildcard matches, it requires HTTP header to match the field. And finally, it requires the HTTP header which is equal to suffix of wildcard. In short, you can adopt approach of following hosts where you have to give a precise match, or you can also use wildcards that matches HTTP host header which will be equal to the suffix of the wildcard rule that you have defined. Finally, we'll give some examples of host wildcard. Let's go through the table which is displayed on the screen. We have host where we are using star.sample.com and host header has example.sample.com. What will happen when you go with match? Matches are based on shared suffix. Then comes star.sample.com, but host header has baz.example.sample.com. It's no match because wildcard only covers a single DNS label. Third is star.sample.com, host header is sample.com. Again, it is no match because wildcard will only cover a single DNS label. So you need to ensure that you are able to utilize capabilities of path types and use hostname wildcards in order to generate the right request URL. In this video, we'll demonstrate how to configure the ingress resource to run a web application behind an external HTTPS load balancer. Now, there are different types of load balancing mechanism, and you can use those mechanisms to specify load balancers for HTTPS traffic which operates in OSI layer 3 and 4 and are not aware of HTTP connections or individual HTTP request and response. Now let's go ahead and see how do we configure an internal load balancer using an ingress resource to run a web application behind it. To do that, we need to configure a file. We'll open the file where we have the configuration ready. To do that, we'll write vi followed by space and name of the file which is c12_v6.yml in our case. We'll press enter. Once we'll press enter, we'll get certain entries which starts with kind, and kind now is a service where we are specifying API version to be v1, metadata gives a name that is ingress-nginx followed by namespace which is ingress-nginx. In short, this service will be created in a particular namespace and that namespace is ingress-nginx. Then we are using labels which will be used in order to select the right internal load balancer. We are using app.kubernetes.io/name : ingress-nginx followed by app.kubernetes.io/part-of : ingress-nginx, and then comes annotations where we are using service.beta.kubernetes.io/aws-load-balancer-proxy-protocol which we are specifying as star within double quotes. Then comes what would be the connection idle timeout for the load balancer, and that we are specifying using another annotation which is service.beta.kubernetes.io/aws-load-balancer-connection-idle-timeout, and we are setting up to 60 which will be in seconds. And finally, we have to specify an entry that makes a service which uses external load balancer, and to do that we will set service.beta.kubernetes.io/aws-load-balancer-internal to false. Once you set to false, it means it's an external load balancer. Then comes type, which is load balancer. Selector that we are using is the same labels that we have specified earlier. And those selectors are app.kubernetes.io/name. Value is ingress/nginx. Second selector that we are using is app.kubernetes.io/part-off and value is ingress-nginx. And then comes the ports. We are using HTTP. Port is 80. Target port is HTTP. And the port that we are configuring for the current video is HTTPS. Port is 443 and target port is HTTPS. We'll save the file and we'll exit. To do that, we'll press escape followed by :WQ and we'll press enter. Now we have configured a file that will configure ingress resource to run a web application behind an external HTTPS load balancer. To create the object, we'll write kubectl followed by space apply followed by space -f followed by space name of the file, which is c12_v6.yaml. You need to ensure that you have specified the right namespace entry in your configuration file. After writing the command, we'll press enter. Once you'll press enter, it will create the required object. This is how you can configure ingress resource to run a web application behind an external HTTPS load balancer. In this video, we'll describe features of CoreDNS and list plugins that can be configured in core file configuration. Now let's go and first identify critical features of CoreDNS. CoreDNS is a DNS server. It manages DNS. It is written using Go language and it can be used in a multitude of environments because of its flexibility. And finally, CoreDNS supports rich plugins. Now let's go through two essential features which encourages Kubernetes administrators to adopt CoreDNS, and they are: it is fast and flexible. Apart from that, it facilitates service discovery. Now we know why to adopt CoreDNS. Let's go through and understand CoreDNS mechanism. It all starts with a DNS query. You will send DNS query which will align to a particular port that will be sent to server DNS, which will create a file. In the second case, as it is depicted in the diagram, we have DNS query, we have server DNS, and we have multiple different components. Apart from files, it has logs, errors, cache, Kubernetes proxy, log files, and errors. So these are two different types of queries which can be made in CoreDNS in order to query for specific objects. Now, in order to make CoreDNS more powerful, there are various different plugins. Let's go through a list of plugins which is currently displayed in a table on the screen. First plugin is ACL. What does ACL do? It enforces access control policies on source IP. Apart from that, it also prevents any unauthorized access that is made to DNS server. Second is any, which provides minimal response to any queries. Third is autopath. This particular plugin allows for server-side search path completion. In order to facilitate integration with Azure, you have a plugin called as Azure, which enables serving zone data from Microsoft Azure DNS service. And finally, you have bind plugin, which overrides the host to which the server should be binded. Now let's go and try to understand how do we implement CoreDNS in Kubernetes. And in order to do that, we'll be using a diagram which is currently displayed on the screen. On the screen, we can see various different components. Let's start from the left. You will have nginx.k8s.local. Using a terminal and nginx.k8s.local will set the DNS to use CoreDNS, and that's what is configured in nginx.k8s.local. Now, apart from setting DNS to use CoreDNS, your CoreDNS will get resource records from etcd cluster, which is mounted over a particular persistent volume, which is running on NFS server. Then comes the second path, where Request will be made to ingress controller. Ingress controller has a component called as default backend, which will take the request and it will proxy it to internal service resource, which in current case is NGINX. And from NGINX, it will make the services available which are running on pod powered by ingress. Now, what about external DNS? etcd cluster will record the resource which is generated from external DNS. And then your external DNS will also facilitate to sync ingress to a service which is present in Kubernetes cluster powered by Kubernetes API server. So we can clearly understand that you have two roles. First, to serve ingress in order to discover the service, and second is the service itself to which access will be provided once DNS resolution is done. So this is how you will be able to come up with an architecture that helps you to implement CoreDNS in Kubernetes. In this video, we'll compare CoreDNS and CubeDNS. That helps us to identify best cluster DNS service for Kubernetes cluster implementation. And before we go and compare, let's go through Kubernetes DNS service evolution. It all started with 1.0 in 2015 when DNS that was used was SkyDNS. It was in use till version 1.5. Then came version 1.6 from where CubeDNS evolved. CubeDNS was heavily used till version 1.8. From 1.9 to 1.15, it was a choice that you can make between CubeDNS and CoreDNS. It means starting with Kubernetes 1.11, CoreDNS can be used as a DNS plugin for Kubernetes to enter the GA state. But yes, we need to understand what is recommendation of Kubernetes. Kubernetes recommends using CoreDNS as a DNS service because CoreDNS is flexible and extensible plugin mechanism with various plugin implementations with diversified functions. Now let's try to explore CoreDNS and CubeDNS by comparing them. CoreDNS uses single container per instance. CoreDNS is multi-threaded and it is written using Go language. And finally, CoreDNS enables negative caching in the default deployment. Whereas when you go with CubeDNS uses 3 containers per instance. Apart from that, CubeDNS uses DNS MASQ for caching and is single-threaded written in C. And finally, CubeDNS does not enable negative caching in the default deployment. With this comparison, we'll go and we'll have a technical comparison between CoreDNS versus CubeDNS from perspective of DNS server query type, QPS, and average latency. CoreDNS query type is external. If it is external, QPS will be 6733 and average latency is 12.02. When you go with CoreDNS internal, QPS is 33,669 and average latency is 2.608. CubeDNS, when you use external, your query per second, which is QPS, will be 2227, whereas average latency will be 41.585 milliseconds. And finally, when you are using CubeDNS and if query type is internal, QPS will be 36,648. Average latency will be 2.639. After seeing the comparison, you can create a benchmark and test in your environment to track QPS and average latency and then decide. Finally, let's try to understand CubeDNS using a scenario. Now, in Kubernetes, service discovery is implemented with auto-generated service names that will map to the service IP address. And we know that service names will follow a standard specification. Now, our objective is to ensure that pods can also access external service. For example, it can be sample.com or example.com. So, we want pods also to access external services using their names. And there comes role of DNS that helps to resolve service names as well as external names. In the current scenario, which we are trying to discuss using a diagram, we are implementing CubeDNS, which is a cluster add-on that is deployed by default on various Kubernetes engine, for example, GKE. We are taking GKE clusters, so we need to understand that GKE uses CubeDNS by default. And responsibility of CubeDNS in the current case, as it is indicated in the diagram, is to run as a deployment that schedules redundant DNS pods. We can see in the diagram we have 2 worker nodes, and on each worker node you have a pod, and those pods are redundant. CubeDNS pods, which we can see in the diagram, are present in Kube system namespace. Now, what is special about CubeDNS? CubeDNS provides capability to scale to serve the DNS demands of the cluster, and this is controlled by a component called as CubeDNS autoscaler, which is deployed by default in certain clusters. So whenever there is request, CubeDNS autoscaler takes responsibility of ensuring that it is scaling up the DNS to meet the demand from the cluster. All the requests will be delegated to CubeDNS SVC, which is a service that runs CubeDNS. And finally, since we are using GKE cluster, we can use Cloud DNS to configure. This is how you'll be able to identify capabilities of DNS and implement the right DNS that meets your case. In this video, we'll demonstrate steps to install CoreDNS using kubeadm as default DNS service while installing a fresh Kubernetes cluster. Kubernetes 1.9 has been launched along with CoreDNS being part of it. We can install CoreDNS as the default service discovery using kubeadm, which is a tool that can be used in order to install Kubernetes easily in a single step. As per Kubernetes roadmap, it is going to make CoreDNS beta in version 1.10 and eventually will be the default DNS that will replace kubeDNS. Now let's go ahead and see how to install. To install, we have created a file called config.yml. Let's open the file and see the entries that we have made in the file. We'll write vi followed by space config.yml. We'll press enter. After pressing enter, we'll specify API version, which will be kubeadm.k8s.io/v1alpha3. Then comes kind, which is init configuration, followed by node registration. We are using kubelet extra arguments. By specifying kubelet extra args, we are taking v to be 2. Feature gates will be CoreDNS equal to true. This will ensure that your Kubernetes, when it gets installed, it uses CoreDNS as the default DNS discovery service. We are also creating one cluster configuration. To do that, we have specified triple dash to separate the configuration. We are writing API version followed by kubeadm.k8s.io/v1alpha3, followed by kind, which is cluster configuration, and then we are specifying networking that we need, where we are giving pod subnet to use 193.168.0.0 as the base IP, followed by 16 as CIDR. After writing the configuration file, we'll save and exit. To do that, we'll press escape followed by :WQ and we'll press enter. Now we are ready with the configuration file. We have to now install CoreDNS instead of kubeDNS. To do that, we'll specify kubeadm followed by space, followed by init, followed by space --v equal to 1, followed by space, followed by ignore preflight errors equal to swap, followed by space, followed by config equal to config.yml. After writing the command, we'll press enter and you'll find that you have installed a fresh Kubernetes cluster where CoreDNS is the default. This is how you'll be able to install CoreDNS using kubeadm as default DNS service while installing a fresh Kubernetes cluster. In this video, we'll demonstrate steps to upgrade DNS service of an existing Kubernetes cluster to CoreDNS, replacing kube-DNS using kubeadm upgrade command. It's one of the simple labs that we are going to do. Sometimes on an existing cluster, you would like to upgrade your DNS service to CoreDNS with the objective of replacing kube-DNS. Why do we replace? We replace because CoreDNS provides a single container per instance, but when it comes to kube-DNS, it gives 3. kubeDNS internally uses DNS mask queue for caching, which is single-threaded, whereas CoreDNS is multi-threaded Go. And finally, we can say CoreDNS enables negative caching in the default deployment, whereas CubeDNS will not provide support to that. So after understanding difference between CoreDNS and CubeDNS, now our plan is to upgrade existing CubeDNS to CoreDNS. To do that, we'll launch Kubernetes cluster, and at master, we'll write kubeadium followed by space upgrade, followed by space plan, followed by space dash dash feature dash gates, followed by space, we'll set CoreDNS equal to true. After writing the command, we'll press enter. Once we'll press enter, it will start the upgrade path. It will take some time for upgrade to happen. You need to wait for upgrade to get completed, and once it is upgraded, you'll start getting features of CoreDNS rather than CubeDNS. This is how you can upgrade DNS service of an existing Kubernetes cluster to CoreDNS. In this video, we'll list and describe features of network plugins in Kubernetes that can be used to configure and clean up pod networking. Managing networks in Kubernetes is one of the challenges. You have to ensure that you have configured it properly to enable container-to-container, pod-to-pod, as well as node-to-node networks. There are various different network plugins that helps us to simplify the task. Let's go and list some of them. First is plain EXEC plugin. This is deprecated because now you have CNI plugins available. Second is CNI plugins that follows CNI specification. An objective of CNI plugin is to enable interoperability, and that's how they are designed. And the third plugin is KubeNet plugin that implements basic CBR0 using the bridge and host local CNI plugins. Now let's try to understand structure of container network interface. Container network interface is a container networking specification which was proposed by CoreOS and was adopted by projects like Cloud Foundry, Kubernetes, RKT, and others. There are also various plugins created by projects like Contiv Networking, Project Calico, and Weave. Now, what was the objective of CNI? CNI was created as a minimal specification which was built alongside a number of network vendor engineers to be able to build a simple contract between container runtime and network plugins. As the diagram indicates, you will have container runtime powered by container network interface, which contains multiple different types of plugins, which runs at one time with a container joining network driven by different plugins. There are certain plugins which we can see in the diagram. First is Loopback plugin, followed by Bridge plugin, PTP plugin, Mac VLAN plugin, IP VLAN plugin, and third-party plugin. Next is CNI in Kubernetes. In CNI architecture, focus is on providing orchestration capabilities to Kubernetes by empowering orchestrator to add or delete CNI plugins using CNI libraries. And that's what is being displayed using a diagram on the screen. You have orchestrator, which is powered by CNI library, which facilitates add or delete of CNI plugins. For example, your current CNI plugin has capability of NetNS container that provides interface and route capabilities. Then you have rootNS/host, which provides you interface, route, bridge, as well as IP tables. And finally, you have NetNS/container, which again facilitates you with interface and routes. And finally, let's talk about Kubelet plugin. Now, when we talk about Kubelet plugin, we need to consider nodes. You have nodes on which you have pods. There are multiple pods which are running. We can see a scenario where we need to consider a case where pod CIDR for first node is specified as 160.10.1.0/25. And for node 2, in the same diagram at the right, we can see pod CIDR is 160.10.2.0/25. In both cases, cluster CIDR will allocate the required IPs for kubelet nodes. For example, in the current case, we can assume an IP of 160.10.1.0 And in node 2, we can assume that IP is 160.10.2.0. Now we need to know one important thing here, and that is CIDRs are different from the actual physical network where Kubernetes master and workers are running. And that's where comes role of kubelet plugin. Kubelet plugin facilitates allocation by using enabling or disabling of CIDR flag and the algorithms for splitting the CIDR into chunks that can be also configured. So we need to focus on the right plugin which we have to use in our cluster to facilitate pod networking. In this video, we'll list features of various CNI for Kubernetes that can be used to build Kubernetes networking model. Deriving right Kubernetes model is essential. And to do that, we need to follow certain Kubernetes rules for networking, where first rule is all containers can communicate with all other containers without NAT, or we can say network address translation. Second, all nodes can communicate with all containers and vice versa without again using NAT. And third is the IP that a container sees itself is the same IP the other sees it as. Now we are aware about Kubernetes rules for networking. Let's go and list CNI plugins that can be used for implementation. First is Flannel, second is Calico, and third is Weave. Now, what are the features afforded by Flannel? First, it is one of the most popular plugins. Second feature is it provides VXLAN tunneling solution, which is handy when you build communication. Third feature is configuration and management are very simple. Fourth, it does not support network policies, so you need to be careful when you are adopting Flannel. And finally, it provides tunnelless solution through the host-GW mode. Now, Calico. It's default choice of most of the Kubernetes platforms. It supports IP to IP encapsulation if BGP cannot be used. Third, it uses BGP and Bird, which is a daemon called Felix, which configures routes on Bird. And finally, you will get support to network policies. There are two other features which we need to discuss about Calico. First, it uses IP tables for routing, but it can be configured to even use kubeproxy's IPVS mode. And finally, to manage Calico, we have a CLI tool called Calico CTL. Now let's try to list certain features of Weave. First important feature is it provides VXLAN tunneling solution. We need to also understand that all the nodes are connected as mesh that allows to run on partially connected network, and this is what is one of the special features of Weave. Third, it does not scale well because of mesh structure. And fourth feature of Weave is it stores configuration files on pods instead of Kubernetes CRDs or etcd. And finally, let's close by discussing three essential features of Weave that makes it an outstanding choice of networking. And those features are it has encryption library, supports network policies, and similar to Calico, it also comes with a CLI tool called as Weave. So before you go and derive Kubernetes networking model, you need to evaluate features of CNI and select the right CNI. In this video, we'll demonstrate steps to configure and enforce network policies in Google Kubernetes Engine. Now, what is objective of setting up network policies? Objective is to control traffic flow at the IP address or port level, typically in OSI layer 3 or 4. Then you might consider using Kubernetes network policies for particular applications which are deployed in your cluster. In short, network policies are application-centric constructs whose responsibility is to allow you to specify how a pod is allowed to communicate with various other network components like endpoints and services which have specific Kubernetes usage over the network. Now, how do we use it on Google Kubernetes Engine, which is deployed on Google Cloud Platform? To do that, we need to log into our Google Cloud. To log in, we'll write https console.cloud.google.com. Once we'll press enter, it may ask us our authentication details, will specify, and it will launch the landing page of Google Cloud Platform. We need to go to top panel, and in the search text field, we'll write Kubernetes. Once you will write few letters of Kubernetes, you will get Kubernetes engine as one of the options. We need to click on it. Once you will click on it, it will launch Kubernetes engine and it will display list of all the clusters which are part of current Google Cloud Platform. We have already configured one cluster, that is cluster 1, which we can see in the content pane. We need to click on it to select the cluster. After selecting the cluster, it will show details of the current cluster where you will have storage and you will have nodes. We'll be back to details and we'll click on edit button, which is indicated with the pencil icon on the top panel of your content pane. Once you'll click on it, it will show you various different options that can be changed. We will scroll down and we will locate network policy for master. It's a drop down. We'll click on it and select enable. After selecting enable, we'll scroll down and we'll click on save button, which is there on the content pane. Once you'll click on save, it will apply the required changes where network policy for node has been now enabled. Now, once it is enabled, you can also disable network policy whenever you want, following the same steps and changing the network policy for nodes to disabled. This is how you will be able to configure Google Kubernetes engine with network policy. Once you have configured, you can define the actual network policy using Kubernetes Network Policy API. So in this course, we have examined how to work with ingress controllers, path types, and hostname wildcards, CoreDNS, network, and CNI plugins in Kubernetes. We did so by exploring the role of ingress in enabling routing outside the cluster to the services, the prerequisites for creating and configuring ingress and the prominent ingress controllers for Kubernetes, the prominent path types, and the use of hostname wildcards for creating multiple paths within an ingress, the features of CoreDNS and CubeDNS, how to install CoreDNS as the default service while installing a fresh Kubernetes cluster, and upgrade the DNS service of existing Kubernetes cluster to CoreDNS, the feature of prominent network plugins that we can use to configure and clean up pod networking, and how to configure and enforce network policies in Google Kubernetes engine, the features of prominent CNI plugins for Kubernetes that we can use to build Kubernetes networking model. In the next course, we'll explore the concept, features, and work with storage class, Kubernetes volume, persistent volume, and persistent volume claim in Kubernetes. In this video, we'll describe the use of storage class in Kubernetes that helps to classify storage types and list the fields that are used to dynamically provision persistent volume of a class. Now, what is a storage class? Storage class helps administrators to describe classes of storage they intend to offer. Apart from that, storage class also maps to quality of service levels which are defined by administrators. In certain cases, storage class are also called profiles in various different storage system implementations. Now let's try to list essential fields of storage class. There are 3 important fields that we need to focus on. First is provisioner. Each storage class will have a provisioner whose objective will be to determine what volume plugin need to be used for provisioning persistent volumes. This is a mandatory field that must be specified. Second is parameters. Storage classes will have various different parameters which will describe volumes that belongs to a particular storage class. Different parameters may be accepted depending on who is the provisioner. And third field is reclaim policy. You will have persistent volumes that are dynamically created by storage class. Now, if they are dynamically created by storage class, they must have a reclaim policy specified in the reclaim policy field of the class. reclaim policy field of the class can have delete, retain, or recycle. Now let's try to understand how do we configure storage class in Kubernetes. To do that, we need to write a manifest file. Manifest file will have following entries. First entry will be API version, which must be storage.k8s.io/v1. You need to be careful when you specify API version because different objects in Kubernetes may have different API versions. Then comes kind. We have to specify storage class. Followed by metadata in order to give a name to the storage class. In the current configuration, it is storage1. Then comes essential parameter called as provisioner. We have specified kubernetes.io/aws-ebs as the provisioner. Then comes parameters type because you will have provisioners provide you storage class of different types. We are specifying type for now to be GP2. Then comes reclaim policy, which in current case is retain, followed by an essential attribute called allow volume expansion, which is set to true. Followed by mount option, we have specified debug, and finally volume binding mode, which is immediate. This is how an administrator can go and create a storage class. Let's quickly list features of storage class parameters. And first feature is maximum limit of parameter for a storage class would be 512. Length must not exceed 256 KB. And key parameters that need to be kept in mind are type, zone, IOPS per GB, FS type, encrypted, and KMS key ID. So when you plan persistence, you need to decide storage class where you have to identify the right provisioner and apply right reclaim policy. In this video, we'll use kubectl command to list storage class and various types of volumes. We know that a storage class typically provides an approach to administrators so that they are able to describe the classes of storage they offer. Now you'll have different classes that are mapped with different level of quality of services. You can also use storage class binded with backup policies. Kubernetes itself is unopinionated about what class represents. Similarly, when we talk about volume, we can compare it with a directory. We can say that it's a directory that is accessible to all the containers which are running in a particular pod. Yes, it is different from container local file system because the data in volumes is preserved across container restarts. Now let's go ahead and use kubectl command to list what all storage classes are there as of now in your cluster and also volumes which are present. To do that, we'll write the command that starts with kubectl followed by space get followed by space storage class and we'll press enter. Once you'll press enter, it will show you that what all storage classes are there. As of now, we have one storage class called sample storage, which is provisioned by using provisioner, which is identified by kubernetes.io/aws-ebs. Reclaim policy is retain and volume binding mode is immediate. Apart from that, does it allows volume expansion? It is showing value called true. And what is the age of the current storage class? It is 10M. After looking at storage class, we would like to see the volumes as well. To do that, we'll write kubectl at the prompt followed by space get followed by space pv and we'll press enter. Once you'll press enter, it will show you what all persistent volumes are there which are currently created in your cluster. Now let's go ahead and write kubectl followed by space describe followed by space and we'll specify storage class followed by space followed by the name of the storage class which is sample storage. We'll press enter. Once you'll press enter, it will show you the detail of your current storage class. Similarly, you can use describe command by just changing storage class in your previous command to pv followed by name of the pv, which in our case is task-pv-volume. We'll press enter. Once you'll press enter, it will give you detail of the specific volume that you want to look at. This is how you'll be able to use kubectl commands to list storage class and various type of volumes. Objective of this video is to demonstrate use of kubectl command to copy local file to pod and transfer pod file to local. Let's first go ahead and connect to our cluster and ensure that we have pods which are going to be source or destination for copy commands. To do that, we'll go to the prompt and we'll write kubectl followed by space get followed by space pods. After writing the command, we'll press enter. Once you'll press enter, you'll get all the pods which are currently present in your cluster. We will be selecting copy demo in order to demonstrate how we can copy from local file system to pod and from pod back to local file system. To do that, we'll first clear the screen. After clearing the screen, let's create a file. To create a file, we'll write vi followed by space followed by sample.txt and we'll press enter. We'll go and we'll enter some data to it. After entering data, we'll save and we'll exit. To do that, we'll press escape followed by $WQ and we'll press enter. Now we have a local file which we want to transfer to a specific pod and we have selected copy-demo as our pod name. In order to copy from local file system, we'll be using a command that starts with kubectl followd by space cp space the path of the file that we want to copy, and to do that we'll write /root/c13/name of the file. After writing name of the file, we'll specify name of the pod where we want to copy is copy-demo followed by colon and the destination where you want to copy. We'll specify destination as /usr/share/nginx/html. After writing the command, we'll press enter. Once you'll press enter, you'll find that you come to next command prompt without any error. And this indicates that you have copied your file from local file system to pod. After copying the file, let's try to verify that the container is running of the pod. And to do that, we'll write kubectl followed by space get followed by space pod followed by space name of the pod, which is copy-demo. We'll press enter. Once you'll press enter, you'll find that you have it running. Now let's get a shell to the running container. We'll clear the screen and we'll connect to the pod where we have copied the file. To do that, we'll write kubectl followed by space exec followed by space /stdin followed by space /tty followed by space copy-demo, which is the name, followed by space -- followed by space /bin/bash. After writing the command, we'll press enter. Once we'll press enter, we'll get into the pod. We'll see that node on which this pod is running is IP-172-31-55-34. We'll move to the directory where we have copied our sample file. To do that, we'll write cd/usr/share/nginx/html and we'll press enter. After pressing enter and once we are there in HTML directory, we'll write ls. Once you'll write ls, you'll find that you'll have your sample.txt copied from your local file system to your pod. We'll clear the screen. In order to copy from a pod to local file system, we'll be using a command called kubectl followed by space cp followed by space copy-demo, which is name of the pod, followed by colon, followed by usr/share/nginx/html/sample.txt. You need to ensure that you are specifying the right path, followed by a space followed by path on your local system. We are specifying /root/test.txt. After writing the command, we'll press enter. You'll find that you come to a new prompt. Now let's go ahead to root by writing cd ... press enter. You'll write ls in order to list the content of root. We'll press enter. And you'll find that it has been copied to your local file system at the destination which you have specified in kubectl cp command. This is how you can use kubectl command to copy local file to pod and transfer pod file to local. In this video, we'll recognize the features of Kubernetes volume and list the different types of volumes supported by Kubernetes. So let's try to recognize essential features of Kubernetes persistent volume by using storage activity and Kubernetes storage primitive. We'll start with provisioning, which is one of the storage activities. Kubernetes storage primitive for provisioning is persistent volume. Then comes configuration, which depends on storage class Kubernetes storage primitive. And third is attaching, which depends on persistent volume claim. In short, your persistent volume must be attached with persistent volume claim before it is configured to be used in a pod. Then comes the features of persistent volume. First feature that we need to understand here is we can provision it dynamically or can also be provisioned manually by an administrator. Second is it should be created with a particular file system. So you need to ensure that you are specifying the file system. Third, it must have a particular size. And finally, persistent volume has identifying characteristics like volume IDs and names that can be referred in order to be binded to a particular Kubernetes object. Now we'll try to understand using a scenario how pod and persistent volume work together. We are having two participants as it is displayed in the diagram currently present on the screen. You have developer. Developer will claim a persistent volume. In response to that particular persistent volume claim, it will be bounded with a persistent volume that is created by administrator. So depending on what persistent volume claim is bounded with what persistent volume, developers will be able to use persistent volume claim by specifying it in pod specification. This is how pod and persistent volume work together. Then comes types of volumes. There are multiple different types of volumes that can be used. Let's list some of them. First is AWS Elastic Block, which is a volume that mounts an AWS EBS volume into your pod. You can differentiate it with empty dir, which is erased when a pod is removed. Now, content of EBS volume are persisted and the volume is unmounted. It means that EBS volume can be pre-populated with data and the data can also be shared between multiple different pods. Then comes Azure Disk. It's a volume type that mounts a Microsoft Azure data disk into a pod. Third is Azure File that mounts a Microsoft Azure File volume into a pod. And then we have ChefFS, which is a volume that allows an existing ChefFS volume to be mounted in your pod. In all these cases, you'll be able to retain and preserve the volume which can be used by other pods. Now let's go and list two other popular types of volumes. First is Cinder. Cinder is a specific volume type that is used to mount the OpenStack provided Cinder volume into your pod. And then comes config map. It's a critical way to inject configuration data into pods. Data stored in config map can be referenced by using config map ref in a volume of type config map. Once it is referenced, it can be consumed by containerized applications that are running in pod. As an administrator and as a developer, you need to know what all are the Kubernetes storage primitive and what is relation between pod, persistent volume claim, and persistent. Now, in this video, we'll list the types of volumes that supports volume expansion along with the volume binding modes of storage class that are used to control volume binding and dynamic provisioning of instances. Before we start discussing more about binding, let's try to understand how to use a volume. To use a volume, you need to write a configuration file. Assuming that you are writing a configuration file to create a pod, you need to focus on a specific block that is spec. In spec, you will have containers where you will give a name to the container. You will specify the image that will be used in order to run that container using that particular image. Then comes essential elements. First is volume mounts, where you are specifying mount path. You are giving a name to volume mount. Followed by ports, where you have specified container port :8080. And then comes volumes, where you are giving a name, data-volume, and you have selected volume type of empty dir. When you specify empty dir, it indicates that volume will not be accessible to other pods. And as lifecycle of that pod is over, your volume will also be lost. You can select various other different volume types if you want persistence. Keeping that in mind, let's classify volume types. We have two different types of volumes. First is ephemeral, where volumes are tightly coupled with the pod's lifetime. Example, empty dir volume, which we have seen in the previous slide. They are the volumes which are deleted if the pod is removed. It can be any reason. So you will have data loss scenarios. Second is persistent. These are the volumes which are meant for long-term storage and they are not bounded to a particular pod or node lifecycle. It can be an NFS or it can also be cloud-based storage. In case of managed Kubernetes offerings, for example, it can be storage provided by AWS, GCP, or Kubernetes. Now let's try to understand different modes of volume binding. There are two different modes. First, immediate, which is the default adopted by Kubernetes. In immediate mode, we'll have volume binding and dynamic provisioning occurs once the persistent volume claim is created. It means as soon as you will create persistent volume claim, binding will occur. Now for storage backends, where you will have topology constrained and are not accessible globally from all nodes in the cluster, volumes will be bound or provisioned without any knowledge of the pod's scheduling requirements. Second is wait for first consumer. As a cluster administrator, sometimes you will like to use wait for first consumer mode, which will delay the binding and provisioning of a persistent volume until a pod using persistent volume claim is created. Now, persistent volume will be selected or provisioned conforming to the topology that is specified by the pod's scheduling constraints. So, depending on your need as an administrator, you can decide what type of volume binding mode you'll prefer. Now, let's try to understand volume binding approach. Now, when cluster users needs to use persistence, they will focus on using persistent storage in their pods. What they will do? Step 1 will be to set up some kind of storage. It can be NFS storage as well, and that is done by administrator as it is displayed in the diagram currently present on the screen. We are able to see NFS export, which is used in order to set up network storage. Now, once network storage is set up, admin will create persistent volume, which is considered as step 2, and it is done by writing a descriptor file and using kubectl API or kubectl command in order to create persistent volume. Now, once persistent volume is created, it will be in a state where it is not bounded. It means it can be binded. Now, when binding happens, that happens when user creates a PVC, that is persistent volume claim. Once a user creates a persistent volume claim, Kubernetes will find a PV of adequate size and access mode and then bind the persistent volume claim to the right PV or to the right persistent volume. And finally, once it is binded, user creates a pod with the volume, but instead of directly referring to persistent volume, they will refer to persistent volume claim. This is how, when you want to manage persistence in your pods, you have to decide how you are going to create volume and what type of volume binding mode you are going to select, and also find out appropriate storage class that you would like. In this video, we'll create a configuration file that creates a pod with one container and configures a volume for that particular pod. To do that, we need to write a configuration file. In order to write configuration file, we'll be using a command called vi, followed by space, followed by name of the file. We'll press enter. After opening the file, we need to make required entries in YML file, where first two lines are specifying what is the API version and what is the kind. Kind is pod, API version is v1. After kind, we are giving a name to our pod that we are going to create, and it is specified under metadata using a property called name. Name is pod with volume. Then comes spec, where we are specifying volumes. We are giving a name to the volume. which is shared-data-volume, and we are specifying empty dir to be empty by specifying opening and closing curly braces. And then comes the containers. We know that containers file system lives only as long as container does. So whenever container will terminate and restart, file system changes are lost. We want to retain those changes. In order to retain those changes, we need to define a storage that is independent of container. And there comes role of volume. It is important when you are using stateful applications where you need key value kind of storage as well as database. Now let's go ahead and explore the lines which will help us to bind a particular volume to the container. To do that, we are using containers. Below containers, we are giving a name to the container, that is container with volume. We are specifying image to be nginx, and then comes the most important part, which is volume mounts. For volume mounts, we are giving a name. We are specifying mount path, which is /usr/share/nginx/html. It depends on your container. You can specify whatever mount path you want. Finally, we are specifying host network to be true and DNS policy to be default. These configuration statements will help us to create a pod with a container and configure volume for that particular pod. Let's go and save it. To save it, we'll write escape followed by :wq. We'll press enter to exit from the editor. Now let's go ahead and use kubectl apply command. To do that, we'll write kubectl followed by space apply followed by space -f followed by space name of the file, which is c13_v7.yml file. After writing the command, we'll press enter. Once you'll press enter, you'll find that it shows you a message indicating that pod with volume is created. Now let's go ahead and verify pod's container is running. To do that, we'll write kubectl followed by space get followed by space pod followed by space name of the pod, which is pod with volume, followed by space, we'll specify --watch, and we'll press enter. Now you'll find the output where we have name, ready, status, restart, and age. You can connect with another terminal and get a shell to the running container, and finally verify by creating a file at the mount. This is how you'll be able to create a configuration file that creates a pod with one container and configures a volume for the pod. In this video, we'll create a configuration file to create a host path persistent volume that can use a file or a directory on the node to emulate network attached storage. Now, host path volume is a specific volume that mounts a file or a directory from your host node file system into your pod. Now let's try to understand it using a scenario. For example, you want to allow a pod to specify whether a given host path should exist prior to the pod running, whether it should be created, and what it should exist as. In order to ensure that you are able to specify whether a given host path should exist prior to pod running or not, you need to create host path volume that should mount a file or directory from your host node file system. Now ensure that when you are creating this kind of volume, you have pods with identical configuration and files or directory created on the underlying hosts are only writable by root. That you can do by changing the privileges. Let's go ahead and create a directory. To do that, we'll write mkdir followed by space /root followed by /data, and we'll press enter. You'll find that directory is created. Once directory is created, now you have to go and you have to write a configuration file. To write a configuration file, we'll use vi followed by space followed by name of the file, which in our case is c13_v8.yml. After writing the command, we'll press enter to launch the editor. Once editor will launch, you need to go ahead and you need to use API version and kind to specify what you want to create and what would be the API version. We have selected v1 and pod. Then you have to give a name to the pod. We are doing that by specifying host path sample as value to name attribute of metadata. And then comes the spec, where we are defining specification of containers. We are using image. You can point to any image of your choice. We are using k8s.gcr.io/test-web server. Then we are giving it a name. Name of container is host path dash container, and then comes the volume mounts. We are specifying certain attribute to configure volume mounts. First attribute is mount path, which is /test-pv. Second is the name itself, which is hp-volume. After specifying the volume mounts, we have to specify volumes. And that we are doing by giving it a name, that is hp-volume, followed by host path, where we have to specify directory location on the host, which is /root/data, which we created in earlier step. And then finally we are specifying type is directory. After writing the configuration file, we'll save and exit. To do that, we'll press escape followed by :wq and enter. Now we are ready with our configuration file. Let's go ahead and use kubectl apply command in order to create the artifacts which are specified in configuration file. We'll write kubectl followed by space apply followed by space -f followed by space name of the file, which is c13_va.yml. We'll press enter. Once you'll press enter, you'll find that it has created host path sample. This is how you can create a configuration file to create a host path persistent volume that can use a file or directory on the node to emulate network attached storage. In this video, we'll create a configuration file that creates a persistent volume claim that requests a volume of at least 4 GB and can provide read-write access for at least one node. Now let's go ahead and first see persistent volume that is already created. To do that, we'll write kubectl followed by space followed by get followed by space pv. After writing the command, we'll press enter. You'll have an output which displays number of persistent volumes and status of availability. Once you see status is available, it indicates that it has not yet been bound to a persistent volume claim. Now let's go ahead and write a configuration file to create persistent volume claim. What you need to do is you need to capture the class which is sample storage, which is being used by the current persistent volume. Now we'll go and we'll write a configuration that will claim at least 4 GB and will provide read-write access for at least one node. To do that, we'll write a configuration file. To write a configuration file, we'll specify vi followed by space name of the file. After specifying name of the file, we'll press enter. It will launch the editor and you need to go ahead and write certain lines of configuration. Where first two lines will specify API version and kind. Kind that we are specifying is persistent volume claim. Then we are giving a name by using metadata and populating name attribute of metadata with test-pv-claim. Then comes the spec. You need to be careful when you are specifying storage class name, because your control plane will find a suitable persistent volume with the same storage class. It binds the claim to the volume. So we need to be careful when we are specifying storage class. Access modes, we are specifying read-write once in order to ensure that it is accessible from at least one node for read-write access. And finally, we are specifying resources where we are specifying requests and storage limit to be 4 GB that can provide read-write access to the node. After writing the file, we'll save and exit. To save and exit, we'll press escape followed by :wq and press enter key. Now you are out of editor. Let's go ahead and execute kubectl space apply followed by space -f space followed by name of the file. Name of the file is c13_v9.yml. We'll press enter. Once you'll press enter, you'll find that persistent volume claim is created with the name test-pv-claim. Now let's go ahead and look at the persistent volume once again. To do that, we'll write kubectl followed by space get followed by space pv followed by space followed by sample-pv-volume. This is name of the persistent volume. We'll press enter. Once you'll press enter, you'll find status to be bound. It means now it is not available. It is bounded to a particular persistent volume claim. Let's go ahead and visualize persistent volume claim. To do that, we'll write kubectl followed by space followed by get followed by space, followed by PVC, which is persistent volume claim, followed by space, name of the persistent volume claim, which is test-pv-claim. Will press enter. Once you'll press enter, you will get the detail where it shows that your current test-pv-claim is bounded with volume named sample-pv-volume. This is how you can create a configuration file which will create persistent volume claim that requests a volume of at least 4 GB and can provide read-write access for at least one node. In this video, we'll create a manifest file and configure it to create a pod configured to use persistent volume claim as a volume. In order to do that, let's go ahead and first list persistent volume claims. And we'll be using persistent volume claims which we created in video titled Create a Persistent Volume Claim. To get all the persistent volume claims, we'll be writing command that starts with kubectl, followed by space get, followed by space pvc, which is persistent volume claim, and we'll press enter. Once we'll press enter, it will list all the volume claims that we have created. We have created test-pv-claim in the video titled Create a Persistent Volume Claim. Once we are aware about persistent volume claim, we'll go and we'll create a configuration file to create a pod that uses test-pv-claim. To do that, we'll clear the screen. We'll open a file by writing vi followed by space name of the file. After writing name of the file, we'll press enter. Now we have to go and we have to provide specification in order to create a pod that uses the selected persistent volume claim. To do that, first two lines will be API version and kind, that will specify the version of API, which is v1, and kind of Kubernetes object, which is pod. We need to give a name to the pod, and that we are giving by using metadata and specifying sample-pv-pod as a value to name attribute. Then comes the spec where we have to be careful. We are creating volumes and we are giving a name to it. Name that we are specifying is sample-pv-storage. And then comes persistent volume claim. We are specifying test-pv-claim as value to claim name property of persistent volume claim. After specifying volumes and claim, we'll be specifying containers where we are giving name as pvc-container, image would be nginx, we are specifying a port and name, and finally we are providing volume mounts by specifying mount path, which is a particular directory of your pod, and then finally we are specifying the name of the volume mounts as sample-pv-storage. Now we need to go and create the pod. To create the pod, we'll save. To save, we'll press escape followed by :wq and we'll press enter key. Now, once we exit from the editor, we need to write command, that is kubectl followed by space apply, followed by space -f, followed by space, followed by name of the file where we have written the configuration. After specifying name of the file, we'll press enter. Once you'll press enter, you'll find that it has created the pod, and the name of the pod that it has created is sample-pv-pod. Now let's go and verify that the container in the pod is running. To do that, we'll write kubectl, followed by space get, followed by space pod, followed by space name of the pod, which is sample-pv-pod. We'll press enter. Once you'll press enter, you'll find that you have the container. This is how you can create a manifest file and configure it to create a pod configured to use persistent volume claim as a volume. In this video, we'll describe the life cycle of a volume and claim that reflects interaction between persistent volume and persistent volume claims. Now, there are 4 essential stages of life cycle of a volume and claim. Let's start with provisioning. Now, whenever there will be a request from a developer, it will be defined in form of persistent volume claim. A cluster administrator will configure one or more dynamic provisioners that provisions storage and a matching persistent volume. Another essential stage of life cycle is binding. Now, when a user creates a persistent volume claim with a specific amount of storage requested and with certain access modes, Apart from that, they can also specify storage class. You'll find that a control loop in the master will watch for new persistent volume claims. Now, there are various scenarios. It either finds a matching PV or waits for a provisioner for the storage class to create one. And once it is created, it will bind them together. Then comes using, which is another stage. In case of using, pods will use claims as volumes. Now, when it is done, cluster will inspect the claim to find the bound volume, and then they will mount that volume for a pod. For those volumes that supports multiple access modes, user specifies which mode is desired when using their claim as a volume in a particular pod. And finally, reclaiming, which is controlled by reclaim policy. Now, reclaim policy of a persistent volume tells the cluster what to do with the volume after it is released. Currently, volume can either be retained or recycled. Now, let's try to understand claim references. As a Kubernetes administrator, we need to understand how volume works together with pod. Let's try to understand it using a diagram which is currently displayed on the screen. At the bottom section, we have pod which contains a claim. In short, pod will just keep reference to the volume claim. The volume claim in turn specifies its actual resource requirement. And one of those is what type of volume binding mode need to be used. It can be wait for first consumer or it can be immediate. Depending on volume binding mode, once a pod is created, it will refer to the volume claim by name and it will find best match, where choice is performed under the restriction that the storage class name also must match. And this is how claim references will work in order to provide persistent capabilities to your pod. Finally, let's try to take up a scenario of configuring persistent volume and claim. And we'll do that using a diagram which is currently displayed on the screen. At the left-hand side, we have a namespace. Currently, we are using default namespace. Default namespace is configured with a pod. And pod has a container. Name of the pod is sample. Your pod is having a claim reference to persistent volume claim, and that particular persistent volume claim will be bound to a persistent volume. Now, how do we manage it? To manage it, you will be using a specification. At the right-hand side, we have the specification. We are using spec.template.spec, specifying the containers, giving a name to the container, specifying volume mounts by populating it with name and mount path, and then comes the volumes where we are using a name. Apart from name, we are also specifying persistent volume claim, which contains a property called as claim name. Depending on whatever name you have specified, reference will be managed by cluster in order to bound right persistent volume claim with right persistent volume, and depending on the reference of the claim specified in the configuration file, your pod will start using that particular persistent volume. So depending on your need, you need to decide what type of persistent volume you are going to create, who are the provisioners, and which provisioner you are going to select, and how you are going to manage persistent volume. In this video, we'll recall the concept of volume snapshot along with the role of volume snapshot content and volume snapshot API resources in creating volume snapshots for users and administrators. Now, what is volume snapshot? To understand volume snapshot, let's try to understand three essential features. First is it represents a point-in-time copy of volume so that you can recover whenever you need. Volume snapshot is used to restore existing or provision new volume. So when you go with volume snapshot, it will be either used to restore existing or provision new volume. Volume snapshot may not be supported by all storage systems, but yes, they are supported by multiple storage systems. So when you are planning to use volume snapshot, Be careful and use those storage systems which supports volume snapshot. Now let's explore how volume snapshot works. And the diagram which is currently displayed on the screen shows how various resources will reference to each other. We can see how a volume snapshot is binded to a volume snapshot data. This is similar to persistent volume claims and persistent volumes. Apart from that, we can also see that volume snapshot data references the actual snapshot which is taken by volume provider. In the same way, how a persistent volume references the actual physical volume backing it. This is what is correspondence between volume snapshot data, persistent volume, volume snapshot, and persistent volume claim, which we can see in the diagram. Now let's try to list certain Kubernetes snapshot API elements. There are three critical elements. First, volume snapshot. It is considered as a request for snapshot of a volume by a user. You can consider it similar to persistent volume claim, which is requested by a user. Second is volume snapshot content. It is a typical snapshot taken from a volume in the cluster that has been already provisioned by an administrator. It is a resource in the cluster which can be compared with persistent volume. And third is volume snapshot class, which allows you to specify various different attributes that belongs to volume snapshot. These attributes may be different among snapshots taken from the same volume on the storage system and therefore cannot be expressed by using the same storage class of a persistent volume claim. Now, before we start using Kubernetes snapshot, we need to meet certain prerequisites, out of which first prerequisite is CSI driver implementing snapshot is deployed and it is in running state. Second feature is you must enable Kubernetes volume snapshotting features. So when you plan snapshot, you need to consider the right storage system which supports snapshot, and then you can plan how you are going to use snapshot to restore volumes. In this video, let's describe the concept and approaches of cloning existing CSI volumes in Kubernetes. We need to know that Kubernetes introduced alpha support for volume cloning in its early version of 1.15. Now, what is the objective of this feature? This particular feature allows us to create new volume using the content of an existing volume present in user's namespace, and that we can do by using Kubernetes API. You'll have many storage systems that provides ability to create a clone of a volume. Now let's try to understand what do we mean by clone using a diagram which is currently displayed on the screen. On the screen, in the diagram at the bottom, we can see block storage and distributed file system, where you have multiple volumes. You have two different nodes of Kubernetes, Kubernetes node A, Kubernetes node B, on which you have pods. Kubernetes node A has pod A, pod B with its own set of containers. Kubernetes node B has pod C, pod D with its own set of containers. Now, a clone is duplicate of an existing volume, but it will have its own unique volume on the system. And that's what we see in the diagram. Kubernetes node A will have its own set of volumes, volume A and volume B. Kubernetes node B can have a clone of volume A and volume B, depicted in the diagram as volume C and volume D, which is being consumed by pods which are present in Kubernetes node B. Now we need to focus on steps that we'll be using to clone CSI volumes. First step is to implement checks for CSI plugin. This will help to implement volume cloning because driver is essential for cloning. In this particular step, you will implement checks for volume content source in the plugin as well as create volume function implementation. Then comes the second step, which is implement clone underscore volume controller capability, followed by deploy volume clone functionality, where Kubernetes CSI development team maintains an external provisioner which is responsible to detect requests for a PVC and provide the information to the plugin using Kubernetes API. And finally, you need to enable cloning for CSI volumes. Now let's try to understand how do we restore volume by defining storage class. To do that, we have to first create a snapshot. To create a snapshot, we'll be creating a configuration file where we'll specify kind to be storage class. API version will be storage.k8s.io/v1. Then comes metadata. We are giving name to the metadata as snapshot-promoter. Focus should be on provisioner, where we are specifying volume snapshot dot external dash storage dot k8s.io slash snapshot dash promoter. And then comes the parameters, where we are specifying type to be pd dash standard. pd dash standard is a type of storage. Now you have defined your storage class. You have to define configuration in order to dynamically provision from snapshot. To dynamically provision it from snapshot, you will start by writing API version, which is v1. Kind is persistent volume claim. Metadata is used to name your persistent volume claim. In the current case, it is sample-snapshot. But remember, most important entry here is annotations, where you are specifying snapshot.alpha.kubernetes.io/snapshot:\latest. Once you specify this, it will refer to the volume snapshot that you want to use for dynamic provisioning and restoring persistent volume claim. You need to decide as an administrator what kind of Kubernetes cloning you are going to adopt that will help you to clone your volumes, which you can later restore. In the same file, you need to also specify a spec where you need to specify access modes, which will be read-write ones, followed by resources, request, which contains storage, 2 GB that is set for persistent volume claim. Apart from that, one of the entry that you have to specify here is storage class name, which should be the same class name that you have specified in the previous slide. In the previous slide, we have used snapshot-promoter. It's the same storage class that we are specifying. So in this course, we have examined the concept, features, and how to work with storage class, Kubernetes volume, persistent volume, and persistent volume claim in Kubernetes. We did so by exploring the use of storage class in Kubernetes to classify storage types, the fields that are used to dynamically provision persistent volume of a class, the type of volumes that supports volume expansion along with the volume binding modes of storage class used to control volume binding and dynamic provisioning of instances. How to create a pod with one container and configure a volume for the pod, create a persistent volume claim that can request a volume of at least 4 GB and provide read-write access for at least one node, and how to create a pod that is configured to use persistent volume claim as a volume. How to use kubectl command to copy local files to pod and transfer pod files to local storage. The concept of volume snapshot and the role of volume snapshot content and volume snapshot API resources in creating volume snapshots. The concept and approaches of cloning existing CSI volumes in Kubernetes. In the next course, we will learn to create and work with persistent volume and persistent volume claims in Kubernetes. In this video, we'll list reclaim policies and features that can be applied on persistent volume. Before we start discussing about reclaim policies, let's try to have a quick recap of managing persistent volumes. And we'll do that by using a diagram which is currently displayed on the screen. Assume that you have hosted a cluster on Azure using Azure Kubernetes Service, where you will have components like cluster master and you will have worker nodes. Cluster master will have API server that will take responsibility of processing all the requests which are made in order to orchestrate applications. Now, applications that runs in Azure Kubernetes Service may sometimes need to store and retrieve data. For some workloads, this data storage can be local, fast storage on the node that is no longer needed when the pods are deleted. But yes, there will be workloads that may require storage that persists for a longer period of time on more regular data volumes. And that can be done using storage capabilities of Azure. Now you can have multiple pods that may also need to share the same data volume. And that's where role of persistent volume comes. In order to ensure that we are able to configure persistent volumes, we'll have persistent volume claim, which will bound to persistent volume in order to provide volume management capability, which is provided by Azure using Azure Managed Disk and Azure Files to Kubernetes cluster. If you are using this approach, you may need to inject sensitive data or application configuration information into pods that can also be achieved by managing persistent volumes. Now, what all are the reclaim policies? In order to define different tiers of storage, you can create storage class, and the storage class will have reclaim policy. This reclaim policy controls the behavior of underlying Azure storage. So whenever pod is deleted and the persistent volume is no longer needed, you need to decide what should be the policy to reclaim. There are 3 policies. First is retained, second is recycled, and third is deleted. Now let's try to understand features of retain that helps us to understand when we need to switch to retain reclamation policy. When our policy is set to retain, it will allow for manual reclamation of resources. It will also continue to exist even if you have deleted persistent volume claim to which it is bounded, but will not be available to another claim until and unless the previous claimant's data remains on the volume. Now we'll discuss about recycle. First, we need to understand that recycle is deprecated. It means it will be no longer in use for future Kubernetes versions. Typically, recycle performs basic scrub on volumes and makes it available again for a new claim. Third and final policy is deleted. In case if your persistent volume is set to deleted reclaim policy, it will be deleted when the claims are deleted. We need to also remember that default reclaim policy for dynamically provisioned persistent volume is deleted policy. And finally, if your policy is deleted, volume is automatically deleted when the corresponding persistent volume claim is deleted. So depending on your need and the way you want to manage your persistent volume and persistent volume claim, you need to set the right policy. In this video, we'll create a storage device using AWS EBS and write a manifest file to create a persistent volume that uses AWS EBS volume using kubectl apply command. Now let's go ahead and see how to configure AWS CLI. To do that, you need to ensure that you have installed AWS CLI by writing app-get followed by space install followed by space AWS CLI. Once you'll press enter, it will install AWS CLI. Assuming that you have installed, we'll go and we'll configure. To configure, you'll write AWS followed by space configure. You'll press enter. Once you'll press enter, it will ask you to specify AWS access key ID. You need to use your AWS key ID and enter. After entering access key ID, you need to also enter AWS secret access key. Post which, once you'll press enter, it will ask you default region name. Specify region name where you want your EBS to be created. Then comes default output format, which is none. You can specify JSON. Finally, you'll press enter and you'll get a prompt. Now your next step is to go and create AWS EBS volume. To do that, you'll be writing a command that starts with AWS followed by space EC2 followed by space create dash volume followed by space dash dash availability dash zone equal to US dash east dash 1A. You need to find out the right zone depending on which region you are creating your assets. After specifying the zone, you need to give a space and you need to specify dash dash size equal to 10 followed by space dash dash volume dash type. We are taking GP2. We'll specify equal to GP2 and we'll press enter. Once you'll press enter, it will create the volume. you need to copy the volume ID, which you have to use in your manifest file that you will configure to create a persistent volume, which should use the current EBS that we have created using AWS EC2 create volume command. You need to copy and retain it. Once you have done this activity, you need to create a configuration file. To do that, we'll write vi followed by space name of the file. Name of our file is c14_v3.yml. We'll press enter after writing name of the file. And then we need to specify API version, which is v1. Kind is pod. Metadata helps us to give a name to the pod, which is AWS-EBS. Then comes spec. Containers, you can select image of your choice. We are selecting an image provided by k8s.gcr.io and name of the image is test-web server. You need to give a name to your container, which is test-container, and then you need to specify the volume mounts. We are specifying mount part to be /AWS-EBS. Then comes the name, which we are giving as test-volume. After specifying volume mount, you need to configure volumes where we are specifying name to be test-volume and we are taking AWS Elastic Block Store, which has a property called as volume ID. You need to go ahead and you need to paste the volume that you have copied in the previous step. After specifying the volume ID, you have to specify FS type, which is ext4. This is how you will be creating a manifest file that creates a persistent volume which uses EBS that you have created. Let's go and save it. To save, we'll press escape followed by :WQ. We'll press enter. We'll be back to the prompt. We'll clear the screen for now. After clearing the screen, we'll use kubectl followed by space apply followed by space -f followed by space name of the file which we have created in previous step. We'll press enter. Once you'll press enter, you'll find that it has created a pod with AWS-EBS. This is how you can create a storage device using AWS EBS and write a manifest file and create a persistent volume that uses this EBS using kubectl apply command. In this video, we'll create a manifest file that creates a persistent volume claim which uses the persistent volume of AWS EBS storage device. In order to ensure that we are able to utilize AWS EBS, first we need to create persistent volume using storage device powered by AWS EBS. We have already done it in lab titled Create Persistent Volume of the current course. After doing that, let's go ahead and install the driver. To install the driver, we'll be using kubectl followed by space apply followed by space -k followed by the URI where AWS has provided the EBS CSI driver. After writing the command, we'll press enter. Once you'll press enter, it will install all the objects, or if they are there, it will update it with the recent changes published by AWS. It creates service accounts, it creates authorization objects, it creates deployments as well as certain daemon sets. We'll clear the screen. After clearing the screen, we'll be now writing manifest file that will create persistent volume claim which uses persistent volume of AWS EBS storage device. To do that, we'll write vi followed by space c14 followed by _v4.yml. This is the name of the file where we will be writing the configuration. After writing the command, we'll press enter. Once we'll press enter, we need to create 3 essential objects. First object is the storage class, for which we have to write kind, which will be storage class. API version will specify as storage.k8s.io/v1. Metadata will give a name to storage class. We are giving EBS-SC. We'll specify the provisioner, which is ebs.csi.aws.com. All these objects are already created because we have executed the statement that installs driver in the previous step. Then we have volume binding mode, which is wait for first consumer, which means that kubectl command, when you'll apply on this current file, will create storage class and persistent volume claim as well as pod. But we need to be clear that pod references the PVC and Amazon EBS volume will be provisioned only when the pod is created. And this is the reason why after creating storage class, we'll create our second object which we have to specify in pod, and that object is persistent volume claim. We are using API version after giving triple dash to separate one object construction with other. API version is v1, kind is persistent volume claim, metadata we are giving a name as block dash claim, and then we are specifying spec. Access modes is read write once, volume mode is block, and then comes storage class name which is EBS dash SC that we have specified in the previous configuration. Finally, we are going and we are setting the resources where we are specifying requests to have storage of 10 gigabytes. And finally, we'll write the configuration to create the pod that uses persistent volume claim and creates persistent volume dynamically. To configure, we have written API version after giving triple dash to separate it from previous configuration. Kind is pod, metadata we are giving a name as app, and then we are specifying the spec containers. Name is app, image is busybox. You can specify whatever image you want. Command that you want to execute on the container and arguments that you want to pass. And then comes volume devices, where we are specifying name to be data, device path to be /dev/xvda. And finally, we are specifying volumes, where we are giving a name to be data and persistent volume claim to be block dash claim. That is what is the name that we have specified for persistent volume claim. After creating this file, we'll save and exit by pressing escape followed by :WQ and enter. Now you have created the file. Your last step will be to create Kubernetes resources, and to do that you'll be using kubectl followed by space apply followed by space -f followed by space name of the file. Once you will press enter, you'll find that all the objects are created. Now you can clearly see that objects are created. These objects are EBS-SC, block-claim, and your pod, which is app. This is how you can create a manifest file in order to create persistent volume claim, which uses persistent volume that you created in the previous lab titled Create Persistent Volume. In this video, we'll demonstrate steps to dynamically create a persistent volume and let Kubernetes create an EBS via AWS API and will mount to an AWS EC2. In the previous labs, we have seen that we were working with storage by creating storage class as well as by creating storage device on AWS EBS. Now, there is another approach which we can use in order to dynamically provision storage. In order to do that, we need to create storage class object, and using that storage class object, we need to create persistent volume. And finally, we need to create persistent volume claim. We'll do that using a configuration file. Let's go and create the configuration file. To create the configuration file, we'll write vi followed by space name of the file. After writing name of the file, we'll press enter. Once you'll press enter, it will open a file where we can start writing the configuration. And first task is to create a storage class. To do that, we'll be writing API version and we'll take storage.k8s.io/v1. Post that, we have to specify storage class as the object, which will specify an attribute called kind. After specifying kind in metadata, we'll give it a name that is EBS-storage-class, and one of the important element that we have to specify is provisioner. We are specifying kubernetes.io/aws-ebs. And then comes parameters. We'll specify parameters where type is IO1, IOPS per GB is 10, and FS type is XFS. Now, once you will deploy storage class into your cluster, all an operator need to do is to come to provisioning volume for their developer and create persistent volume that uses the storage class. And that's what we are doing in the second configuration, which starts with triple dash. We are specifying API version to be v1, kind is persistent volume. Metadata to specify name, we are using AWS-PV-SC. We are giving a label where key is type and value is SC, and then comes the spec where we are specifying capacity. Using storage, we are allocating 5 GB. Access mode is read write once, and finally we are specifying the storage class name, which is ebs-storage-class, which we have configured in the previous configuration. So now after using these steps, we'll be able to define a persistent volume which will use the storage class where you have specified provisioner. Then comes the third configuration, which is for persistent volume claim. We are using API version after specifying triple dash in order to end configuration of persistent volume and start configuration of persistent volume claim. We are specifying API version to be v1, kind to be persistent volume claim, metadata in order to give a name to persistent volume claim. We are using AWS-PVC-SC, followed by spec where we are specifying access modes to be read write once, and for persistent volume claim we are specifying request with 3 GB storage, and finally we are specifying storage class name which we have configured in the first configuration. Name of that configuration is ebs-storage-class, which we will use in order to specify storage class name of persistent volume claim. And finally, we are using selector in order to match labels where we are using the same key value which we have specified in persistent volume configuration, that is type:(SC), where SC is the value of the label and type is the key. After configuring these 3 objects, which are storage class, and using that storage class in persistent volume and persistent volume claim, we'll be able to let Kubernetes create an EBS via AWS API and mount to an AWS EC2. Let's go ahead and save the file and exit from the editor. To do that, we'll press escape followed by :WQ and enter. Now we are out of editor. Now let's go and specify the command, which starts with kubectl followed by space apply followed by space -f followed by space name of the file, which is c14_5.yml. After writing the command, we'll press enter. Once you'll press enter, you'll find that it creates the required objects. This is how you can dynamically create a persistent volume and let Kubernetes create an EBS via AWS API. In this video, we'll create a manifest file and use it to create pod that uses dynamic persistent volume claim. In this particular demonstration, we'll be using dynamic persistent volume claim, which was created in video titled Create Dynamic Persistent Volume, where we created a dynamic persistent volume claim. Let's go ahead and find out what dynamic persistent volume claim we are going to use. To do that, we'll connect to master and we'll write command that starts with kubectl followed by space get followed by space PVC, which stands for persistent volume claim, and we'll press enter. Once you'll press enter, it will list all the persistent volume claims which are configured. We have one sample storage which is bound. Then we have AWS-PVC-SC, which is pending. That indicates that it is not yet bounded. Now let's go ahead and clear the screen. After clearing the screen, we'll write the configuration file. To do that, at the prompt, we'll write vi followed by space followed by the file name. After writing name of the file, we'll press enter, and then we'll configure a pod that will use dynamic persistent volume claim. To start the configuration file, in line number 1 and 2, we'll specify API version, kind will be pod, metadata will give a name to the pod, that is nginx-cloud. And then comes the spec where we are giving specifications of volumes and containers. In volumes, we are using name. To give a name to it, we have specified cloud-storage. And then we are specifying name of the persistent volume claim by specifying claim name and using the claim name of dynamically provisioned persistent volume claim, which we created in video titled Create Dynamic Persistent Volume of this course. Then comes the containers. We are using name and image. For now, we'll be using nginx. You can specify name as per your choice and you can use image of your need. And finally, we are specifying volume mounts where we are giving a name, that is cloud-storage. which we have created in the specification block of volumes. Finally, we are specifying the mount path, which is /aws/data. After creating the file, we'll save and exit, and to do that, we'll press escape in VI editor followed by :WQ and press enter key. Now we are out of editor. Let's go ahead and create the pod, which uses dynamic persistent volume claim. And to do that, we'll be writing kubectl followed by space apply followed by space -f followed by space name of the file. After specifying name of the file, we'll press enter. And once we'll press enter, you'll find that nginx-cloud pod is created. Let's go and describe the pod. To do that, we'll write kubectl followed by space followed by describe followed by space pod followed by space name of the pod, which is nginx-cloud. After writing the command, we'll press enter. Once you'll press enter, you will get details of your pod. Need to go to volume claim and look at the volume claim to which your current pod is bounded. This is how you will be able to create a manifest file and use it to create pod that uses dynamic persistent volume claim. In this video, we'll demonstrate steps to delete persistent volume and persistent volume claim. Now, before we delete, we need to be careful because persistent volume is a cluster-wide resource that you can use to store data in a way that it persists beyond the lifetime of a pod. We need to also know that PV is not backed by locally attached storage on a worker node, but by a network storage system like EBS, NFS, or distributed file systems like Chef. Our objective is to see how do we delete. Before we delete, let's go and get persistent volume claim first. And to do that, we'll be writing a command that starts with kubectl followed by space get followed by space pvc. We'll press enter. Once you'll press enter, you will get all the persistent volume claims. Let's select one of them. We are selecting sample storage, which is bound to a particular volume. In order to delete, we'll be writing a command that starts with kubectl followed by space delete followed by space pvc followed by space name. And name that we are giving here is the name of the pvc, which is test-pv-claim. After writing the command, we'll press enter. Once you'll press enter, you will get a message that indicates persistent volume claim. Name of the persistent volume claim is getting deleted. We'll wait for some time for PVC to get deleted. Now, once delete is over, we'll clear the screen. After clearing the screen, our next objective is to delete persistent volume. To do that, we'll write kubectl followed by space get followed by space pv to get all the persistent volumes which currently exist. Once you'll press enter, you'll find all the persistent volumes which are there. Let's go ahead and delete task-pv-volume. To do that, we'll write kubectl followed by space delete followed by space pv followed by space task-pv-volume. After writing the command, we'll press enter. Once you'll press enter, you'll get a message that indicates that task-pv-volume is deleted. Be careful when you are deleting. You need to ensure that you are managing claims as well as pods which are using those persistent volume for their internal use. This is how you can delete persistent volume and persistent volume claim. In this video, we'll demonstrate steps to change reclaim policy from retain to delete for persistent volume. Let's go ahead and see what all are the current persistent volume and what all are their status. To do that, we'll connect to master and at prompt, we'll write kubectl followed by space followed by get followed by space followed by pv. After writing, we'll press enter. Once you'll press enter, you'll find whatever persistent volume are created. We have a persistent volume that is sample-pv-volume and its reclaim policy is retain. Now from retain, we have to change the reclaim policy to delete. In order to do that, let's first understand what happens in retain. Retain claim policy will allow for all manual reclamation of the resources. when the persistent volume is deleted. So when you delete persistent volume claim, the persistent volume still exists and the volume is considered as released. But it is not yet available for another claim, because you'll have some previous claimant's data remain on the volume. As an administrator, we can manually reclaim the volume using certain steps. Let's go ahead and change the reclaim policy. To do that, we'll be writing command that starts with kubectl, followed by space patch, followed by space pv, followed by space name of the persistent volume. We'll specify sample dash pv dash volume. Then we'll specify space dash p, followed by single quotes, and within single quotes, we'll start our curly braces. Within curly braces, we'll specify key value, what we want to change. We'll specify spec within double quotes, followed by colon, followed by start of the curly brace. And within start and end of the inner curly brace, we need to use double quotes. And within double quotes, we'll use persistent volume reclaim policy. After closing double quotes of persistent volume reclaim policy, we'll give a colon, and within double quotes again, we'll specify the new policy, which is delete. Finally, after writing the command, we'll press enter. Once you'll press enter, you will get a message that will indicate that persistent volume named sample-pv-volume is patched. Now let's go and write kubectl, followed by space get, followed by space pv, and press enter. Once you'll press enter, you'll find that sample-pv-volume and its reclaim policy has changed from retain to delete. This is how you will be able to change reclaim policy from retain to delete for persistent volumes. In this video, we'll create a persistent volume using an existing Google Compute Engine persistent disk populated with data and use it in a pod. We'll go with assumption that we have Google Compute Engine configured with persistent disk, which is already populated with data. Now we need to use a pod. To do that, we need to configure a file. And configuration will be done by opening the file, where we'll use vi, followed by space, name of the file. Now in the current file, we have taken API version to be v1 as usual, kind is persistent volume. Then comes the metadata. We have given a name and UID, followed by annotations, where we are using first annotation as kubernetes.io/created by. We are specifying GCE-PD-dynamic-provisioner to indicate that provisioner would be Google Cloud Engine. Then we are specifying another essential annotation, that is pv.kubernetes.io/bound-by-controller yes, followed by pv.kubernetes.io/provision-by, and we are specifying kubernetes.io/gce-pd. And then comes spec, where we are specifying access modes to be read-write once, capacity to be 30 GB, which is specified in storage attribute of capacity, followed by claim ref, where we are specifying persistent volume claim, which starts with API version, v1, kind persistent volume claim. Name that we are giving to persistent volume claim is pvc-demo, and you need to ensure that you are using the right UID. After specifying claim ref, we need to specify GCE persistent disk, where two essential entities are fs type, which is ext4, and PD name is gke-cluster-1-pvc, followed by alphanumeric number that you will get from your Google Cloud Engine. Then comes node affinity. For now, we have specified required, and it will follow affinity using match expressions, which is specified in node selector terms. In match expressions, we have specified key to be topology.kubernetes.io/zone, and operator that we are using is in. Values us-central1-c, and key is again to specify the region that we are doing by using topology.kubernetes.io/region. Operator is in, and value is the region where you have your compute engine. Finally, reclaim policy we are specifying to be delete by using delete value in persistent volume reclaim policy attribute. Storage class name we are giving as standard, volume mode is file system, and finally status we are specifying by giving phase to be bound. This is how you will be able to write configuration file that creates persistent volume on an existing compute engine. We'll save the file and we'll exit. To do that, we'll press escape followed by :WQ. We'll press enter. And your final task is to use kubectl followed by space apply followed by space -f followed by space name of the file where you have the configuration. After specifying name of the file, we'll press enter. Once you'll press enter, you'll find that it has created persistent volume using configuration that specifies use of existing compute engine, persistent disk populated with data that can be used in a pod. In this video, we'll describe concept of node affinity and recognize various phases of volume. Now, what is node affinity from perspective of Kubernetes? Node affinity is set of rules which is used by scheduler in order to determine where a pod can be placed. Typically, we can say that it defines those rules which are used by scheduler to decide proper node placement. Node affinity can be classified as required and preferred. When we use node affinity, it allows pod to specify affinity towards group of nodes. And finally, node affinity can be configured using pod specification file. So remember, when you are configuring a pod, you can define node affinity. Now, how do we configure node affinity rules? In order to configure node affinity rule, we'll be creating a specification file. Let's go ahead and see what will be content of that specification file. It will start with API version, which will be set to v1. Kind will be pod. Metadata will be used in order to give name to the pod, which in current case is sample-node-affinity, followed by spec in order to specify specification. Under spec, you will have affinity. Under affinity, you will have node affinity, where you will define what type of affinity you expect. You are using required during scheduling, ignore during execution. After specifying node affinity, you will also specify node selected terms, and below node selected terms, you'll specify match expressions which will contain key, which is specified here as E2E-AZ-north-south. This is what is the key which is specified. Then comes operator, which you have specified as n. Now, match expression parameter in the pod specification can have n, not n, exist, or does not exist. Apart from that, you can also use less than or greater than in order to write proper match expression powered by operator. Now, let's go ahead and see the values. Values in the current case are E2E-AZ-north, E2E-AZ-south, and then comes the containers where you have to specify the name, which is sample-node-affinity, and image, which is docker.io/ocpque/hello-pod. Once you have configured this file, you have set a rule that requires the pod to be placed on a node with the label whose key is E2E-AZ-north or E2E-AZ-south. Depending on the configuration, it will add affinity capability to your pods. Now let's try to understand volume provisioning. Now there are two different ways in which we can provision. First is static provisioning. Second is dynamic provisioning. Let's try to understand what happens in static provisioning. As the diagram present at the left of the screen shows static provisioning, where developer will start creating an object. That object will be of type persistent volume claim. In response to that particular request, persistent volume will come into play that will be created by admin. Step 3 will be to bind persistent volume claim with persistent volume. And then comes the pods. In pod specification, you will be specifying reference to your persistent volume claim as it is specified in the diagram. And finally, persistent volume will be using a storage that will be provisioned by administrator. This is example of static provisioning. Now what happens in dynamic provisioning? In dynamic provisioning, you'll be creating a storage class using a particular volume plugin as it is displayed in the diagram at the right, and that volume plugin will provision persistent volume using external storage. Now for persistent volume, you need to create persistent volume claim so that you can bind, and that persistent volume claim will be used in pod specification in order to mount volume. This is what is fundamental difference between static provisioning and dynamic provisioning. Now let's try to quickly go through phases of volume. Your volume can be in 4 specific phases. First is available, which means a free resource that is yet not bound to a particular claim. It means your persistent volume is still not bound to a persistent volume claim. Second is bound, which means now your volume is bound to a claim. Released means the claim has been deleted, but the resource is not yet reclaimed by the cluster. Finally, failed, which indicates that volume has failed its automatic reclamation. So by understanding node affinity, you'll be able to set rules that will be used by scheduler in order to decide node placement. So typically, if you want your scheduler to follow a policy to place the pods on different nodes, you have to go with node affinity. And finally, you need to also visualize volume phases in order to know their current status. In this video, we'll describe the maximum number of volumes that can be attached to a node for various cloud providers and recognize approach to configure custom limits. Now let's first list different types of volumes supported by Kubernetes. First is AWS Elastic Block Store, which mounts an Amazon Web Service EBS volume into your pod. Second is Azure Disk, which mounts a Microsoft Azure Data Disk into a pod. Third is Azure File, that mounts a Microsoft Azure File volume into a pod, followed by Chef FS, which mounts an existing Chef FS volume into your pod. And finally, Cinder. It is used to mount OpenStack Cinder volume into your pod. Now, after going through diversified kind of volumes that can be mounted, let's try to understand how persistent volume works in Kubernetes. As an admin, you will be creating pool of persistent volumes for which you can use kubectl commands after defining configuration in YML files. Now you will have a list of persistent volumes which are created. Now comes developers. Developers want to use your persistent volume, for which they will claim persistent volume. Now, once they claim, depending on storage class, appropriate persistent volume reference will be passed on to developer, which will be claimed while they are creating pods. This is how persistent volume mechanism works in Kubernetes. Now comes types of limits that can be specified on volumes. There are two. First is custom limits. These are the limits which can be changed by setting the value of cube_max_pd_vols environment variable. Second is dynamic volume limits. Now, these limits are not supported by all volume types. If you are going with cloud providers like Amazon EBS, Google Persistent Disk, Azure Disk, or CSI, you'll find support of dynamic volume limits. Now let's try to list Kubernetes default limits, and we are considering Kubernetes version 1.19. We are going to consider cloud services. Amazon Elastic Block Store maximum volume per node can be 39. Google Persistent Disk maximum volume per node can be 16. Microsoft Azure Disk Storage maximum volume per node can be 16. Keep all these limits in mind and then decide what type of volume you are going to utilize in Kubernetes. In this video, we'll create a pod with 2 containers that uses an empty dir volume to exchange data. Now let's try to understand what is role of empty dir first. An empty dir volume is first created when a pod is assigned to a node and exists as long as pod is running on that particular node. As the name itself indicates that empty dir volume will be initially empty. Now once it is initially empty, all containers in the pod can read and write the same files in the empty dir volume, though the volume can be again mounted at the same or different paths in each container. So let's go ahead and create a configuration file that creates 2 containers along with empty dir volume. To do that, we will connect to the master and will write vi followed by space name of the file. After writing name of the file, we'll press enter and we need to enter certain configuration details. That starts with API version, which we have specified to be v1. Kind is pod. Metadata in order to associate name to the pod will be test-pd in current case. Then we have spec, where we can see configuration of 2 containers and a volume. First container uses image, that is k8s.gcr.io/test-web server, and we are giving it a name called test-container. Then comes second container, which is using image called Ubuntu, name is test2, followed by volume mounts, which we are specifying as mount path /cache and name is cache-volume. And finally, we are specifying specifications for volumes, where we are giving it a name called cache-volume, and volume that we are creating is empty dir, and this is the reason why we have empty dir : followed by empty curly braces. We'll save the file and we'll exit. To save and exit, we'll press escape followed by :wq and press enter key. Now let's go ahead and create the resources. To do that, we'll write kubectl followed by space apply followed by space -f followed by space name of the file, which is c14_v12.yml. After writing name of the file, we'll press enter. Once you'll press enter, you will get a message that indicates that pod is created, and this pod is configured with 2 containers that uses an empty dir volume, which can facilitate an exchange of data among all containers of the pod. In this video, we'll create a deployment that uses persistent volume claim to mount it as a volume. Let's go ahead and create a configuration file where we'll first create persistent volume followed by persistent volume claim, which will bound to the persistent volume, and then we'll go and we'll create the deployment where it will use persistent volume claim as volume. To do that, we need to write a configuration file, and to write a configuration file, we need to use an editor. We are using vi editor, so we are writing vi followed by space name of the file. We'll press enter and it will launch vi editor. Now let's go ahead at the top. Our first object that we are going to create is persistent volume. To do that, we are specifying API version to be v1, kind to be persistent volume. Then we are giving a name to it in metadata along with the label. Name is pv-volume-example, and label that we are using is type as key, local as value. Then comes spec, where we are specifying storage class name. We are taking manual storage class, and then we are going for capacity, where we are specifying storage to be 10 GB. Followed by access modes, where we are specifying read write once, followed by host path in order to specify path of the mount. To do that, we have specified path to be in double quotes /mnt/data. This will help us to create an object of type persistent volume. We'll specify // in order to separate and create another configuration in the same file to create an object of type persistent volume claim. To do that, we are using API version to be v1, kind to be persistent volume claim. Metadata to specify name, we are using volume-claim. Followed by spec, where again storage class name we are giving as manual, because persistent volume that we have defined is using manual. Then comes access mode, which is read write once, resources that we are specifying for volume claim is requests. Under requests, we are using storage to be 3 GB. After defining persistent volume claim and persistent volume, now we need to create an object of type deployment where we'll be using persistent volume claim as volume. To do that, after triple dash, we are using API version, which is equal to apps/v1, kind is deployment. We are giving name to our deployment as nginx deployment, which contains a label called app, which is the key, nginx, which is the value. Next, we have to specify specifications where we need to specify replicas. We are giving 3 selectors where we are using match labels in order to specify key and value of label, that is app and nginx, followed by template where we are using metadata. Under metadata, we are specifying labels and we are using the same label key value, which is app nginx, followed by spec, which is the most important part of the current deployment configuration, where we specify containers, volumes. Containers need to be specified with 3 essential properties. First is image, we are using nginx. Second is name, which is test nginx. Volume mounts, we are specifying mount path and name. Name we are giving as volume. And then finally, we are specifying volumes where we are giving the same name that we have specified below volume mounts. Below volume mounts as volume, so we are specifying the same name, followed by the final element, which is persistent volume claim, which contains a property called as claim name. We are specifying volume dash claim, which is the same persistent volume claim that we have configured in the current file. Now we'll create the objects. To do that, we'll press escape followed by :wq. Now, once we are out of the editor, we need to execute kubectl apply command to create all the necessary objects. To do that, we'll write kubectl followed by space apply, followed by space -f, followed by space name of the file, which contains configuration of persistent volume claim, and deployment, which is configured to use persistent volume claim as volume. After specifying name of the file, we'll press enter. Once you'll press enter, you'll find that it creates persistent volume. It also creates persistent volume claim, and it creates your deployment, which is using persistent volume claim to mount it as a volume. In this video, we'll create a pod that mounts the NFS volume provisioned in a Docker container on the master. Now let's assume that we have provisioned the required NFS volume. Now we want to create a pod that uses that particular volume. To do that, we need to configure again persistent volume claim, and a pod in order to ensure that we are able to show the relation. Let's go ahead and create the file. To do that, we will write vi at the command prompt after connecting to master, followed by space and name of the file where we have that configuration. We'll press enter. Once you'll press enter, you'll find 3 essential objects which are similar to video title mount PVC on deployment. Instead of using regular storage class and persistent volume claim, we are going to link it with NFS. To do that, our first task is to configure persistent volume, where we'll have API version to be v1, kind will be persistent volume, metadata will be used in order to specify the name that is specified as NFS-PV. Then comes the spec, where we are specifying capacity of storage to be 1 GB, followed by access modes, which is read, write, many. One of the important element that we are configuring here is persistent volume reclaim policy, which is set to retain. And then comes the NFS configuration, where we are specifying the path and the server. You can also specify IP address of NFS server, which you will get from your NFS administrator. Finally, we are specifying read-only to be false. After declaring persistent volume, assuming that you have created NFS, which is powered by Docker, you have to create a configuration for persistent volume claim. That we are doing by using triple dash in order to separate the configuration, and again we will be using API version to be v1, kind to be persistent volume claim, metadata to give a name to the claim, that is NFS-PVC, and then comes access modes, which is read, write, many, And finally, we'll specify resources and request of storage capacity that need to be specified for persistent volume claim, which in current case is 1 GB. And finally, we'll create a pod. To do that, we'll use API version to be v1, kind to be pod, metadata in order to give a name to the pod, which is sample-nfs-pod. We'll specify labels where we are giving label as sample-nfs-pod. And then comes the spec where we are specifying containers with property name, which is sample-nfs-pod, image is nginx, ports that we are using is container port 80. We are giving a name to the port, which is web. And finally, we are specifying volume mounts with a name called nfs vol. We are specifying mount path, that is usual mount path of nginx, which is specified using /usr/share/nginx/html. We can also give security context where we can specify supplement groups with a number that is specified in square bracket, followed by privilege set to false. We need to understand that supplemental groups is the ID that need to be assigned to the container. We can say it's group ID that will be assigned to the container. And finally, volumes, where we are specifying name, which is nfs vol, and persistent volume claim is the claim name that we have created in the previous configuration while creating an object of type persistent volume claim. We are using the same name, that is nfs-pvc. This is how you will be able to create a pod that mounts nfs volume provisioned in Docker container on the master. Let's go and run it. To do that, we'll press escape followed by :wq to save and exit. Once we are out, our next task is to use kubectl apply command in order to create the desired objects. To do that, we'll write kubectl followed by space apply, followed by space -f, followed by space name of the file. Now, assuming that all the entries that you have made related to NFS are correct, we'll press enter. Once you'll press enter, it will create a pod that mounts NFS volume provisioned in a Docker container on the master. So in this course, we have examined how to create and work with persistent volume and persistent volume claim in Kubernetes. We did so by exploring the reclaim policies and features that can be applied on persistent volume and how to change the reclaim policy from retain to delete for persistent volume. How to create a persistent volume that uses EBS. Create a persistent volume claim which uses the persistent volume of AWS EBS storage device. Dynamically create a persistent volume and mount to AWS EC2 instance, and how to delete persistent volume and persistent volume claim. The concept of node affinity and the various phases of volume. The maximum number of volumes that can be attached to a node. How to configure custom limits and create a pod with two containers that uses an empty dir volume to exchange data. How to create a deployment to mount it as a volume, and how to create a pod that mounts the NFS provisioned in Docker container to the master node. In the next course, we will learn how to implement logging in Kubernetes.